Hey everyone, and welcome back to PrepFusion. I am Anish, and today we will start with the marathon 4 of power system. So today we will discuss about power system stability. So we will cover the swing equation of generator very comprehensively with basics, right? I will derive the swing equation. Then we will discuss about steady state stability limit, steady state stability. Also we will discuss about transient stability. Obviously the most important criterion is the equal area criterion. That also we will discuss, okay, with more problems. Like it will be almost around 10 hours of marathon with huge number of problems. So I have tried to take as many problems as possible, so that in gate examination you should not leave the question, you should be able to attempt the question, okay. Also if you are enjoying these marathons, make sure to hit the like button, okay. Don't forget to hit the like and comment down below whichever portions you enjoyed the most. And of course we have covered these marathons previously, right? Marathon 1, marathon 2, marathon 3, about the faults, right? Symmetrical fault, unsymmetrical fault, and basics of power system. If you want the notes, you can go to the pinned comments in the video there. Currently the course is, for now it is free for all, so you can access the course and get the notes, watch the lectures, whatever you want to do, you can get the notes from there, okay. So that's it basically. We will start with power system stability. Thank you. Hi everyone, and welcome back to PrepFusion. So today we will start a new topic, that is power system stability. Okay, so we learned about fault analysis, how to do the analysis of a fault. But what happens when there is a fault? What happens to the power system, right? Like we know high current will flow, right? Due to that high current, our generator can go into instability. How can I understand this? Because if you see, if I am suddenly changing the load, because in fault what happens? It is a low power phenomena. So power suddenly goes to zero. If power suddenly goes to zero, I'm still giving the synchronous machine some mechanical input. So output power is going to zero. We know in a synchronous machine, if I have a rotor, right? If I have a prime mover, we know that the prime mover, we are providing it some mechanical torque Tm, and it is generating some opposing electrical torque. This we have learned in electrical machines. Why this opposing torque comes? Every action will have an equal and opposite reaction, right? So this Te is developed due to the electrical power demand from the machine, right? And Tm is developed by the myself, mechanical input to the machine. So if suddenly power goes to zero, electrical power suddenly goes to zero, because during fault it is a low power phenomena. So suddenly this Te will go to zero. If this Te goes to zero, what will happen? If this Te suddenly goes to zero, suddenly this opposing torque is gone. If this opposing torque is gone, now the rotor will accelerate. Rotor will accelerate because I don't have any opposing torque. Previously it was rotating, the rotor was rotating with a constant speed, but I only have now a forward moving torque, that is Tm, right? So it will now accelerate. If it accelerates, the speed will increase. Speed will increase. Okay. So that is the problem over here, right? So if the speed increases, what will happen? The rotor angle will increase, right? So it will move toward instability. So we will discuss about those things today. So just before starting, if I hope you have already, if you have not studied, please study the electrical machines, right? At least the synchronous machine chapter. A lot of things will be learned. So that's why we are moving in a sequence. First I completed electrical machines. Now we are moving into power system, which is a application. The stability part is the application of that synchronous machine, right? Wherever we discuss the stability of synchronous machine. So we will continue with that discussion. Yes, of course, I will again explain few things from scratch here as well. But I would really appreciate if you go and watch these two videos. This will help understanding this current video even better. Okay, so that's my own suggestion, that please go through this quickly. Even if you have watched, make sure you go through this quickly again, once again, or go through the notes once again. Okay, so let's start. So what is power system stability? Like, what is stability? Stability means if I'm giving some input and I'm getting some output, if I'm giving some stable input, the output also should be stable, right? So for a stable input, the output should also be stable, right? So finite and control. So if I'm giving some stable input, the output should be stable. Now that is what BIBO stability is. That is what you will learn in signals and system, right? But in the input, let's say there is some finite disturbance. So input was, let's say this was my input, but suddenly what happened? I had a bit of disturbance in the input, right? due to some noise or whatever, suddenly the power gone down or something, right? And due to this disturbance, the output should not go towards instability. What do I mean by instability? So we know if the synchronous generator goes out of synchronism, then either the power will go to zero or it will rotate at a very large speed, right? So what will happen to the output of the synchronous machine motor is that this, if normally when the power was constant or the input was constant, then the speed also was constant. But suddenly there is some disturbance. Due to those disturbance, what happened? My motor is going towards instability. That means it will increase, and it will keep on increasing. So it is not constant, or it is not going to zero. It is going unbounded. That is, the output is going unbounded. That is infinity. I'm giving some bounded input. I'm getting output as unbounded. So those kind of systems are called as unstable system, right? So we will get a condition here, right, in power system stability, that when should I clear my fault, right? If I don't clear my fault before that time, critical time, then my power system will go out of stability, it will go out of synchronism. So that is what we will learn actually. That is what we will learn. So our main purpose is to understand what is the critical time before which output, what is the critical time before which output or generator, like in our case synchronous generators, synchronous motors and generators, or synchronous machines. Mainly we will like do the analysis of synchronous machines only. Synchronous machine will go out of synchronism. So if I don't clear my fault, synchronism, so understand what is the critical time before which I should clear, before which otherwise, before which I should clear faults in power system. Otherwise synchronous machines will go out of synchronism. Okay, so like that is the main purpose of this chapter. So here what they have told, telling that for a given small disturbance or fault, the system which should be able to return to steady or control state without runaway oscillations are called as like stable systems, right? And which are not able to return to their stable state are called as unstable systems. So there are mainly three kinds of stability that we are concerned in power systems. So first one is the frequency stability, okay, next one is the voltage stability, and the last one is the rotor angle stability, and this is what we will learn in this whole chapter, right? So what is frequency stability? So due to some fault or something, right, or due to some changes, due to some disturbances, the frequency varies. We know all our supply has a like frequency variation. It is not exactly 50 hertz. It is not exactly 50 hertz. There will be some variation. It cannot be exactly 50 hertz, but we try to be as close as possible to the 50 hertz. So generally our IE standard says that it should be 50 hertz plus minus 1%. That is, generally you will see your supply will be between 49.5 hertz to 50.5 hertz. Okay, so that is what your frequency must lie between. Okay, so this is what you have to understand about frequency stability. Okay, so what are the root cause? It occurs in if generation and load mismatch is there. So if remember, we studied the droop characteristics in machines, right? Droop characteristics. So there we learned that if there is a load variation, load sharing variation, then the frequency changes, right? So this is called as the frequency stability. Right, now what about the voltage stability? Again the same thing, right? If like current is flowing through a wire, so I have my voltage source here, then I have the transmission line, and then finally it is the terminal voltage. So of course current is flowing, so of course there will be some drop. If I am connecting higher load, the drop will go higher, right? Drop will go higher because current will be high. If current is high, drop will go high, so the terminal voltage can go down. So we have limit for this, so it can vary between, in our Indian standard rules, it can vary between plus minus 6%, right? So this is called as voltage stability. Although there will not be much problem due to voltage stability, because ultimately what will happen, your voltage will go down. If your voltage goes down, what will happen? Basically your equipments will not turn on, they will remain off, because it does not operate in low voltage. In low voltage there is no problem of fault, there is no problem of like system getting damaged, right? High voltage can damage, so open circuit faults can damage, right? But it is low voltage, so it will not be a problem. Okay, so this usually happens when does the voltage drop usually? So one is the reason when the current is huge. Another reason, I already told you that our reactive power demand sent is proportional to voltage. So if it is able to send enough reactive power that the load is demanding, then the voltage will be higher, right? If I am not able to if I am not able to complete the reactive power demand, or voltage depends on the reactive power, if I am not able to complete the reactive power demand, the voltage will drop sharply. Okay, that is what they are telling. This I have discussed, right? So active power depends, is related with the load angle, like this delta angle difference between the two voltage sources, and reactive power actually depends on the voltage magnitude difference, right? So yeah, that is what they have written. So during what is the effect of fault? During fault, voltage dips further because there is a sudden increase in the fault current in the bus. How there is sudden increase in the fault current, I will explain. So let me copy this diagram. Let me delete this, actually this is not, let me take it to the previous page, that would be the best thing. Yeah, so how does this affect, like basically how voltage goes low during a fault? So let's assume that we have a power system here, right? So these are just buses, right? So I have 1 2 3 4 4 buses, and let's say in this whole power system I have only one generator. Okay, this one generator is there. So there are three loads. This is taking 20 amperes of current, 20 amperes of current, 20 amperes of current. Total I am taking 60 amperes of current. So previously when everything was like working normally, so here I was transferring like power very normal, right? It was here, it was delivering 30 ampere, here 30 ampere, it was 10 ampere, 10 ampere. So it was symmetrical. But let's take a case, if some fault happens in the line, this line, if some fault happens in this line, of course what I have to do, I have to isolate this line. I have to isolate this line. So if I isolate this line, I have to remove this line, right? Still the load, like the fault has occurred in this line, but load is connected, so I have to deliver power to the load, right? I cannot say no मैं load पे power नहीं दूंगा. Like let's say like some fault has occurred in Kashmir, and our India is in it is a interconnected network, and you are here in Bangalore. So some fault has happened in Kashmir and you are here in Bangalore. So they will say, because the lines are connected, you will they will say, the electricity guys will say, look, what we have to do, we have to disconnect the line here. So if I disconnect the line, I won't be able to supply you the power. Will you accept it? No, right? You will just throw shoes at them, because you will say, why I will suffer if there is a power fault in Kashmir. So of course power needs to be sent, right? We will, because it's an interconnected network, we have multiple paths to send the power. So instead of choosing the easiest shortest path, now I have to choose the longest path, right? What is the problem? So this current will go up to 60 amperes now, because why? Because this was providing 30 amperes of current, now it does not have any 30 amperes of current, right? So that additional 30 amperes of current has to flow through this path. So through this, total 60 amperes of current will flow. If total 60 amperes of current flows, that means what? That means what? Current has increased. That means there is huge voltage drop here. Voltage drop has doubled. So this point, the voltage will reduce, right? The terminal voltage of the loads will reduce. So the voltage, there will be voltage drop across the loads. So what is the I hope you have understood what is the effect of fault in buses, right, in a power system. So what will happen? Due to fault, we will observe voltage drop in power system. We will observe voltage drop in power system, right? So this is the problem, right? We'll observe a voltage drop in the power system. So if I observe a voltage drop in the power system, what will happen? Voltage drop across the loads in the power system, across the loads. So what will happen? Voltage will go down across the load. So what will happen? Basically, the equipments will not turn on. That is what will happen. The equipments will simply not turn on, and that's fine. They will not turn on. Okay, so it's not a big problem, but it is a problem still, right? So of course you don't want voltage to go down too low. So that is the problem. That is the problem here. So I hope you have understood what is the effect of fault. Now the final one is the ultimate one that we want to discuss, because why is this so much of importance? Because these things, right, these things can be sorted in the power system, okay, but this thing is a machine problem. It is a machine problem, right? So if the generator itself goes out of synchronism, that is a problem, okay, it can lead to instability. So of course we don't want that. So that's why we will study. So in power system stability, we actually study only the rotor angle stability. Okay, so this refers to the ability of the synchronous generator to remain in synchronism with each other after disturbance. Do you remember what was the power that used to keep the synchronous machine in synchronism? We derived this, right? I hope you remember. It was the synchronous power. It was the synchronous power. So synchronous power was the power that used to keep my machine into synchronism even if there is some small disturbance, right? So it focuses on how the rotor angle of all generators stays within the safe limits. What is the safe limit? We will see. Okay. So causes of rotor instability: large disturbances like faults near generator, line outages, sudden large load changes. So uh, I hope you remember this equation. This was the most used equation that we derive. Our synchronizing power, also called as the accelerating power, PA, also called as the accelerating power. PA was equals to, there I just ignored the angle discussion there, but here today we will discuss what do you mean by angle, because that was not important in that lecture. In the machines lecture, the angle was not that important. What do you mean by angle? I will explain. So PA for a generator, it is equals to PM minus PE into M, moment of inertia. Like I will derive this expression, don't worry, I will derive this, okay? D theta E T upon dt square. Okay, d theta et upon et square. So if there is sudden change, right, if the load suddenly goes to 0, what will happen? I told you, right, the reverse torque will go to 0, t will go to 0. If t goes to 0, there will be acceleration. So rotor angle will just keep on accelerating, it will keep on increasing, right? The angle difference between the stator mmf and the rotor mmf will just keep on increasing, right? So that's why we have to study all this. That's why we have to study all this. So uh, so faults, if such sudden fault happens, power goes to zero, right? Line outages also, like it's just basically faults. If there is sudden load change, if the load increases suddenly, then also the rotor angle, it will deaccelerate. If it deaccelerates, then also the rotor angle changes, right? Or if there is poor system damping, because we know we have damper windings that used to oscillate the like this slow changes, right, across the rotor angle. Because if you see in the graph, right, if you remember, how is to our rotor angle change. So this I derive in the machines lecture, right? So it does not initially go to the steady state, right? The rotor angle, it just oscillates around the steady state, then finally after few cycles it reaches the steady state. If there is not enough damping present, because we solved it for undamped system as well, there the rotor angle was fully oscillating like this, right? It was never stopping. So we need proper damping. If there is poor damping, right, then our rotor will just keep on oscillating. That's the problem. Okay, so that's the problem, right? So one more thing is there. Let's say our rotor angle of generator is varying. So delta G is varying, and it is varying very slowly, very small. Okay, the variation in delta G is very small. It's like very minuscule, right? You're not even able to observe it. Okay, but the problem is, if this delta G changes, what will happen? Then the power flow also will change. Let's say there is a motor connected, then the power flow also will change. If the power flow also will change, right, here your power flow will change. If power flow changes, this motor, because delta is varying there in the generator, motor delta also will vary. So delta M also will vary. Okay, delta M also will vary. So that's a problem. Right? Delta M also will vary, right? Okay, so what will happen? So delta M also will vary. It will have some frequency of oscillation. So what will happen? These two frequencies of oscillation both are varying. Both will resonate. Like small variations, if the frequency of oscillation of generator, let's say, is Fg, and if the frequency of oscillation of motor is Fm, and if Fg is equals to Fm, then what will happen? Then they will both will resonate. It is a resonant condition. And in resonance, you know, right, in resonance either the voltage goes very high or the current goes very high. This we have seen, right? In resonance, what happens? In network theory, we have seen either the voltage peak happens or the current peak happens. So voltage will go very high or current will go very high. That is not good for us, right? It is just like a fault. So this is also another problem with rotor angle variations. Okay, I hope it is clear. So before starting the power system stability analysis, few assumptions I will take. Okay, so this, if I wouldn't have told to you, you would not have cared, but it's my duty to say everything to you. It's my duty to be honest, everything about honest. Like, I know your partner may not be totally honest, but I have to be honest with you. Okay, as a teacher, I have to be honest. So the thing is, first assumption is the whatever analysis we will do, the assumption is the frequency will remain constant. The terminal frequency will always remain constant across the buses. We are not discussing about the frequency variations, right? So frequency will be constant. This is the first assumption. And the second assumption is the field excitation voltage EF is assumed to remain constant and unaffected by variations in rotor speed. The field excitation voltage EF is assumed to remain constant and unaffected by variation in rotor speed. So if there is some rotor speed variation, EF voltage of the generator will remain unaffected. It will be constant. No matter what, it will be constant. Okay. So EF voltage of the generator and the motor, of course, and the terminal frequency, basically the voltage and the frequency are constant. We are solely discussing about the rotor angle. Okay, solely discussing about the rotor angle. So let's understand, like, what is rotor angle stability. So rotor angle stability refers of the ability of the synchronous machine in a power system to maintain synchronism with each other even experiencing a small disturbance. Okay, even experiencing a small disturbance, it will regain back to its stability. Okay, so let's say if I'm giving some, like what is our stability. So rotor angle stability is, so rotor angle stability refers to the ability of the synchronous machine in a power system to maintain in synchronism with each other even after experiencing small kind of disturbances. So even after experiencing disturbances, right? I'm not saying small disturbances. So uh, there can be many types of disturbance. One disturbance will be sudden disturbance. Suddenly the load has changed. That is what, when fault has occurred, right? Suddenly the load has gone to zero, right? Another kind of disturbance are known as gradual disturbance. Okay, gradual disturbance. Okay, so we have like sudden disturbance, gradual disturbance. So gradual is the study of steady state stability. Steady state stability. And sudden is the sudden disturbance is the study of the transient stability. So of course we'll study both of them, right? We'll study both of them, but today we will discuss about steady state stability. If I gradually change my load, what happens, right? If I gradually change my load, what will happen? Okay, so we will discuss. So we will discuss about like what happens if the speed changes. If the speed changes, the frequency also tries to change, uh, which is proportional to the speed, right? So if the speed of the rotor changes because the opposing torque is not there, of course it is proportional to the frequency, which will also try to vary. Okay, but I have told you frequency, we will assume it to be constant. So there will be some other disturbances that we will see, right? That we will see because our frequency is dependent on speed. So frequency also will try to vary. Which we will not let it, like actually frequency will vary, but our assumption is frequency does not vary, but in reality frequency will vary. So we have to somehow analyze that even if some small disturbance have been given, there will be for split second there will be bit of instability in the synchronous machine, then again it will regain back its stability to make the frequency constant. Okay, so we have to identify the condition. So what is steady state stability? So we know a generator, right? Generator, what is a generator? In a generator we have a load connected, right, which is demanding some electrical power, and of course we are giving the input as some mechanical power. So whenever there is some mismatch, there will be some problems, right? If the mismatch is happening gradually, so minor load changes. So let's say if there were previously 1 2 3, so I have 3 loads connected, and let's say I suddenly remove one of the loads, right? And each of them were taking 5 amperes of current or 5 kilowatt, whatever power they were taking, right? Suddenly I remove one of the loads, then what will happen? If I suddenly remove one of the loads, then the load reduces, right? But not instantly. If I disconnect all of the loads, then there is a problem. But if I just disconnect one of the load, that's not a problem. Again, if I disconnect the second load gradually, slowly, right? So slowly the rotor angle will change. There will be some instabilities. So we will study those instability, right? Because we know that the power P is dependent on EV by X into sine delta. So E and V are constant. I have told you. X is constant. It will not change. So delta will change, right? Okay, so initially if I am changing my load gradually, what will happen is, if the system is stable, if my machine is stable, so the speed of the machine will feel a jerk for a second. So initially it was rotating with synchronous speed, right? Omega s, it was rotating. Let me make the graph bigger. Okay, so not omega, sorry, omega r, time. Initially it was rotating with the speed omega r. Initially it was rotating with speed omega r. Then what happened? Sudden disturbance, right? Sudden disturbance happened if the load got reduced. So there will be bit of speed jerk in the speeds. Okay, there will be bit of jerk in the speed. Then again, after it reaches steady state, the speed will again become omega s, right? So this is what we mean by steady state stability. We mainly see the initial and the steady state. So in between, what is happening? We will, in today's lecture, we will not discuss. In between, what will happen? That will be discussed. Like this will also be discussed today only. But the analysis, the formulas, all those things, right, will be discussed in transient stability. We'll be discussing transient stability because here we are gradually changing the load. So there are two things. If I'm gradually changing the loads, there will be some variations. If I'm instantly making huge changes in the load, the behavior of the machine will be different. So both of them we will study one by one. So today mainly we will discuss in steady state stability, where there will be slight load increase, okay, small network variations and minor generator changes, right? Okay, minor changes we will discuss if that happens. So before that, we want to like get to a level, we want to understand few things. So one thing we know, we have this rotor mmf and stator mmf. I know the angle between rotor mmf and the stator mmf is delta. The angle between rotor mmf and stator mmf is delta. Okay, but we have to assume a reference. We have to assume a stationary reference. Let's say this is my reference, right? Stationary reference. This is my stationary reference. I know my rotor mmf will rotate with speed what, omega r. You will say in synchronous machines, sir, omega r is omega s. Yes, you are correct. In synchronous machines, omega r is omega s. But I told you, right, if there is some certain variations, the rotor speed is not same as the synchronous speed. It will vary slightly for a certain duration. For a certain duration, it will vary slightly. Okay, it will vary. That is the thing over here. I hope you have understood this point. Now that's why it is not always equals to omega s, right? So rotor mmf will rotate with a speed of omega r with respect to reference. With respect to reference, rotor mmf will rotate with the speed of omega r. Stator mmf is constant, it will never change, it will rotate with the speed of omega s, that is for certain. And the angle difference between rotor mmf and stator mmf is delta. Is it constant? Is this thing constant? Is delta constant? It is not constant, it is variable. Why is it variable? Why is it variable? Okay, you might have a question, sir, why is it variable? It is variable because the rotor speed changes, and whenever there is a variation in the rotor speed, the angle also will change. Okay, so what will be the angle between the rotor mmf and the stator mmf? That is delta. So delta is actually a function of time. Delta is actually a function of time with respect to what? Okay, so what is my delta equals to? That is what we want to understand over here. So if I assume a thing that, let's say at time t, right, at time t, my rotor mmf has rotated angle theta e, right, theta e. So theta is a function of time. How much has it moved actually? How much has it moved? So if I consider the stator mmf, I know the speed of the stator is fixed, and the angle between stator and rotor is delta of t. So if I can say how much this has moved, right? What is theta s? How much has theta s? How much is theta s in time t? How much is it? So theta s will be what? It will be the stator rotational speed, that is omega s, into t, whatever is the time duration. So omega s into t, that is what my theta s is. So theta e actually is what? It is the sum of two angles, theta s and delta, right? So it is delta of t plus theta s of t. So from here, if I differentiate on both sides, this will be utilized later on. D theta of t upon dt, this comes out to be d delta of t upon dt. plus what is theta is? Theta is omega s into t. Omega s is constant. It is a function of time, right? So if I differentiate with respect to time, it will be simply omega s. Okay, it will be simply omega s. So what is this d theta of t upon dt? What is this? What is d theta of s upon dt? If I differentiate this with respect to time, d theta of s upon dt, that is what? That is the speed of the stator mmf. Speed of okay, it is the speed of stator mmf. So it is the speed of the stator mmf. So if I differentiate this angle theta e or theta r, what is it? It is the speed of the rotor mmf. Speed of right. So if I rewrite this, so I can rewrite my equation that my omega r theta d theta e upon dt is omega r, and if I take this omega s on the left hand side, omega r minus omega s is d delta of t upon dt. Now does it make sense intuitively? This is a very important equation that will be utilized later on. Very important equation. Is it like, does it make sense? So it tells me that the speed of the stator mmf and the variation, the relative speed between the rotor mmf and the stator mmf, if there is a variation, then the delta, it tells me the change in the delta with respect to time. It does make sense, right? If the rotor speed changes, stator speed changes, something like this, right, then the delta will also vary. So the variation of delta actually is dependent on the relative speed between the rotor mmf and the stator mmf. Okay, so I hope that is clear. Now what is omega r, what is omega s? Remember, omega r and omega s, these are all speeds with respect to reference. These are all speeds with respect to reference. Okay, this is what my omega r and omega s is equals to. So I hope it is clear. I hope it is clear, right? Okay, so one more key point I want to say is that if I differentiate this again, that also will be utilized. If I differentiate this equation again with respect to time, if I differentiate this equation again, this will be d square e of t upon dt square will be equals to, because this is a constant, I already told you that the stator mmf will rotate with a constant speed, so this will be constant, right? There will not be any problem. Okay, so this will be d square delta t by dt. This also will be utilized later on. Plus 0 is there, that is not any of use to me. Okay, so I hope, like, I will write down few definitions. What is theta e, theta m again, right? Because I have not wrote it down, right? So what is theta m? Theta m or theta e of t? It is the absolute angular displacement of rotor with respect to some stationary angle in mechanical radians. So I will write this definition: theta m or theta e of t, right? It is the absolute rotor mmf, and the rotor is same because they are rotating with the same speed. So absolute angular displacement, absolute angular absolute angular displacement of rotor with respect to some stationary axis, that is our reference, whatever reference we have chosen, that is our reference. Okay, in what? In mechanical, because this is a rotor angle, right? It is in mechanical. Mechanical radiance. Okay, because it is measured in, like, it is a rotor angle, right? It is a physical property, physical dimension. That's why it is measured in mechanical radians or mechanical degree also you can measure. Okay, that is what my theta m is equals to. Now let's come back to this equation. I told you, right, if I know that if there is some power variation, like this is my pm, this is my pe, I know that if suddenly my electrical power goes to 0, then the speed will increase rapidly, right? Because I'm giving some input to the generator and it is not producing any output. So whatever input I'm giving, all of it will be converted into the kinetic energy, stored kinetic energy, because then the rotor will rotate fast. Because I'm giving some input to the generator, right? Here is my generator, I'm giving it some input, I'm giving, let's say, some 10 kilowatt of power, and in the output it is not producing any, like, it is not, we are not taking any power. So where will that power go? That power cannot suddenly vanish, right? What will happen? That power will be stored as kinetic energy on rotor. Why? What is kinetic energy? I know, like, somewhere that power needs to get stored, right? So we know kinetic energy is half mv square or half I omega square. So half I omega square. So I know that, like, this is constant, inertia of the rotor will be constant. So we have to store the energy, right? Somewhere the energy needs to store. So automatically the generator will store it in the rotor. So omega will increase. Omega will increase. Hence the kinetic energy, like, we have to store more kinetic energy. Hence something has to increase. So omega will increase. Omega means omega r. So the rotor speed will increase. Okay. So of course this has been established in this equation as well. So if I want to further write this equation properly, we know this thing, that force is equals to mass into acceleration in linear motion. In rotational motion, I know torque is equals to inertia, that is J, into alpha, angular acceleration, right? So this was in linear motion, right? Linear motion. And this is in the angular domain, right? Rotational motion. So what is the net torque acting on the prime mover? So net torque acting on the prime mover, net torque acting on the prime mover. Okay. So net torque acting on the prime mover will be Tm. Like, first of all, Tm will come. Why first Tm minus Te will come? Why it is not Te minus Tm? Why it is not Te minus Tm? I've explained this multiple times before as well. Because I am giving the input, I am giving the mechanical input. That's why Tm is coming for a generator, right? So as, like, this opposition will come when you are doing something, right? Every action has an equal and opposite reaction. So if you are doing some action, then only some opposition will come. So this negative sign means it is opposing, but I have to do some action. So this Tm is the representation of that action. I am providing you some torque. So for generator, Tm is my action and T is my reaction. Okay, Tm is my action and T is my reaction. I hope it is clear to you, right? So that's why Tm minus Te, net torque, will be equals to the moment of inertia, that is J, into the alpha, that is angular acceleration, And what is A? If you remember, what was A equals to? Linear motion. It was d square x upon dt square, right? Similarly here also it will be equals to d square. This time it is a rotor angle. Previously actually I forgot to explain this, right, in the machines discussion. There I did not explain, like it is actually the rotor angle, not the delta angle. So which will come out to be same as the delta angle only, but there I did not derive it, right? So it is actually equals to theta m, the rotor angle, or theta e, whatever you want to say, upon dt whole square. Like it is just analogous to the linear motion. Now one more thing, if you remember, our acceleration also I can write in terms of velocity. It will be change in velocity upon time, right, with respect to time, dv upon dt. So same I can do in rotational motion. What is velocity? It is angular velocity, right? So it will be d omega, remember it will be m or e upon dt. Okay, so this is called as the swing equation. Okay, and this is the rotor dynamic equation. This is called as the rotor dynamic equation. That is a very, very important equation. Called as the rotor dynamic equation. Okay, so here my J is the moment of inertia, moment of inertia. Okay, so remember this Tm is actually not the Tm that I am providing. This Tm has two components. This Tm actually, which I will not discuss after this, right? Only this, at this moment of time I will discuss. After this we will not discuss. So Tm actually, I am providing some shaft. I'm rotating the torque. I'm providing the torque in the shaft, right? But of course there is some friction and windage loss. If I'm providing some torque, there is some friction and windage loss. So the generator is not receiving the shaft torque. Generator is receiving shaft torque minus the friction and windage torque. This I will not discuss again, right? After this I will not discuss. So this is what I am providing. And this is what I am receiving. Okay, so I hope it is clear. What actually is Tm? What is the meaning of Tm? You should not get confused by Tm. Tm is what the generator is receiving, right, after subtracting the friction and windage loss. I hope it is not difficult for you to understand, because this have been very well explained in the machines subject, right? So now this is the equation. This is the dynamic equation. Can I rewrite this equation in terms of power? Because ultimately I am providing electrical power, right, and I am giving some mechanical input power. So I want to write this equation in terms of power. How can I write this equation in terms of power? That is what I want to know. So in your linear motions, we know what is my power is equals to force dot v. In linear motion, power is equals to force into velocity. Why? What is power? Power is d w upon dt. That is my work done, right? It is not omega. It is work done. Okay, omega. It is not omega, w, dw upon dt. So what is dw upon dt? So we know what is dw. Dw is simply f dot ds, right, divided by dt. So what is f? F is f, okay, force, and ds by dt is velocity. So that's how my power became force into velocity in linear motion. What is power in rectilinear motion? In rotational motion. So power in rotational motion is basically equals to the force, that is torque. Like in rotational motion, what is force? It is torque, right? What is velocity? It is omega. So power is equals to torque into omega, right? So what is torque equals to? Torque is equals to power by omega. So I will replace here, right? I will replace my Tm with what kind of power? Pm by omega r, and I will replace my Te with Pm by omega r, right? So this equation will be replaced with Pm by omega m. Also you can write basically the rotor movement, omega r, omega m, whatever you want to write, you can write, right? Minus P by omega r, okay, equals to what? Equals to this value, or this value also you can write, whatever you want to write, d square, sorry, okay, sorry, I forgot to write here j also should be there, right? Sorry, j also should be here, j should be there. J should be there, okay. So this will be equals to j into d square theta m into dt, okay, d square theta m into dt. Now I will just simply multiply by omega r on both sides. I will multiply by omega r on both sides. So what I will get? So this will become Pm minus Pe will be equals to omega r into j d square. Now what is if I want to write this in electrical, because I want to mention everything in electrical quantities, I don't want to write in mechanical quantities, I want to write in everything in electrical quantities, right? So all of these are in mechanical quantities, okay, because your theta m is in mechanical radian, okay, your omega r is in mechanical rotational speed, right? Rotor speed is mechanical, rotor speed is mechanical, okay. So I want to convert everything into electrical domain, right? All of this is mechanical, all of this is mechanical, right? I can write here omega r, omega m, you can write omega r, omega n, does not matter, all of this is mechanical, physical speed. But I want to write this whole thing in electrical domain. Why? Because I want to write in phasor format, I want to write in terms of rotor mmf and the stator mmf, and here everything is in electrical quantity, right? So we have to convert this. How will I convert this? We know that our theta electrical is equals to P by 2 of theta mechanical. So from here I can directly say what is my theta mechanical equals to theta mechanical is equals to 2 by P of theta electrical. If I differentiate on both sides with respect to time, it will be d theta m upon dt will be equals to 2 by P of d theta e upon dt. Remember, like whatever these variables these were, these are all electrical quantities, okay, electrical quantities, okay. Okay, so one mistake I have made here, actually I wrote them same. Theta e is the electrical angle, right? So I made a mistake. Theta e is the absolute angular displacement of the rotor with respect to a stationary axis, but it is not in mechanical, sorry, that was my bad, it is not in mechanical, it is in electrical radian, okay, and theta m is the same, definition is same, but it is in mechanical. Mechanical degrees or mechanical. So of course, like our phasor and all those things are in mechanical, okay, all these things are in mechanical. So if I have written somewhere theta m, sorry about that, okay, everything will be in mechanical only, everything will be in electrical only, everything will be in electrical only, because in phasor it is electrical domain analysis, right? So everything will be in electrical radiance here. Rotor is a physical thing, Rotor is a physical thing, that will be mechanical. Rotor is physical, mechanical. MMF, electrical quantities, electrical. Okay, so mechanical degree or mechanical radian. Okay, so actually this is pretty important, otherwise you will get confused. Okay, so yeah, so we want to convert everything into electrical, right? All these are in mechanical. We want to convert everything in electrical, right? Because we want to get in this domain d omega upon dt, everything in electrical quantities, because power, all these are electrical quantities, right? Okay, so I'm just checking whether I have written anywhere else any mechanical, otherwise you'll get confused. You'll just आ जाओगे comment section में, ठीक है? तो okay, yeah. So now I will convert everything in electrical domain. So this is mechanical rotor speed, this is mechanical radius. So whenever rotor is involved, actual rotor also always will be with mechanical quantities, mechanical angles. If rotor MMF is involved, that will be what? That will be electrical quantities. Okay, so here that's why we want to convert. So this equation will convert, right? So this is already halfway we have converted, so rest also will convert. So your PM minus PE, let me keep it with the box. PM minus PE will be equals to what? PM minus PE will be equals to M. So not M, sorry, I will convert these things. So omega R will be what? Omega R. So this is what? Theta M. D theta M upon dt is what? It is simply the rotor speed, right? Rotor speed. And this is the rotor speed in electrical domain. In electrical, with respect to electrical angle. So it will be 2 by P, and this is what? This is omega E, rotor speed in electrical radian per second. Rotor speed in electrical radian per second. So omega R is rotor speed in mechanical radian per second, and omega E is rotor speed in electrical radian per second. Okay, so this will be 2 by P into omega E into what will be your theta m. So theta m will be converted into P by, theta m, yeah, will be converted into 2 by P theta E. Now 2 by P is just a constant. If I differentiate on both sides with respect to time, 2 by P will be outside. If I double differentiate, 2 by P will be outside, right? So I hope I'm not making anyone mad if I write this value 2 by P into d squared theta m theta E upon dt square, right? Sorry, here there will be a square. I hope you guys are not getting mad at me, right? 2 by P is just a constant. So if I differentiate if I differentiate this equation twice on both sides, 2 by p will just be outside, right? 2 by p will just be outside. Okay, so what ultimately what is happening, also there is moment of inertia, don't forget there is j. Okay, don't forget the j will be there. So ultimately the equation that I am getting is Pm minus Pe will be equals to j into omega e into 2 by p whole square into d square theta e upon dt. So this equation is actually called as the swing equation of generator. Why swing equation? Because it tells me how the variation of theta e happens, right? So theta e I can write what? Theta e I can write as d delta, because d square theta e upon dt I have derived it as d square delta upon dt. So it shows us the variation of the rotor angle and the stator, variation of the stator and the rotor mmf, their angular variation, okay, with respect to some disturbance. That's why it is called as the swing equation, and specifically this is the swing equation of generator. Now we have another term which of course every time I will not write this, right? This is not suitable for me. So we have another term for this, that is called as m. So we totally write this whole thing as a single term, that is m. M is what? M is known as the inertia constant or angular momentum. J into omega is called as the angular momentum, right? So that's why it is called as the inertia constant. So just like it is mass into velocity is called linear momentum, mass into velocity is linear momentum. Similarly, angular momentum will be mass in angular domain, that is j, and omega in angular, and velocity in angular domain, that is omega. So j into omega or m into 2 by p whole square, this whole thing is called as angular momentum, and in everywhere else in power system you will be given this value. So this is called as the inertia constant. Sometimes it is called as the inertial constant, or sometimes it is called as the angular moment, like it is also called as the angular momentum. Both things work. Okay, both things will work. Either you say it as uh, inertia constant or angular momentum. Also this value, sometimes we write this value, sometimes we call it as synchronizing power, also sometimes we call it as accelerating power. So PA or PS, right? So PA is what? PA actually is called as the accelerating power. Why? Because it tells me how fast the rotor will accelerate. If there is huge difference, the rotor will accelerate. If there is no difference, rotor will just remain stable in it. It will not change its speed, right? So PA is known as the accelerating power. Okay, PA is known as the accelerating power. I hope you have understood this point. Like we defined this as synchronizing power in the machines lecture. If you remember, right, it was defined as the synchronizing power in the machines lecture. Okay, so if I rewrite this equation, right, this equation can be rewritten in multiple ways, right? I can rewrite this as d delta square upon dt, or this can be rewritten as d, like all these values will be there, so I will rewrite here only. So Pm minus Pe will be equals to m into d square delta upon dt square, also equals to m into d omega e upon dt, or equals to m into alpha. Anything will work. Okay, now remember one more thing, if unless and until specified, your units always will be in electrical quantities. So unless and until specified, you will assume units to be in electrical domain if it is related to electrical quantities. If it is related to electrical quantities, it will always be like by default you will assume it to be electrical, like electrical radian per second. It will not be mentioned. If it is mechanical, it will be mentioned mechanical radian per second. But unless and until it is specified, if it's a electrical quantity, it will be in electrical domain only. Electrical, the units will be in electrical domain only. Okay, I hope this thing is clear. Okay, so this whole thing is called as the swing equation. This will be my swing equation. Swing equation for generator. Similarly for motor, I can copy. For motor, what will be the swing equation? Just the opposite. It will be PE minus PM. Why? Because we are giving electrical power as input, right? First I am giving the electrical power as input, then the load is providing some load torque, that is mechanical load torque, that is opposing. So it will just be swapped. PE and PM will be swapped. So it is not swing, actually swing equation. I did not write it completely. Swing equation for generator. Swing equation for generator, and this will be swing equation for motor. Okay, so I hope it is clear now about generator and motor. Everything is clear now, right? Generally mostly we will be using the generator only. We will not be using motor, of course. Mostly we will be using generator, like the swing equation for generator. So what is the like unit of M? Unit of M. Unit of M. Right? Because in most of the questions either M will be given or H. H also we'll discuss later on. But what is the unit of M? That is what we want to discuss, right? So unit of M. So what is my M equals to? M is equals to, basically it is equals to this accelerating power upon d square delta upon dt whole square, right? Or I can write accelerating power upon d omega upon dt. This also I can write, right? Whichever one is suitable to you, both of them you can write. So it is accelerating power upon d square delta. Delta, remember, is electrical, right? It is electrical quantity upon dt whole square. Okay, so that is what my M is equals to, right? That is what my M is equals to. So I can say M is equals to, like, what is power? What is power? Like generally power, right? In power systems it will be in mega only. It will not be in kilo because it is a power system, so we are generating huge power. So it will be in mega, not in kilo, not in simple watts, it will be megawatts. Okay, and this, the numerator is, I am differentiating this delta twice with respect to time. So what is this? Delta is electrical radians, right? Delta, unit of delta is electrical radians. So this will be electrical radian, and this is time square. So this is simply second whole square. Now simply I can multiply the second whole square on the top. So this will come out to be megawatt second square divided by electrical per radian. Megawatt second square divided by electrical radian, right? So what is megawatt into second? So what is power? Power, I told you already, it is energy by time, right? It is a change of energy upon time. That is what my power is equals to. Okay, so what is energy? Or what, like, it is simply dw upon dt, right? So what is the unit of power or unit of watt? So watt is actually joule per second, right? Or I can say joule is equals to watt into second. So I can take one of the watt second and I can combine it to be joule, and it will be useful actually later on. It will be useful to us. Okay, so I can combine this megawatt per second to megajoule. So 1 watt second will be converted into joule. So this will be megajoule second per electrical radian. So that is the unit of your m, inertial constant. Okay, do you need to remember it? No, but it's good to know how to derive, because this will be helpful later on. Okay, we will derive few more constants that will be utilized. Okay, so let me analyze this accelerating power further for a generator, right? So this is the accelerating power further for a generator. Okay, so if suddenly there is some fault happening, right? So if there is some fault happening, what will happen? If suddenly there is some fault happening, your accelerating power initially, when it was in steady state, if it was in steady state, I know my rotor speed will be what? It will be equals to my stator mmf speed, that is ns, synchronous speed, right? Rotor speed will be stator speed, that is synchronous speed. Okay, now what does it mean? That means your d omega e, or this is also called as e only, d omega e upon dt is 0. Is it the case here? So if d omega upon dt is 0, that means pm minus pe will be 0. That means pm will be equals to pe. Isn't that what we know? In steady state, the whatever the mechanical power I am giving and the electrical power it is generating, both are equal to each other, right? Initially, this was the initial case. Right? This was the initial case, right? So if this is the initial case, now what is happening in the when there is some change, when there is some variation in load. If there is some variation in load, what will happen? Okay, that is what we want to understand. So let's take for first case, that in the case 1, suddenly there is some fault, so my PE goes to 0. If PE goes to 0, what will happen? If PE suddenly goes to 0, then your PM minus PE is equals to PM only, right? Because your accelerating power will be equals to PM minus PE, that is equals to PM only. Okay, that is equals to PM only, right? Which is positive. So this is positive, which is equals to what? M into d omega t upon dt. M into d omega t upon dt. So what is happening? So you're basically, what can I conclude? Your d omega t upon dt is greater than 0. So your d omega t upon dt is greater than 0. That basically means your omega e will increase. If omega e increases, what will happen? One more thing is there, that if you observe here, right? If you observe one more thing, the rotor actually leads the stator MMF. Is this intentional? Yes. Again, this is intentional. Rotor MMF leads the stator EMF by delta. Why? Why does it lead the stator EMF by delta? Why? Because first I am applying the torque to rotor, right? I am applying the torque to rotor, not to the stator, right? I am applying the torque to the rotor. That's why the rotor EMF will lead the stator EMF, because stator will come later, right? First I will apply torque to the rotor, then the EMF will be induced in the stator, right? So that's why rotor will lead, rotor MMF will lead, because the torque is applied to stator first. Sorry, to the rotor first, right? So that's why the rotor MMF will lead the stator MMF. Okay, rotor MMF will lead the stator MMF. I hope it is clear now, right? Rotor MMF will lead the stator MMF. Okay, so if the rotor speed increases, what will happen? This delta value will increase, right? This delta value will increase, right? Will it only increase? Will it only increase? No, it will not just only increase. Why? Because it will, if it is increasing, the rotor will somehow come here again, right? It will come here again. So for a certain split second, delta value will increase, then again it will come here. It can reduce as well. So we'll see the variation. Basically, I'm just telling you what will happen. We have the graph, so we will see from the graph itself what happens. I'm just giving you a overview how to do the analysis, right? So this is one of the equations that we will use to do the analysis. Where did it go? So this is one of the equations that we will use to do the analysis. Another equation we have, right? One more equation we derived. What was the other equation? Yeah, this was the equation. So these two equations mainly we will use, this equation and this equation. Okay, so here we see omega r is increasing, that is omega e is increasing, right? Basically omega e is increasing. Okay, so if omega e is increasing, that means your d delta upon dt is previously, initially what was happening, omega e was equals to omega s. So your d delta of dt was initially constant, some delta naught, it was not changing. Okay, as this omega e is increasing, so this is becoming positive, so delta also will increase, Now it will not always be the case that delta only increases and it becomes more positive. No, what if initially your delta, like if delta is positive, if delta was initially positive, right? So your delta will become more positive, right? If this was the case, if let's say delta was initially negative, let me take a number. So let's say if delta was initially 2 radian, as d delta upon dt is positive, so it is increasing, right? It is increasing, so it became now 3 radian, right? 3 radian per second. Now if your delta naught, let's say if your delta naught is equals to negative. Initially, let's say for some reason my rotor mmf was lagging, right? For some reason, okay, some disturbance. Then what will happen? Then I will change the color. Then your delta naught will it like become more negative? No. It also increases the value will increase, but it will be -1. So it has increased, but it has become less negative, right? So it is very important to understand. So here what happens, delta naught has, overall magnitude of delta has increased, right? In the first case, in the case 1, right? So the angular difference displacement will be more, right? And in the case 2, if you see, the angular displacement has reduced actually. So it's not always the case that the angular displacement will increase, right? So what do I mean? I will show you with example as well. So in the case 1, right, if initially rotor was here, right, and my stator was here, and initially the angle, this is my stator mmf and this is my rotor mmf. Initially my angle was delta naught, which is 1 degree basically, because +1, because rotor is leading, okay. And then I told you that rotor speed is increasing, both are rotating in the same direction only, right? Both are rotating in the same direction only, okay. So rotor speed is increasing. If rotor speed is increasing, then it became 2 degrees, right? This angular difference became more high. This became 2 degrees because rotor rotated at a higher speed. So it is not 1 degree anymore, it is 2 degree. But will the angular difference always increase? No. The delta angle can reduce as well. How? So let's check for the case 2. In the case 2, I will have rotor mmf lagging. So this time the rotor mmf will lag the stator mmf, okay. Right, so this will be what, this will be still 1 degree, but rotor mmf is lacking, right? So rotor speed will still increase. So this is the stator speed, which is constant, this is the rotor speed. In both cases rotor speed will increase. This is the rotor speed, this is the stator speed. So rotor, as the rotor speed increased, so what happened, it went, the angular difference increased because this is slower, so the difference increase. But rotor speed will increase, right? Rotor speed will increase, but as it is increasing, this is slower, so it will catch up. So the angle will reduce now. So previously it was 2 degrees, I guess, in the previous case when it was lagging. -2 means lagging, right? Now what will happen? Now it will become 1 degree because it is catching up. Rotor is speeding up, so it is catching. Previously it was lagging, now it is catching up, right? So this will become 1 degree. Okay. So that is the important point that you should keep in mind. So it's not like this is positive, so delta also will keep on increasing. No, you cannot comment about the double derivative. What you can comment? You can comment about the rotor speed. Rotor speed will definitely increase. So what can I comment? If, so the conclusion is if PA is positive, that is the accelerating power is positive, rotor speed will definitely increase. Definitely increase. Okay, but what about delta of t? Would delta increase or decrease? Can't comment. Okay, need to do analysis, need to analyze further. Okay, same thing. If that's so, this is not just P. I will. This is the accelerating power, right? This is the accelerating so if the accelerating power is negative, if the accelerating power is negative, then rotor speed will definitely decrease. But again, for delta, I cannot comment. Need to do further analysis. Okay, so we have to check this. Okay, so now we will do the steady state analysis, like before 90 degree and after 90 degree. Why? I hope you remember, right? Why 90 degree is the like critical angle after which the system goes to instability. This we have discussed in the like the synchronous machine chapter. Okay, so now we will do the steady state analysis before delta equals to 90 degree. So we are doing the steady state analysis. So we know at steady state the electrical power output of the generator and the mechanical input of the generator will be same. Okay, that is what we know. So we have this generator where we are providing some mechanical power as input, and this generator is able to provide electrical power as output, right? So the power graph is something like this. This follows what I hope you remember the graph. I hope you remember the formula for PE, the electrical power generated. It is equals to EF sine delta or EV by XS sine delta, right? So variation of power with respect to delta, that is what we are trying to understand. So which will be equals to P max sin delta, which will be equals to P max sin delta, right? So let's assume that initially we are taking the case where I am gradually increasing the load. Gradually I have increased the mechanical input load from PM0 to PM1. So we are taking the case when I gradually increased the mechanical input PM0 to PM1. Okay, so if I have gradually increased the load from PM0 to PM1, what will be the initial angle delta naught, right? And what will happen after I increase the mechanical input? If I suddenly increase the mechanical input, what is the swing equation? Swing equation is PM minus PE equals to M d square delta upon dt square. Now if I suddenly gradually increase my PM, I'm increasing my PM, my PE will not increase instantaneously. PE will still be almost constant for a few initial cycles, right? Where will that, so PA is greater than 0, right? That means your d square omega upon dt is positive, or I can say your d omega E upon dt is positive. That means your omega E is increasing. That means what? Whatever extra power, additional power, energy I was giving, that energy is getting stored as kinetic energy in the rotor. Then it will get converted into electrical energy, right? That will take some time. Okay. So basically what is happening? is if mechanical input is increased, electrical power output will not increase instantaneously. It will take some time, right? It will take some time for the electrical power output to increase. So during that time, during that time additional energy is stored as kinetic energy in rotor. Right, that is the thing. It will be stored as additional energy in the rotor side. Okay, in the rotor side it will be stored as additional energy, right? Why? Because your omega r is simply increasing, right? We derive from the swing equation. Okay, so there will be two kinds of motion. So when omega r is increasing or omega e is increasing, that is called as the forward motion, right? So my stable point will be this B, where again my electrical power will be equals to the mechanical power. Initial stable point was this. So can you find out what is the initial value of P E naught? What is the initial value? Sorry, what is the initial value of delta naught? What is the initial angle? And what is the steady state angle? Let's name this as delta 1. So delta naught will be very, like, I know if I use this formula, right? This simple formula. PE0 will be equals to P max sine delta naught. So PE0 P max sine delta naught, and my I know, so from here I can easily find out what is my delta naught, right? Delta naught equals to sine inverse P naught divided by P max. Okay, so that is what my delta naught is equal to. Delta naught is equal to sine inverse P naught by P max. Okay, this is the initial delta naught angle. What is the final angle delta 1? If someone says, ask you what is the delta 1 angle, delta 1 angle, same formula you will apply. It will be sine inverse PE1 by P max. Okay, so we will see in between what is happening. We will not do the exact analysis. Exact analysis, transient analysis we will do in the like 2 lectures after this lecture and another lecture. But today we will see like basically what is happening. So first of all we will discuss about the forward motion. In forward motion what is happening? So in forward motion, what have I told you? My omega r is increasing, right? So initially let's assume that delta is positive. If delta is positive, right? So what will happen? That means my rotor mmf is leading the stator mmf. So omega r increasing means delta further increases, right? So delta will keep on increasing, right? Similar analysis we have done in synchronous machines as well, right? So delta will keep on increasing and increasing. So that is the forward motion because the rotor is rotating more fast. So delta will keep on increasing. Now will I stop here at B point, because at B point I have told you that PE1 is equals to PM1, right? Should I stop here? No. Why shouldn't I stop? Tell me in the comments below why shouldn't I stop, right? Pause the video, because this same analysis we have done in what, in the synchronous motor as well. So for steady state, PE is equals to PM. This is one condition. Also another hidden condition is there. Your omega R or omega E is equals to omega S. Then only it will be steady state. Otherwise it will not be in steady state. Right? So what is happening here? In this whole forward motion, what is happening? Your omega R is increasing. So omega R is greater than omega S. It is still increasing. Right? So your omega R is greater than omega S. So your rotor is greater than omega S, right? So what can I say? So omega R minus omega S is equals to d delta upon dt. So omega R is greater than omega S. D delta upon dt is still positive. D delta upon dt is still positive. That means what? Delta will increase. Delta will still increase. So it will still go on and on and on until this point. Now you might have a doubt, sir, why shall it stop here? Why shall it stop here? So let's assume that this was the 1600 rpm speed, right? Or 1500 rpm, whatever like is the ns, right? And here as the speed increase, because omega R is increasing, here the speed increase, let's say by 1000 rpm. So here the speed got to 2500 rpm, right? But still ns is what, 1500 rpm. This is my ns, right? So here the rotor speed is not equals to ns, so of course it will not be stable. And of course I have told you, right, if the rotor speed is higher than the stator speed, delta will still increase, right? So it will go on till this point. Let's say it is some point C, and that will be the maximum value. Let's say here still as delta. Okay, here what is happening? Can you tell me here what is happening? One thing to notice here. What is the swing equation now? So in this whole region, from A to B, there were two things, right? My PA was positive, so of course I know my omega R will increase for certain. So and my omega R is always greater than omega S, so that is also certain my delta will increase. Right? Now from B to C, what is happening? From B to C, if you notice, right, your PA is not positive anymore, because this is your PM1, right? And your electrical power developed has become higher. So your PA is negative, right? If PA is negative, what will happen? For certain I can say d omega upon dt is negative. That means omega R is reducing. Now will omega R be greater than omega S? Yes, because I told you at this point what was the speed? 2500. So it will not suddenly go to 1500, right? It will decrease, but not instantaneously to 1500. It will decrease to, let's say here, right? Let's say here the speed reduces to some 2200 rpm. Here it reduces to some 1800 rpm. Finally at point C we come, and here the speed becomes 1500 rpm. So again, so here what is the conclusion? Conclusion is your omega R will still be greater than omega S. That will still be certain. The rotor speed will still be greater than the stator speed. Okay, so your delta will still increase, right? That's why we are observing delta is still increasing. Right? Now the thing is, the thing is omega r is greater than omega s, right? So what can I say? What can I say? I can say that uh, at this point omega s is equals to omega r. So after this point what will happen? After this point you tell me what will happen. After this point there will be backward motion. After this point there will be backward motion. Why? Because what is the accelerating power here? Negative. So your omega r will reduce. Omega r will reduce. So here delta was increasing. Now omega r is reducing. So your omega r, your delta was increasing, right? This is your omega r. This is your omega s. So as omega r was increasing, so delta was increasing, right? But now I'm telling you omega r is equals to omega s. At point C, omega r is equals to omega s. Okay? At point C, omega r is equals to omega s. So after this, what will happen? After this point, your accelerating power is negative. So it will now go back. There will be backward motion. Okay? So that is what I have written here. Backward or reverse motion. What do I mean? So I will just delete this. So backward or reverse motion will happen from point C to B, right? That is the backward or reverse motion. Why? Why is it called as the backward or reverse motion? Point C to B. Because here, if I observe, here the accelerating power is negative because your PE, power developed, is higher than the mechanical power. So what is happening? Here what is happening? Actually, what does PA negative means? Basically, here your kinetic energy, rotor speed was increasing, so kinetic energy of the rotor was increasing, and here rotor's speed is reducing. That means your kinetic energy of the rotor is reducing. Okay, so whatever that additional power that was stored, right, whatever additional power was stored, now the load is taking, right, P. So that's why kinetic energy is reducing, right? So here from C to B, if you notice here one thing, that your accelerating power is negative because PE, I'm higher than my PM, right? So PE is higher, so your accelerating power is negative. For certain I can say your omega r will reduce. So if your omega r reduces, what will happen? If your omega r reduces, I know at this particular point, at point C, my omega r was actually equals to omega s. At point C, my omega r was equals to omega s, right? So omega r was equals to omega s. So what I can say is my omega r minus omega s will be what? It is equals to d delta upon dt, which is negative because omega r is reducing, right? And omega r is equals to omega s at point C. So if omega r is reducing, that means this is reducing. That means your d delta upon dt is negative. That means your delta is reducing. That's why it is moving backwards. That's why we call it as reverse motion. I hope it is clear. That's why we call it as reverse motion, right? Now again, will I stop at this point? So here I told you, right? Here the speed was 1500 rpm. But speed is reducing here, right? So here the speed will be something like 1200 rpm. Here the speed will be 1000 rpm. So again, at this point, nr is not equals to ns, right? Nr is not equals to ns. So if nr is not equals to ns, and again that is not a point of stability, again it will keep on moving from B to A. So from B to A, what will happen again? If I move from B to A, what is happening? If I move from B to A, right, I notice my accelerating power this time will become positive, right? Because your PM is here and your electrical power graph is below this. So your accelerating power will become positive. So your omega r will again start increasing. Omega r will again start increasing. But what will happen to delta? Remember, here the speed is still 1000 rpm, right? It is still less than omega s. So still it will stop at A. At point A again the speed will become not exactly at A, somewhere between A and stuff. it will exactly become again 1500 rpm, right? So that's why it will stop basically, because your d delta upon dt will be 0, because omega r and omega s are equal, right? But still from b to a, the speed will be basically omega r minus omega s is still negative, even if omega r is increasing, but I know omega r is 1000, it will increase to 1500, but at point a, right? So again your d delta upon dt will be negative, that means your delta will reduce. Your delta will reduce. Okay, so like this is what we have analyzed in hunting as well. Same thing I'm analyzing here again, just to clear this thing. So what will happen, it will just oscillate, right? There will be some damping, we will get some damping, and ultimately it will settle to point b, it will settle to point b. Okay, so that is what will happen. So ultimately what will happen, for few cycles it will oscillate, then settle at point b. Okay, there will be some like damper windings connected, and ultimately it will settle at point b. Okay, so now what if the initial point, right, is not here, it is after delta equals to 90? What will happen here? So same kind of analysis if I do here, right? If I do here, that let's say I have increased my mechanical power, right, to PM1, correct? If I have increased my mechanical power to PM1, so this is my point B, right? And this is the point of stability, right? B is the steady state point, steady state point. What is happening? So my A is here, right? And I have suddenly increased my mechanical power input, right? And this is the steady state point where it cuts the graph of PE, right? So this is my point B. Okay, so what can I say over here? What can I say over here? That if I'm at point A, right? Currently I'm at point A, initial point, this is my delta naught. So what is the accelerating power here? Can you tell me what is the accelerating power? The accelerating power, if I notice, is negative, because sorry, it is positive, right? Because PM1 is here, accelerating power is what? Accelerating power is mechanical power have changed instantaneously, but electrical power output is still the previous value P naught. So it is positive. If it is positive, what does it mean? If it is positive, that means your omega r will increase. If omega r increases, what does it mean? So omega r minus omega. So at the steady state point, what was the speed? The speed was, let's say, 1500 rpm. Right? Both of them were rotating at 1500 rpm, and my rotor is leading. Right? This is my omega r. Rotor is leading the omega s. Right? So omega r minus omega s is equals to d delta upon dt. Okay, omega r upon omega s is d delta upon dt, right? So your delta will increase. So I'm observing it is actually going in the opposite direction of the stable point. So it will not stable, it will not stable at all. It will keep on increasing, it will keep on increasing, and it will go here, where the power developed will be 0. So PE will keep on increasing. PE, electrical power developed, sorry, electrical power developed is reducing here, right? Delta is increasing. Electrical power developed is reducing actually, but actually electrical power developed has to increase, right? It had to match the mechanical power, but it kept on reducing. So PE, electrical power developed is reducing. Now if it is reducing, it will keep on will keep reducing, hence more unstable. It is moving away from stable point, from steady state point, hence it is moving towards instability. Okay, it is moving towards instability, so the system will be unstable. So if we operate after delta equal to 90 and if there is small disturbance, the system will never become stable. Right? So the initial point is very important. What is your initial point? If I'm lying before delta equals to 90, system, we can bring the system back to stability, but if I'm lying here, I can never bring the system back to stability. Okay, this we learned with synchronizing power concept in the synchronous machines, right? Same thing I will explain with a different concept. So conclusion, what is the conclusion? Conclusion is, if the initial operating point, if the initial operating point is delta less than 0, delta less than 90 degree, then system is stable. So if delta less than 90, right, so for small disturbance system will remain stable at new steady state point. Okay, now if the initial operating point is greater than 90, right, if the initial operating point is greater than 90, what will happen then? If it is greater than 90, then for small disturbance the system will go out of stability, system will not remain stable. System will not remain stable. So that is a very, very important point for you to understand over here. Okay, how we have understood this point? Like, that's why we tell that after 90 it will not remain stable. So just to like understand whether you have understood the concept or not, just I have taken a question, like very basic question. For a generator operating in the following conditions, if the mechanical input is suddenly increased, the motor will move towards what, right? Let me change the question, right? If it is, let's say, suddenly decreased, if let's say the mechanical input is suddenly decreased, what will happen in both the cases, in both the circuits? So I will take here, and this was my initial PM naught, right? Then I changed my mechanical input and I reduced it. Right? So this is my PM1, and here also the same thing, right? PM1. So in this case, what I observe, if the mechanical input is reduced, right, and electrical power is still here, right? This is still my P naught, right? This point is still my P naught. So what happens? Your accelerating power is actually negative. If your accelerating power is negative, what does it mean? It basically means your omega r will reduce. If your omega r reduces, what will happen? We know here at this particular position, omega r was equals to omega s. It was a steady state point, right? So omega r minus omega s equals to d delta upon dt, right? And at this particular point A, both were equal, right? There was no change, but omega r is reducing. So this is negative. This is negative. So your delta will be negative, right? So delta is negative, it will move towards point C. For this case, it will move towards point C. Okay, but what is the stable point? Stable point is here. So again, I'm moving towards instability. I'm moving in the opposite direction. Like someone tells you that you have to go in gate 1, right? And you're going in the opposite direction of gate 1, right? So you're not listening to that person. So I'm telling to reduce the load, but it is not listening. It is going in the opposite direction. But here this is stable, right? This was after 90. Here if you see, if I suddenly reduce the PM1, what will happen? So here in this case, so this was the case circuit A. In the circuit B, what is happening? In the circuit B, my PA, right, is positive actually. If I reduce my, sorry, not it is, here also it is negative only, accelerating power is negative only, because initial P naught is here. It is my initial P naught. So P naught is higher than PM1. So accelerating power is negative. Same condition will follow. Omega R will reduce, right? And delta will reduce. Yes, everything will be same only, right? But this time my operating region is here. So I'm reducing my delta naught. So I'm going in the left hand side, that is in the bottom towards the stable point, right? So that's why this will be stable. So in for this the answer will be, for this the answer will be, for the circuit A the answer will be towards C point, towards C, right? For this the answer will be towards C, and for this the answer will be towards C. For both the answer will be towards C only, but one will be stable, another one will be unstable. Okay, both are towards C only. So I hope you have understood this basic point. So these are few conclusions basically. So whenever, like, what is the stable point? What is the like critical angle? Critical angle is 90. Maximum power transfer occurs here as well. P is equals to P max, when P max sin delta is 90. That is the maximum point, and this is the point where the stability changes. After this, if my operating point shifts here, right, somewhere on the right hand side of 90, then automatically my system will become unstable. So this is the steady state limit. That's why it is called as the steady state limit. If at steady state my rotor angle, right, operating angle is beyond 90, my system can never become stable if some small disturbance is happening, right? So for a purely inductive load, your delta is 90, purely inductive load, and for a simple cylindrical rotor, cylindrical pole motor, it is 90, right? And we will assume everything to be cylindrical only, we will not assume salient pole. But I have already discussed, for a salient pole it will be somewhat less than 90, right? We have discussed this, it will be somewhat less than 90, because your power graph for the salient pole will be, it has this 2 sin omega component, so the graph will be somewhat like this if you remember for the salient pole. So all these have been discussed. So the operating point will be somewhere here. So basically the thing is, the crux is the rate of change of power with respect to d delta. If it is positive, then the system is said to be stable. stable. Then it is working in the stable operating region. If dPe upon d delta is less than 0, that means it is working in the unstable operating region. Okay. So I hope you have understood this point. Basically, these things are clear. So the steady state limit, steady state stability limit, the maximum electrical power that can be transferred without causing the system to lose stance, without the system to lose synchronism during small disturbances. That is the formal definition of steady state limit. Okay. For stable operation, my delta operating should always be less than the steady state limit angle, that is 90 degrees. In our case, it will be 90 degrees if the line is purely inductive. If the line is purely inductive, then the formula of power is this, right? Then the formula of power is PE is P max upon sin delta. Okay, then the value of delta for which the maximum power occurs, after that what happens? Your slope will always be negative, because the point at which maxima occurs, after this the slope will always be negative. Why? Because the value will always increase, always reduce, because this is the point of maxima, right? So that's why it will always reduce, and before this the value will always increase. That's why the slope is always positive. Okay, now in the next page I will show you a formula, and please don't get scared by the formula. That formula will be derived in transmission line. So it's my request, don't get scared by that formula. Just understand what I am telling there, what am I explaining. Okay. So if the line is not purely inductive, right? So if the line is not purely inductive, and if there is some power transfer, right? It is Z, it is not purely inductive. Then your formula will not be just EFVT angle sin delta. I think we have derived this in the synchronous generator as well. What is the power delivered, right? So there this cos angle, all this used to come, but this beta mod of B mod of A does, like, we have not seen it, right? So this AB, these are just ABCD parameters of the transmission line. Okay, we will discuss this in the transmission line chapter, that is PSA 1. Don't worry. Okay, just understand this. We have to identify the condition for which this will become maximum. Here your delta is varying, so what is the value of delta for which this will be maximum, right? What is the value of delta for which this will be maximum? When your delta is equals to beta, because when cos is 0 it is 1. So the condition for steady state stability limit, here it will not be 90 anymore, because the line is not purely inductive, line is some, like, it is complex, right? Line is complex, consists of real elements resistor. So delta will be equals to beta. It is almost similar to whatever we have derived in the expression for synchronous generator, power delivered by the synchronous generator. Here delta has to be equals to theta s. Basically delta has to be equals to beta, that is angle of this impedance. It is magnitude of Z into angle of this impedance, let's say beta. So delta has to be equal to this impedance angle, right? Whatever is the impedance angle, that is the condition after which that is a steady state limit after which the system will pull out of synchronism. So if delta is greater than beta, right, delta operating is greater than beta, it is basically the impedance angle, then system will be unstable, system will be unstable. And if delta operating is less than beta, system will be stable. Okay, so these are few conclusions that I wanted to take. So I will give you few homeworks. You try out these questions, and in the next lecture we will solve these questions, right? Whatever we have discussed. In the next lecture we'll solve these questions, and along with that we'll start with like a few more terms, right? Few more terms we'll discuss. So this one I hope you guys can easily find out. So you have to find out the delta for the steady state stability, for the maximum steady state stability limit, right? Delta for steady state stability limit. Okay, so what is the value of delta for steady state stability limit? It's pretty easy, right? Not that difficult. So you just have to find out the impedance angle. What is the impedance angle here? It is 45, right? So your beta angle here is 45, and don't worry, I will tell you how to find out the ABCD parameters as well, transmission line parameters, that will be discussed later on. So what is the beta angle here? Beta angle here is simply tan inverse 1 upon 1, that is 45 degrees, right? So what is the value of delta for which maximum power, like what is the limit of delta? Delta equals to 45 degree will be the steady state stability limit. This is the steady state stability limit, right? And what is the like this power is also called as the steady state stability power. Okay, maximum power transfer. Okay, this we will discuss in the next lecture. Basically, what is a maximum power transfer? Sometimes that is also called as the steady state stability, right? Either it will be asked in delta, right? What is the maximum value of delta, right? Or sometimes they call what is the Pmax. Pmax is also sometimes called as the steady state stability. Sometimes, right? Pmax is also called as the steady state stability. Either they will ask in angle or Pmax, steady state stability limit. Okay, they can ask in two things. So I want you to find out here in this question the Pmax. What can be the Pmax value? Just find that out in per unit. Okay, so yeah, I hope that's it for today's lecture, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the lecture 14, where we will be doing questions on like stability, steady state stability. Also, we will be understanding what is the inertia constant. I told you what is m, right? M. So it has another variation. M has another variation known as inertia constant. We'll understand the relation. Also, we will do many numericals. Okay, whatever theory, whatever we have learned, we will do numericals on that. So before starting, I gave you a few homeworks. This was the homework. So we will start with this question, right? So we have to find out the steady state stability for the circuit. Basically, actually, I told you, right? Either it means delta or Pmax. So here, I should have asked you the power. They are asking the Pmax. Here they are asking the Pmax. They are not asking the delta. They are asking the Pmax. Okay, both, it can mean both things. Here they are asking Pmax. Okay, so what is the power maximum transferred over here? So I observe that it is a inductive load, pure, like not inductive, sorry, it is a purely reactive load, right? There is no resistance present, there is no real part present, it is a purely reactive load. So if it's a purely reactive load, what will happen? If it's a purely reactive load, it basically means that I can use that formula. What is that formula? So Pmax formula will be equals to, if I have a purely reactive load connected, will be E V by X sine E V by X, right? That is my Pmax basically. Now the thing is, what is the X, right? X was just, if I have this simple connection, in this case the X was just a single element, but here X is not single element. So what is the power transferred? So this I have taught in synchronous machines as well, how to find out the power transfer. So what you will do, we just need to convert this into delta. Okay, we will convert this into delta, and don't worry, we will solve this using ABCD parameter as well in the last, in the end of steady state, in the end of stability, I will solve this using ABCD parameters. So not ABCD, Y parameters. Okay, so there is another method as well that I will discuss at the end of stability, not now. So we have to convert this into a single element, right? Single link. So it does not matter if I have here some capacitor here, some inductor here, it does not matter. Ultimately what matters is the potential here, angle between the potential and the inductive link, whatever inductive or capacitive link, right? That is what it matters, correct? That is what matters. So I have to convert this into this format. Like currently there is a link in between, right? I cannot directly find out the Pmax. I cannot directly find out the Pmax. Okay. So I have to break it. I have to break it basically. So if I break it, what will I get? So I have to convert this into, this is in what? This is in star. I have to convert this into delta. So star to delta. I have to do star to delta. Star to delta basically means summation, right? Star to delta basically means summation. So summation basically means it is what does summation means? So I will have my, here I will have reactance, whatever the value, here I will have reactance, and here I will have reactance, right? So I'm doing star to delta. So what will be the values here? So it is R1, like this Z1 plus Z2 plus Z1 Z2 divided by Z3, right? So Z1, so this impedance will be basically J plus J square divided by minus of J5. So this actually comes out to be, both are okay. This is -1 gets this will become plus, this will become minus 0.2. So this will be J 1.8. This will be what? This will be J1 plus minus J5. So J minus J5 plus J into minus J5 divided by the opposite impedance, that is J only. So J will get cancelled. This will be minus J5. Okay. So this will be actually, it does not matter whatever this value. I don't need to calculate these values. I don't need to calculate, right? This I can neglect. So ultimately I just need to understand what is this value. This value is J1.8. This value is J1.8. Here the voltage is 1 angle delta. Here the voltage is VT angle 0. Actually, okay, I forgot to mention, it should be 1 angle 0. Sorry. That's my bad, right? It should be 1 angle 0. It has to be 1 angle 0, right? Otherwise, how will you be able to solve it? No. It has to be 1 angle 0. Sorry. So this has to be 1 angle 0. So this will be 1 angle 0, right? So to make change here as well. This will be 1 angle 0. Yeah. So what is the Pmax here? I don't care whatever I'm getting here. I don't care, right? These are of no use to me. I can ignore this. So my Pmax will be Pmax will be 1 into 1 divided by 1.8. This is my Pmax, which is equals to 1 divided by 1.8, that is equals to 0.56. okay, so this is what your Pmax is equals to. Like this is your steady state stability limit. I hope it is clear. What is your steady state stability limit? What if you would have thought that you will solve it using some different manner? What you will do? You will say, sir, I can solve it using this, right? Without going into star into delta, I can individually find out the Pmax. What is the maximum power transfer here? What is the maximum power transfer here? Can I do it individually? If I neglect this, can I do it? So if I just, you will say, sir, you told, right, the parallel branches I need to neglect. So let me neglect this. If I neglect this, what will be the Pmax in this case? The Pmax will be 1 into 1. Here I have 1, here I have 1. And the reactance between the link is J2, is 2, basically, magnitude is 2. So it comes out by 0.5, which is wrong. This is wrong actually. Why? Because the problem is, right, some current will flow here, right, But here ultimately these 2 points are my endpoints. These 2 points are my endpoints where I'm actually connecting the voltage, right? So yeah, active power will flow through this path only. There is no possibility. But here what will happen? These two, like due to this, right, this is not the end point or the starting point. This is not the end point or the starting point. Some current will flow here. That is a problem. That will give me wrong answer. Right? This is not the correct answer. Okay. So why is it called as the maximum steady state limit? Why is it called as the maximum steady state limit? Because if you see, if uh, let's say this was the case, right? If let's say this link was not there actually, let's assume that this link was not there. If I assume this link was not there, then what will be the graph? Then the graph, right, will be something like this. 0.5. P max is 0.5, right? This is 0.5. This is 0.5. Okay. Now this delta equal to 90, and for this graph P max has increased. It is 0.56. So this has increased, right? So P max has increased. This is 0.56. So is this good? Of course this is good, right? Because now I have more headroom. My mechanical power, right? I can increase my mechanical power here as well. But for this graph, will I be able to do it? No. My mechanical power, I cannot make it my mechanical power higher here, right? Because obviously it is higher than the P max, so there will not be any intersecting point. So it will not be stable. It will not get any stable points, right? So that is the like advantage. So the advantage of adding capacitors in shunt is that the stability increases, right? Stability increases. So the advantage, if this capacitor was not there, then the Pmax was this, right? If this capacitor is there, then the Pmax is this. So the advantage of adding capacitor is, the advantage of adding capacitor is like it increases the, I can afford more variation in mechanical input, right? So is that we can have more variation in mechanical input power. Okay, that is the advantage, right? So that's why this is also called as the steady state limit, right? Because the more higher P max, the more range I'm getting for mechanical input. So if there is higher variation in the mechanical input, the stability increases, right? So basically indirectly it increases the steady state stability. So hence steady state stability is increased. Okay, steady state stability is increased. That is the advantage of increasing the Pmax. So let's check the next cases. So here will I be able to do start into delta? Here actually you will not be able to do start into delta. Why? Because here the potential actually has been provided. Somehow I am able to make the potential 1 angle delta 2. So here star into delta conversion is not allowed, right? So don't convert this into star or delta. So how can I understand what is the maximum power transferred here? So you will individually find out. So the voltages potential at 2 points have been, all the 3 points have been given. So individually find out the how much maximum this load is able to transfer. So let's say between this link, right, I'm able to transfer, just taking an example, let's say I'm able to transfer 1 pu of power, and between these link I'm able to transfer 2 pu of power. Then what will be your answer? What is the overall maximum power that I will be able to transfer through the line? What will be your answer? If your answer was 2, you are absolutely wrong. So it's same like I have two devices, right, and those two are in series. So this first resistor says that this first resistor is 1 ohm. It can at max support 1 amperes of current. The second resistor in series says I can at max support 2 amperes of current, right? So what is the safe limit of the current? What is the safe limit of the current? The safe limit of the current, if I pass 2 ampere, for this resistor it is fine, but for this resistor it is not fine. It is higher than its limit, right? So I cannot pass the maximum, I have to pass the minimum. So same here, I have to choose the minimum. So minimum of the two between P max 1 and P max 2. Now your question might be that, sir, why are we not converting this into delta? We were not converting this into delta because this potential is fixed. This potential is fixed, right? So it is not just a simple star, it is not a simple star configuration because this point potential is fixed. Somehow I am fixing the potential, right? So then you have to solve like this. Then you have to find out P max 1. So what will be P max 1? P max 1. So P max 1 will be the voltage magnitude between the 2 points. So let me find, this is my P max 1, right? PM1 and this is my PM2. Okay. So P max 1 will be what? Voltage magnitude upon the magnitude of the reactance. So it is 1 into 1 divided by magnitude of the reactance, that is 0.4 equals to 2.5 per unit. All the values are in per unit. Okay. What about P max 2? So it is equals to 1 into 1. So this point potential is also 1 divided by 0.2. So P max 2 is 5 per unit. So which one will you choose? You will choose the minimum one, right? You will choose the minimum one. You will not choose the maximum one. So your P max in this case, it will be minimum of those two values, minimum of 2.5 comma 5. So it will be 2.5 pu. 2.5 pu. Okay, this will be my P max for this transmission line. What about the last one? So in the last one, again this potential is fixed, right? As well as this side potential also has to be 1 angle 0, otherwise how will I be able to solve it? I have to solve this, right? Yeah, this also will be 1 angle 0. Sorry about it. So will you be able to solve it? So here remember, this is given, this is not given, right? This E angle delta. So I have to change this. This will be 1 angle 0. Yeah. So this potential is not given. So will you be able to find it now? I know what is my P max for the circuit C. What is my P max? It is very simple. For the circuit C, the P max is very simple, right? So P max will be E upon E upon 1.5. Okay, but I need the value of E, right? How will I find out the value of E? E into 1 upon 1.5, because this side potential is 1. So I need the value of 1. I need the value of P max. How will I find out the value of P max? So how will I find out the value of E? So E value will be like, I can, this is a series circuit, right? So current is here is I. So this current, E angle delta minus 1.2 angle theta divided by theta value should be given or not, that is what I'm thinking. Theta value should be given or not. Okay, theta value, actually no, theta, without theta giving theta as well, I think we can solve it. Yeah, I just need the magnitude, right? Magnitude, I think without theta we'll be able to solve it. Okay, so this will be divided by J 0.5. This current, incoming current, will be equals to outgoing current, that is 1.2 angle theta minus 1 angle 0 divided by J1. Okay, so this will be okay, so E JJ will get cancelled. E angle delta minus 1.2 angle theta is equals to 0.6 angle delta minus 0.5. Okay, so here will I be able to find out my E? Will I be able to find out my E? So my E angle delta will be equals to 1.8 angle theta minus 0.5. Okay, so let me solve this equation. So if I solve this equation, my E cos delta is equals to 1.8 cos theta minus 0.5, and my E sin delta is equals to 1.8 sin theta. Okay, so now would I be able to solve it any further? That is what I'm trying to think. Will I be able to solve it any further? So one thing I know, okay, one thing I know, what do I know? The condition for maximum power transfer. Condition for maximum power transfer when line is purely inductive. Okay, line is purely inductive. Okay, what was the condition? Condition was, right, it is purely inductive, right? So the delta angle, phase difference between them should be 90 degrees. Okay, delta angle will be equals to 90 degrees. Okay, delta angle will be equals to 90 degrees. So I will put that condition over here. Delta will be 90. So if delta is 90, this is 0, right? This is 0. So delta is 90, then this is 0, right? Cos this is 0. Cos delta, cos 90 is 0. So from here I can get the value of cos theta. Cos theta will be 1 by 3.6, right? So what will be sin theta? So 1 divided by 3.6 cos inverse sine of theta, it will be 0.96 0.9606. Okay, so this will become, now I will solve this equation. Delta is 90, so E is equals to, sine 90 is 1, E is equals to 1.8 sine theta, so 1.8 into sine theta, that is 0.9606. so I got my E value. So what will be my P max value? What is my P max value? P max value we have calculated, right? It is E divided by 1.5. So 1.8 into 0.9606 divided by 1.5. So this into 1.8 divided by 1.5. So this will be equals to 1.1527 pu. So this is how you will calculate the P max per unit. Okay, so I hope it is clear what we are doing here, right? I hope it is clear. So you might have a doubt, sir, here why we are not solving here? In this case, why we did not put delta equals to 90 here? We actually did, right? We indirectly did. So from here to here I saw what is the maximum, because here the voltage is fixed, the delta to angle is also fixed, right? So from here to here I found out the maximum power transfer. From here to here I found out the maximum power transfer. So you might have a doubt, sir, you could have done the same here as well, right? You could have done the same. From here to here, what is the maximum power transfer? That is E into 1.2 divided by 0.5. From here to here, what is the maximum power transfer? But here the current is fixed. Current has been fixed here, right? I is fixed. This is the I. But here current can change, right? So some current can flow here, some current can come here, some current can come there. So if the phase differs, then the current changes. So I just find out the individual P max and then compare. So basically what I am explaining is that, actually I should have mentioned in the question that here it is a voltage control device that is controlling the voltage. So it is a voltage controlled device, right? And here this is just a place where we are measuring the voltage. Okay, voltage measuring device. It is not a source. So here, as in the both sides we had sources, this is a source, this is a source, then I can apply this P max comparison. But this is not a source as per se, it is just the voltage at this point, voltage at this point. Right? So basically conclusion is, if across the 2 points, voltage is fixed, that is voltage source are applied. Okay, 2 points, voltage source is present. If across the 2 points voltage source is present, then you will apply this formula P max. E, like it will be V1 V2 upon X. Okay, so if at this node here I have V1, that is a source, this is a source, and at the other end I have V2, that is also a source. Okay, and in between I have X, right? But if voltages are not fixed, right? If voltages, let's say, are not fixed, so here I have connectivity, right? this is my 1 angle 0, and here I have my E angle delta, right? And it is just like I know the current here, right? I know the current let's say is some like 1 angle 45 degree. So from that I can find out the potential here. Voltage drop will be what? E angle delta minus, let's say this is some x1, so minus this is j x1 into 1 angle 45. So this is my V, and this V is given. It is not like it is not a source. So this is not a source, right? It is not a source, not a source, not a source. Then solve the circuit. It's very simple, right? If on the two ends voltages are given exactly their source, then I can directly solve it, right? I can directly solve it like this formula. If voltages are given, these both are source, but if one end is source, other end is not source, I cannot directly find out the P max here, right? That is the like crux of this discussion. And trust me, these things no one will tell you. No one. I know this confusions are there in your mind, but no one will clear you this. You see in any other coaching, they will first of all they will not explain these concepts. Okay, they will not even take these questions. Okay, and if they do, there will be some doubts. So I'm trying to clear every single doubt what can come in your mind. Okay, so yeah, now basically let's start with like this discussion we already did. What is the condition for maximum power transfer? Now we will derive the result for maximum power transfer. What is the value of the I know the angle delta has to be beta, right? I know angle delta has to be beta, but what about the impedance, magnitude of the impedance? What does my magnitude of impedance has to become, right? So if let's say I have a like link transmission line which consists of a R resistive load and resistance and inductance, right? So we model our short transmission line with resistance and a series inductance, right? If you don't understand, ignore it, right? We will see this in short transmission line, but for now just take my word that we model our short transmission line, it is also called as STL, right? STL as a series resistor and a inductance. Good to go. So now what will my PE expression be? One more thing, in short transmission line, your A, right, like this A is the ABCD parameter. A is actually 1 angle 0, and your B is simply Z angle theta Z. Okay, don't understand, just take my words for now. Everything will be derived in transmission line. Every single thing I will derive in transmission line, I promise. Okay, so just take my word that A will be 1 angle 0, B will be Z angle. So A, like it is just the transmission line parameters, that's it. It is just the transmission line parameters A, B, C, D. So A is 1 angle 0, so magnitude of A will be 1, angle of A will be 0, so alpha. So A is actually compared as magnitude of A alpha, and B is actually it is Z theta Z. Also it is known as magnitude of B into beta. So from here I can directly say that my alpha is 0 degree, right? Beta is theta Z, whatever is the theta Z here, right? And magnitude of A is 1, magnitude of A is 1, magnitude of B is simply magnitude of Z. Okay, so I will replace all these things here and I will find out the condition for maximum power transfer, right? So if I replace all these things here, right, so my PE will become, this will be same, this will be constant, VS, VR voltage are constant, right, upon B is magnitude of Z, right? I think we derived this expression in synchronous machines as well. This will be cos of theta Z minus delta, right, minus, what will this become, minus A is 1, so this will be only magnitude of VR square divided by B, that is magnitude of Z, into cos of beta, that is cos of theta Z, right, because alpha is 0, so it becomes cos of theta Z, right? So we have to maximize this. What is the condition for maximum power transfer? The condition for maximum power transfer is when my delta is equals to theta Z, delta equals to theta Z, right? So if my delta is equal to theta z, then I get the condition for maximum power transfer, right? Now what is the PE max expression? PE max expression is magnitude of Vs, magnitude of Vr divided by magnitude of, what is magnitude of Z? Magnitude of Z, it is a simple R, resistance inductance series Rx, right? So it will be R square plus X square. Okay, it will be R square plus X square. Okay, minus magnitude of VR square divided by, now that this will be still there, R square plus X square into cos of theta Z. Okay, because we have assumed that it is maximum. This is the condition for maximum. In the previous lecture we discussed about this, right? Now I want to see for what value. Now delta I have fixed, so for delta equal to theta Z I will get my P max. Now I want to check what is the value of X for which the power will be, P max will be maximum, right? P max will be maximum. Basically P max already we have calculated for delta equal to theta Z. This is the expression. I want to find out what is the value of X for which this expression becomes maximum, right? So one more thing I will discuss, that if I assume my Vs is equals to Vr, so the magnitude of the sending end voltage and the receiving end voltage are same, magnitudes is same. So magnitude of the sending end voltage I will assume, because I want to get to a expression, so for that I have to assume that magnitude of the sending end voltage and magnitude of the receiving end voltage is same. Okay, so if the magnitude of the sending end voltage and the receiving end voltage is same, if I assume it, so this is also called as flat voltage profile. Voltage profile. This is also called as flat voltage profile, right? When my magnitude of Vs is equals to magnitude of Vr. So if magnitude of Vs is equals to magnitude of Vr, then my P max basically becomes what? P max, this becomes magnitude of Vr square divided by R square plus X square minus magnitude of, like, why do I want to find out the value of reactance, right? I will explain, just in a second I will explain. Vr square divided by R square plus X square into cos of theta Z. So I want to find out the maximum value of this, right? So I have to differentiate this with respect to the variable. I will differentiate this value del P max divided by x dx. I will equate this with 0, right? So before proceeding, like, one more thing I will, like, because I want to write this expression in terms of r and x, right? So this cos theta z is what is cos theta z? Cos theta z is simply, it is a series resistance, and I know how to write cos theta z. It is r upon magnitude of z, which is equals to r upon under root of r square plus x square. R square plus x square. Okay, so now we can derive this value, right? We can derive, like, now we can convert this. This will become, basically this will become r into r square plus x square. It will not be under root anymore. So if I differentiate this now it is fine, because everything has been converted into in terms of r and x, right? So now if I differentiate this, right, what will I get? If I differentiate this, first of all, magnitude of Vr square is common, that will be outside. I am differentiating this with respect to x. So r is constant. So this will be what? Minus 1 by 2 divided by r square plus x square 3 by 2, right? Minus and minus 1 by 2 will be still, will minus 1 by 2 will be there? No, minus 1 will be there, right? It is just the inverse, minus 1 will be there, and this will become r square plus x square whole square. R is just a constant number, right, equals to 0. So we know of course that r is not equal to 0, r square plus x square also will not be equal to 0. Okay. Oh, one more thing I forgot to multiply. Here I need to multiply 2x, right? I need to multiply the inside function. It's just a chain rule. So I have to multiply 2x here, and similarly I have to multiply 2x here as well, right? I have to multiply 2x here as well. So automatically x is also not equal to 0. So what I can do is x is also not equal to 0. So I can simply remove all this. So 2x will get removed. This will have minus of half. The minus sign also can be removed. So this is half, and this is r. So this is actually half r square plus x square 3 by 2. Okay, minus half x square 2x x 3 by 2 minus r. So yeah, what will this become? This will be r, minus sign is anyways gone. So r square plus x square whole square, right, equal to 0. So now what will I do? I will multiply. What shall I multiply this? So if I take it on the right hand side and then square both sides, right? So this will be 1 by 4, this divided by r square plus x square whole cube will be equals to r square, I'm just squaring both sides, divided by r square plus x square whole raised to power 4, right? So this will become yeah, so this will be r square by 4 plus x square by 4 is equals to r square. So from here I can directly find out what is my x, right? So this will be 3 by 4. So x will be equals to, right, under root 3 r. X will be equals to under root 3 r. Now there are two solutions, right? Plus minus. Which one shall I choose? Both is valid. Both is valid, right? Because cos theta z will always be positive. It does not matter. Your theta z will always be positive, right? Theta z will always positive. And I'm squaring x. So it does not matter whether it's a capacitive or inductive. So we have assumed inductive. If it's plus, it will be inductive. It can be capacitive as well, right? If it is minus, right, minus root 2r, root 3r, it is inductive. It is capacitive, right? So this is also very good condition to remember. Of course, you will not derive this, right? So yes, we know for what value of delta the power transfer will be maximum, but for what value of x I can make the power transfer to maximum. So let's say I'm connecting an external reactance, right? How can I make it maximum, right? That is the main purpose of understanding this condition, deriving this condition, right? Okay, so yeah, both for inductive and capacitive case this will work. Okay, so this is the condition for which the maximum power will be transferred, right, from the source to load. Okay, so yeah, I hope you have understood this point. If you have understood, I will give you this as like questions. You try these questions. Okay, what is this? Try these questions by yourself, and then I will come back with the solutions. So I'm showing you all the questions that will solve in today's lecture, and I will come back with the solutions. So let's start with this one. Here they are asking me stability of a power system can be improved by what? By using series compensator, by using parallel transmission lines, by reducing the voltage of the transmission, right? So by using series compensator, so what does stability depend on, right? I know my steady state stability formula, but P steady state stability limit is known as P max. What is P max dependent on? It is E V upon X, right? So if I somehow reduce my X, right, or if I increase my voltage, both of them can actually help me in increasing the steady state limit, right? This we have learned already here, right? So if I connect a X of value, let's say this capacitive reactance, that will actually help me in increasing the steady state stability, like that will provide me the maximum P max, right? So by using series compensators, yes, if I can connect a series compensator, my X can reduce. So if previously, let's say my X was equals to Jx, right? Now Jxl, now if I add a compensator, series compensator, it will be Jxl minus Xc. Hence the magnitude of X will go down. If magnitude goes down, the steady state stability limit will go down. So one is absolutely a correct thing to do. Then what about the second one? Using parallel transmission lines. If I want to use parallel transmission lines, right? So yeah, again this is correct because we studied, right, when I used parallel capacitors in the previous lecture or in today's lecture only, the steady state limit increased. So of course option 2 is also a correct answer. What about the third one? Reducing voltage of the transmission. If I reduce the voltage of the transmission, will the steady state limit go up? No, it will be quite the opposite, it will go down. So 1 and 2 will be correct. So option D will be the correct answer for this particular question. Okay, so yeah, so if I use parallel transmission lines, here also the X, right, can be reduced. Here also the X can be reduced while using series compensators. Okay, so let's now move on to the next one. So next one is this question. So the steady state limit, for round rotor basically means it is talking about the cylindrical rotor. Cylindrical rotor and salient pole 3-phase synchronous generator are attained at the values of power angle delta, okay, equals to this pi by 2 and pi by 2 respectively, less than pi by 2, greater than pi by 2. Okay, so when does like the maximum power transfer occurs? That is what they're asking, right? Steady state stability limits. What for what value of delta? I know for a cylindrical rotor, this is the formula, right? When this will be maximum? When delta is 90, right? This will be EV VTM1 sine delta. So when delta is 90, my PE will be maximum, that is P max. Okay. Right now for a round rotor it is 90, it is correct, but for a salient pole, is it correct? No. For a salient pole, if you remember, this was the formula, right, of PE. Like I have told you also how to remember, so all these things I have told you. This is the formula for PE, and we know for a salient pole rotor it is a combination of, what is this? This is the reluctance power, right? Reluctance power. This is the synchronizing power, like synchronous generator power. This is the reluctance power due to the reluctance torque. So it is a combination of two sinusoids. One is with frequency delta, another one is 2 delta, right? So if I add this, right, if I add this, overall the resultant will be somewhat like this. So before 45, the value will be high, right? Before 45, this is the half 45 degrees. So say not 45, so this is 90, right? This is 90, right? So this will be before 90, the value, both of these will be added because both of them are positive. Before 90, both of them are added. So graph will be somewhat like this. Just after 90, what will happen? The second term becomes negative, the first term is still positive, so the value will go down. The value will go down, right? So actually what will happen? So no, not so, until this point, right, both are increasing function. So both of them are increasing, so the value will rise up very quickly. But just after 45, what do you observe? Just after 45, what do you observe? Both the values are like this is reducing, this is increasing. This value is increasing, but this is still reducing, right? So I exactly don't know exactly at what point I will get a maxima. I cannot comment, but somewhat the rate of increase will decrease, okay, and somewhere in between I will get a maxima. And at this point, right, at this 90 degree, both of them has to be same, because here it is, let's say P max, and here it is 0. So 0 plus P max will be P max only. So it will cut at this point. After this, what will happen? Value will actually go below this graph because this is something negative, right? Minus 1 plus 4. So minus 3 plus 3, right? So I will be somewhere below this green graph. So it will be somewhat below. Okay. So this will be the graph, and this will be somewhat, this will be my delta. Now exactly I will not be able to comment where the delta max is. It depends on the value of this xq, xd, all these things, vt. Okay, I cannot exactly comment what is the maxima point, but I can definitely say that the maxima will lie before, this is my pi by 2, right? Maxima will lie before pi by 2. whatever this delta is, delta will be, this delta has to be less than pi by 2, because after this point this reduces, this increases, so it has to be somewhat lower, right? So yes, so delta has to be less than pi by 2, it cannot be equals to pi by 2. So for round rotor it will be equals to pi by 2, for salient pole it will be less than pi by 2. So option D will be the correct answer for this particular question. Now let's solve the next question. So find the steady state power limit. Okay, whenever they are talking about steady state power limit, they are basically talking about the Pmax. They are basically talking about the Pmax. Okay, okay, this kind of question already we have done. This kind of question already we have done. Actually, yeah, this is the same question, right? This is already done. Which question is this? Same question. Here, there I provided the picture. Here I am not providing you the picture. What is the same question? This is the same question, right? If you remember, yeah, this one. This question. Here the data was changed. Basically, this was point. No, data is also not changed. Data is also same. Exact same ditto question, right? So it is 74C. Okay, same solution. Just here I have provided the circuit like the power system diagram. Here directly I have provided the like written format. So you should be able to solve both ways, both written and the text and the circuit diagram, right? So 74C is the same question, right? Both of them you can read, go and have a read. It is just exactly the same question. Okay, so yeah, that is done. Solution is done basically for this. Find the value of the reactance in ohms to be connected in series for maximum power transfer. Now this is interesting, right? We have to find out the value of reactance in ohms that I need to connect for maximum power transfer. So not that difficult actually, not that difficult. We have already derived what is the value of the reactance that I need to connect. What is the value of the reactance? The value of the reactance that I need to connect has to be equals to this, right? I just wanted to mention, like I was wrong here actually, that X will have two solutions. Here I was wrong. Okay, X will have only one solution. This will be the correct solution and this will be the incorrect solution. Why? Intuitively I can say, because what do I want? I want my X to reduce, right? For power to become higher, I want my X to reduce. That's why we connect series compensators and all those things, right? So I want my X to reduce. So if I want my X to reduce, what do I have to do? I simply have to add a capacitive network, because generally the line is inductive, right? So how can you prove it mathematically? You can prove it mathematically. You find out the double differentiation of this value, right? You find out double differentiation dp Emax. Okay, no need of doing this, right? I'm just telling you for those guys who need some assurance that yes, it mathematically how can you prove it? Dp upon dx, dp d square upon dx whole square equals to, if it comes out to be positive, that means it is a what? It is a minima, right? And this will come out to be positive. This will come out to be positive for what? This will come out to be positive for my x equals to, you will see, you will put x equals to plus root 3r, you will see it is coming out to be positive, right? And this value will come out to be negative for x equals to, you can verify, you can double differentiate for x equal to minus root 3 by 2, hence we will get a maxima, right? Hence we will get a maxima. So this is the only solution. So I have to add a capacitive. So basically the conclusion is, if line is inductive, then I have to add a capacitive reactance of value root 3r, then I will get the maximum power. If it is flipped, right? If it is flipped, if the line is capacitive, then I have to add a inductive, because I want to cancel out the reactance, right? I want to reduce the reactance. then I have to add a inductive reactance of magnitude root 3R. This is the conclusion. This is ultimately what you have to keep in mind. So note. Okay, this is the main conclusion. One more thing, what is my X? X is actually the total reactance, right? X is the total reactance. Okay, it is the total reactance of the line. It is the total reactance of the line. So magnitude of X will be actually X total. Magnitude of X total is root 3R. So if the line is already inductive, I have to add a capacitive reactance of what reactance? X total will be root 3R. Magnitude of X total will be root 3R. That is for certain, right? So how much value of reactance I need to add, right? If it is inductive, I need to add, and if the line has already reactance of X naught or XL, let's say, if the line has a reactance of XL already, line has a reactance of XL, but overall total reactance must be root 3R for maximum power transfer, right? So if it is inductive, I have to add a capacitive one. If XL is, and if magnitude of XL is greater than magnitude of X total, right? Then I will need to simply add a capacitive reactance to reduce the line reactance, right? What am I telling is, let's say this is my line reactance. Okay, in this case, let's assume that this is my line, this is my R, this is my XL, JXL, right? What is the condition for maximum power transfer? The condition, if I just ignore the inductance, right, the reactive value must be root 3R, but currently it is XL, right? So XL is here, and XL magnitude is higher. So what do I need to do to make it root 3R? I will add a capacitive reactance in series so that I can reduce it. So we'll add a capacitive reactance of what value? XC will be what? It will be XL minus root 3 into R. This much value if I add, sorry, root 3 into, it will be root 3 into R minus XL. So what will be the total? What will be the total reactance now? It will be XC plus XL, right? Which is root 3R. Correct? We'll do example. I will show you. We'll do example. I will explain you. Okay. Same here as well. That here, if the line is capacitive and I know my XC, magnitude of XC is greater than the X total, that is root 3R, right? Then what will do? I will add a inductive reactance of what value? XC. So XL will be what? It will be again root 3 minus XC, right? So let us do example. From there we will understand this even better. Let us do example, right? So this is the example. Basically, if I have a line, right, whose resistance and inductance is this value, when will the maximum power transfer occur? What value of reactance I need to connect? So I know what is the condition for maximum power. My overall total reactance, like after connecting. So after connecting, what will the circuit look like? So I will have a 1 ohm resistor here. I will have this J2 ohm. Okay, I will have this 1 ohm. Then I will connect a reactance Z. Okay, so I am connecting a reactance. I don't know whether it is capacitive or inductive. So my X total must be equals to root 3 into R, right? Currently it is equals to what? It is equals to X. If I assume it to be inductive, it will be X plus 2. If I assume it to be reactive, capacitive, it will be 2 minus X, right? Both will be opposing or adding. Now what is R? R is 1. So it has to be 1.732. So I am seeing that my magnitude of X total, right? Currently my inductive reactance is greater than the X total. So of course I will need to add a capacitance, right? I will need to add a capacitor to reduce the overall reactance to this value, because at this value only the power transfer will be maximum. So I will need to add a capacitance. Right? So mine X total will be equals to what value I need to connect? So it has to be this, right? It has to be capacitive because I want to reduce. I want to go to 7.32. So I have to add a capacitive reactance. So x will be what? So 2 minus x will be equals to 1.732. So from here I will get my x value. What will be the x value? X value will come out to be 1.722 plus 2. So it comes out to be 0.268, and the nature will be what? Nature will be capacitive. Right? Now there can be two solutions of this. So let's say if they ask find the value of the reactance, or find the magnitude of the reactance, or find the value of inductive reactance to be connected. So what will you write here? So we know, from the conclusion we know we have to add a capacitive reactance, but here they are asking inductive reactance. So you will just add a negative sign. So in capacitive reactance is plus 0.286, right? 268. So inductive reactance will be what? Inductive reactance will be just negative, because I know the nature is capacitive. I have to just use the negative sign. So inductive reactance will be minus 0.268, right? Ohms. This will be an answer. Okay. What if they ask the magnitude? Generally they will not ask this inductive reactance. They don't want to confuse you. Generally they will ask you the magnitude. So magnitude will be this value only. It's positive, right? Magnitude I hope you're able to answer. Okay. So yeah, I have to make a change in the question. It should be inductive reactance here. So answer will be a bit trickier. Okay, I hope it is clear now. Okay, now let's come to the next topic, that is the inertia constant. We'll learn about the inertia constant. What is inertia constant? It is just another way to represent m. Okay, we'll see the relation between m and h very soon. Okay, so inertia constant, the definition, you have to remember this, right? Unfortunately, there is no other way. You have to remember it. Okay, h equals to kinetic energy stored in rotor in millijoule to rating of the machine in MVA. Kinetic energy stored in rotor of the in millijoule and rating of the machine in MVA. Okay, so what is the kinetic energy stored in the machine? So it is basically Ke, kinetic energy, upon G, the rating. So what is the unit of this? It is megajoule per MVA. The unit of H, or inertia constant, is megajoule per H, right? Sometimes they give this as well. Sometimes they give this as unit as well. So what is megajoule? Megajoule is simply megawatt upon, unit is megawatt into second. So power into time is known as energy into second divided by MVA. So unit of, like, this dimensions of MVA and megawatt are actually same, right? Because I know S equals to P plus JQ. If I'm writing this, right, that means the dimensions of P and J has to be, dimensions of P and S has to be same, because it has to follow the homogeneity property, right? Simple physics. So this can get cancelled. So ultimately the inertia constant, the unit of inertia constant is second. This is the unit of inertia constant. Right? Now can I really like, what does it actually mean? What does it actually mean? What is the physical significance? What is the physical significance? Basically it means in how many seconds, seconds will the rating be equals to the kinetic energy stored in the machine. So in how many seconds will the kinetic energy stored in rotor be equals to rating of machine. Okay, so when both of them are equal, like in how many seconds I am able to make them equal, that is the meaning, physical meaning of this inertia constant h, right? So now I want to define this. What is kinetic energy? What is kinetic energy? Or what I can say, what is what is kinetic energy from here? Kinetic energy is equals to g rating of the machine into h inertia constant. What is kinetic energy? It is half into moment of inertia into omega m square. It is a mechanical quantity, omega m square, if you remember it properly, right? So again, if I derive this is equals to my g into h. I need to convert everything into electrical. I need to convert everything into electrical. So if I convert everything into electrical, this will be half g, this will be 2 by p whole square into omega e. I'm not explaining how I'm writing this. Okay, into g into h. So what is this value actually? Do you remember this value? Does something click in your mind? Okay, so what is this value actually? If you remember the swing equation, right? PE, PM minus PE was equals to m into d square delta upon dt square, right? So I can go back there again. I can again go back there if you want to get back to the swing equation. Yeah, this one, right? So j omega into 2 by p whole square was actually equals to m. j omega into 2 by p whole square was actually equals to m, right? So I can copy this. So 1 omega will be left out, but other things will be replaced with m. So the relation between m and h we are deriving. So half into m into omega e is equals to g into h. Okay. So from here I can directly say what is my m equals to. I want to write m in terms of frequency, right? So m is equals to gh 2gh by omega e. Now what is my omega e? Omega e is nothing but 2 pi f, right? It is electrical quantity, it is not mechanical. So omega e is 2 pi f, right? It is electrical quantity. So if I replace here, this will become gh upon pi f. Very important relation, gh upon pi f. Okay, so this is your m value equals to. So this is actually your derivation for m. Like both of them sometimes they are called. So m is what? M is the angular momentum, right? M is called as the angular momentum. What was it equals to? If you remember, it was j into omega e, right? It was j into omega e, correct? J into omega e into 2 by p square, that was there. Okay, so j into omega e is what? Angular momentum. So that's why angular momentum is this m. That is equals to what? That is equals to my, that is related with my inertia constant as this gh upon pi f. So it is megajoule second per electrical radian. Okay, that is what my m is equals to. Now remember, that is the unit basically, megajoule second per unit. So this is the unit. So unit of g is, in either you can write mva, right, and unit of h is seconds, right? So mva into seconds. Mva is same as, oh, sorry, it is watt, right? It cannot be megajoule into second, cannot be. Okay, sorry, frequency is also there, right? Yeah. So what is g into h? G into h is kinetic energy, right? G into h is kinetic energy. What is the unit of kinetic energy? It is joules. So that's why megajoules. Okay. And what is the unit of f? F unit is 1 by seconds, right? 1 by time. So that's why the 1 of the second went up. What is the unit of pi? it is electrical. It is a electrical unit, so that is electrical radiance. Sometimes this is also written as this, GH is 180 into F. Sometimes it will be written. Then your angular momentum, unit of angular momentum will be in megajoules into seconds per electrical degree. Then the unit will change, remember, right? Sometimes 180 is divided, sometimes pi is divided. When to divide what, it is very important to understand. When to divide what, I will conclude as well. Okay, when to divide what. So this you have to remember. This is a very, very important formula. This you have to remember. Okay, कितनी बार derive करोगे? Like you can obviously derive it, that's not a problem, but it's good if you are able to remember this, because this will be used in multiple places. This will be used in multiple places. Okay. So one more thing, in per unit, what will be the value? In per unit, if I want to define this value in per unit, how will I define this in per unit? Okay. So okay, what is, because I want to write this in per unit, so what is my H in per unit? This is second I cannot define, right? No, this is not in per unit. How can I define this value in per unit? Because sometimes they, what they are called, they are defined in per unit as well. If I want to change the base, okay, let's say I want to change, like let's say my M is given in per unit. Okay, let's say in system 1 I want to define in system 2 what will be the per unit value of M. How will I define it? So this is inertia constant H, right? So H is will not change. Frequency also we don't define in terms of like as base values. What changes in base? The voltage. So here the voltage will be V base 1 and S base 1. Here the voltage will be V base 2 and S base 2. So this G value can change, except this, all this will remain constant, right? Anyways, the actual value will be constant. What do I mean? I will explain. So what is MPU1? What is M actual here? M actual here will be MPU1 into the base, M base 1. And here what will be the M actual? Actual value will never change, MPU2 into M base 2. Okay. Into M base 2, right? So what can I do? What can I do here is I can take out the ratio of these, right? If I take out the ratio, M actual upon M actual, so it will be 1 will be equals to MPU1 upon MPU2 into M base 1 upon M base 2. So M base 1 upon M base 2. So what will be the base value? Basically in base I see H and F, all these are not changing, right? This will be same only, just the G will change because S base has changed. So this will have S base 1 and S base 2, right? This will be multiplied with G1 and G2, that is basically SB1 and SB2. So ratio will become, from here I can see here this will be G1 proportional to G1 or SB1, and this will be proportional to SB2. So from here I can say the new per unit value will be basically equals to the old per unit. So new per unit value will be equals to basically the old per unit into the old base divided by the new base. Okay, so do you need to remember it? No, you can derive it, right? I have derived it, so you can derive it. It's not like you have to remember it. Now, what is the inertia constant in per unit value? If I want to find out the inertia constant in per unit, how can I find it out? Generally, here inertia constant has a unit. They don't discuss. Okay, this is the value basically. In per unit, you can find it out. Whatever will be the base. This will be the base basically. I can divide it. Okay, this will be the base. I can divide it. Like with the base, you can divide. You can get the per unit value. Okay, so I hope you have understood. Now let's do a few numericals so that we can understand this even better. Okay, so this is the first basic question. So a 500 megawatt 21 kilovolt. So the rating, power rating is given to me as 500 megawatt, and voltage rating is 21 kilovolt. Frequency is 50 hertz. Number of poles is 2. Synchronous generator with a rated power factor of 0.9 has a moment of inertia 27.5 into 10, right? So its moment of inertia J per meter square. Calculate the inertia constant H. What will be the inertia constant H, right? So inertia constant H is what? It is simply equals to kinetic energy upon the rating of the machine. So it is operating at a power factor of 0.9. Can you find out the rating of the machine? What will be the rating of the machine? So rating of the machine will be what? P upon the power factor. So it will be P is 500 upon 0.9 MVA. So this will be 500 upon 0.9. So 555 MVA. Okay. So this is my G basically 555.55. But what is the kinetic energy stored? Kinetic energy stored will be half into J into omega square. Right? Remember, omega must be in electrical, right? Omega cannot be in mechanical. So what is the electrical speed? Or what is either you can write omega s, or you can directly write what is omega. Omega will be equals to what? Omega in electrical will be equals to what? It will be simply 2 pi f. That is what omega in electrical is. So I can replace it over here. Half into J. J is given to me 27.5 into 10 cube into omega square. Omega is basically equals to 2 into 50, basically 100 pi it is, because frequency is 50 hertz. No, okay, frequency they have not given me. What is frequency actually? Oh, frequency is given, right? 50 hertz. Okay. This whole square, right? This in megajoules, so I will multiply minus 10 raised to the power minus 6. So what will this value come out? So 100 into pi whole square into 10 cube into 10 raised to the power 6 into 27.5 divided by 2. Okay, this comes out actually very low value. How is it possible? It comes out very low value. Okay, maybe I'm doing some sort of mistake. What am I doing here? It should not be this low value, man. 100 into pi whole square. It is almost into 10 cube. Oh, sorry. 100 into pi whole square into 10 cube into 27.5 divided by 2 into 10 raised to 4. Yeah, now it is fine. Yeah, divided by 555.55, it comes out to be 2.44. Okay, so the value will come out to be 2.44 seconds. So you don't have to worry about this, right? So many I have seen many guys convert this again from mechanical. They will first of all find out omega m, then they will do this 2 by p into omega e. No need to do all this, right? Directly I know. Sorry, then they will convert this into omega I. But directly I know what is my omega E is equals to. It is the electrical quantity, it is 2 pi f. So I don't need to do all this conversion, right? Directly I can find it out. Okay, no need to do all this conversion. Okay. So yeah, 2.44 seconds will be the answer for this question. Let's now solve the next one. So in the next question, what they have told, that we have a 50 hertz 4 pole 22 kilowatt machine. So frequency is 50 hertz. It is a 4 pole machine and the rating of the machine is 500 MVA. It is a 22 kilovolt turbo generator rated at a power factor of 0.8. Suddenly a fault occurs, causing the electrical power output to drop by 40%. Okay, suddenly a fault occurs causing the electrical power output to drop by 40% when the mechanical power input of the shaft remains constant. So initially my PM naught was equals to P naught, but suddenly the new power electrical power output suddenly has reduced due to fall by 40%. It has dropped by 40%. So my new power will be 0.6 PE0, the previous power, right? For it has dropped by 40%. Okay, it has dropped by 40%. That is what they are telling me. Now what they are telling me is, so they have already told me what is the initial power. It is rated power and it is operating at rated output. So if it is operating at rated output, what is the PE naught? It will be equals to what? It will be S into the power factor 0.8. That will be equals to 400 mega watt. So it is operating at 400 megawatt, but suddenly it has reduced to 60% of this, right? 60% is 240 megawatt. Okay, 60% is 240 megawatt. Okay, now what they're telling me, determine the accelerating torque developed in the generator at the time of the fault in mega Newton meter. So what is the accelerating torque? What is the accelerating torque actually? So accelerating torque is basically nothing but the accelerating power upon omega m, right? With whatever speed the rotor is rotating. What is the speed? Because just at the instant, the speed will not instantaneously change. It will still rotate with some like constant speed only just at the instant of fault. So what is omega m? How do I find out omega m? Omega n will be nothing but 2 pi ns, because it of course at steady state nr will be equals to ns before the fault. So it will be 2 pi ns by 60. What is ns? Ns is 2 pi, it is 120 f by p, 60 into poles. Number of poles is given to me, that is 4. So from here I can easily find out this will be 2, this will get cancelled, right? So it will be 50 pi. So omega m is simply 50 pi, right? So what is accelerating power? So accelerating power is nothing but it is a mechanical minus the electrical power. Mechanical power has not changed, that is PM naught. PM1 is equals to PM naught. PM naught minus PE1, electrical power has changed due to the fault, right? So this will be what is PM naught? PM naught is nothing but PE naught. So it is PE naught minus PE1. PE1 is nothing but 0.6 PE naught. So this is 0.6 PE naught. So ultimately your PE naught comes out to be 0.4. Sorry, your accelerating power comes out to be 0.4 PE naught. So ultimately this is 160 simply. This is 160 megawatt upon omega m. Now they are asking in meganewton meter. They are asking in meganewton meter. So I will calculate this value. This will be PE meganewton meter. So remember, torque is a electrical quantity. Torque is a electrical quantity. So I don't need to change it into mechanical, because this is a mechanical speed, right? This is the mechanical speed. This is not the electrical speed. So I don't need to do any conversion. This will be 50 pi. Okay. So from here I can easily find out the torque value. This will, the unit will be, you will see it will be meganewton meter only. Unit will come out to be meganewton meter. Torque unit cannot change. So this will be 50 into pi into 160. So this comes out to be 1.02. 1.02 meganewton meter. Okay. So this is my accelerating torque. This is basically the answer of this question, right? So accelerating torque is what? Nothing but accelerating power upon omega m. Remember, we don't do any unit conversion here into electrical radians, because this is a mechanical parameter. Torque is a physical parameter, mechanical parameter, right? Your electrical power is a electrical parameter. If I want to find out something electrical, then I will do this conversion. Okay, then I will do this conversion. I hope it is clear to you. Okay. So now what, one more thing I forgot to mention here. What is the MPU, right? What is the value of MPU if I want to calculate the MPU, right? So let me calculate the value of MPU. So like this, right? Change of base I will explain in the next slide. If I want to calculate the MPU, okay. So if I want to write the per unit value of M, how will I find out the per unit value of M, right? So M is equals to H into, so M, we already know M is equals to GH by pi f, right? Now what else do I know? I know this thing. I know this thing, that my PM minus PE is equals to M into d square delta upon dt square, right? D square delta upon dt square. This much I know, right? Now if I am dividing this by, if I want to write PM in per unit, PE in per unit, how will I write it? So PM in per unit will be what? I have to divide by the rating. So PM minus PE divided by the rating, right? Dividing by rating, that is G, right? S or G both are interchangeable, right? S is equals to G basically, don't worry. That is equals to M divided by G into d square delta upon dt square. Okay. So this will be basically PM per unit minus PU per unit. Now this whole thing is per unit, right? This whole thing divided by the G rating is actually per unit, right? So we know that angle, power factor angle, those are already in per unit, but is delta and T per unit? Delta and T are actually not in per unit, right? So what will be my MPU? So I can write this as M delta square upon dt whole square in per unit. Okay. So what will be the value of MPU? From here, because this whole thing, the unit of this whole thing is actually watts, megawatts, right? So that's why I'm dividing by the S base. The unit of this whole thing is watts. So I cannot directly say that like I want to just say what is your MPU? Is MPU is equals to M by G? No. MPU is not equal to M by G. MPU is not equal to M by G. Why? Because unit of this whole thing, right? This whole thing unit is watts. It is not just unit of M, and this is not unitless. This is some unit, right? But what can I certainly say? What can I certainly say? I can certainly say, like, this is what, if I'm dividing by G, right? I can certainly say that my M base is proportional, inversely proportional to G. So one more thing I want to say, what is the like per unit value of this M base, like this inertia constant, if I want to say what is the per unit value. So we are dividing this M by G, right? So what is M equals to? So M is actually equals to what? GH by pi f, right? M is equals to GH by pi f, right? So if I'm dividing by G, right, this will be H by pi f. Okay. Now this is not exactly the per unit value. This is exactly not the per unit value. This is not exactly the per unit value. But what do I know? If I multiply this term by d square delta upon dt square, what will I get? I will get the per unit, because this will be in per unit, right? Why? Because here the left hand side is on per unit, the right hand side is on per unit. So if I'm dividing this by G, this whole quantity will be in per unit, right? So that's why I have told you that M base is proportional to like 1 by G. So this whole quantity is per unit. So what is the unit of this? Simple units and dimension. The unit of this, right, this whole quantity will be radian, second square divided by radian, because the unit needs to get cancelled, right? The unit of this will be second square divided by radian. That will be the unit. Okay. But sometimes what they do is they tell you that your MPU is actually this value, that is independent of this G, because I'm dividing this by G, right? So sometimes they tell you that this is my per unit, but exactly this is not my per unit. The per unit is this multiplied by some constant, because this also will have some base, right? So actually MPU is equals to what? MPU is equals to this M actual divided by G, right? M actual value of the M divided by G into some constant K. What is this constant? This value, right? Because I have to multiply this constant as well, right? This is not unitless. This has some unit. So let me name this constant as K. This is an actual value. So this also will not change, right? This K constant also is an actual. This will not change. Okay. So ultimately I can safely say, like, if you are not able to understand the previous explanation, that from here also I can say that my MPU, these are all actual values. So this will not change. What will change? The base G will change. MPU is inversely proportional to 1 by G. So if you are having problems with the previous explanation, I have explained it over here again, right? Because I'm dividing both sides by G. I know the left hand side is in per unit. So right hand side also has to be in per unit. So this whole unit has to be in per unit. So I'm dividing M by G. So M by G, right, is exactly not equal to per unit, because I'm multiplying by this, then I'm getting this per unit. So what is the unit of this? Second square radian, right? So if I'm dividing MPU by like M actual upon G, so this is not exactly per unit. I have to multiply by some constant, the actual value, that will yield me the per unit, right? I know this will not change, actual value and the constant will not change. Ultimately, my MPU is inversely proportional to 1 by G. That is the most important portion that you need to understand from this conclusion, okay? Your M inertia constant is inversely proportional to the generator rating, okay? That's the only thing that you need to keep in mind. like you could have understood this directly here as well, that what is your H proportional to? Your H is inversely proportional to the G, right? So same, your per unit value also will be inversely proportional to G, like your base also will be inversely proportional to G, right? So like that also you can understand, but the most important conclusion, the conclusion is this one. This is the most important conclusion out of the discussion. Now let's solve the questions basically which we are solving. So this was the question. So here a 50 hertz generating unit has an inertia constant of 2 megajoule per MVA, right? Inertia constant, what is given? 2 megajoule per MVA. What is it? It is H. Just see the units. Just see the units. It is megajoule per unit, right? Megajoule per unit means what? It means kinetic energy upon the generator rating. G KE upon G, right? So this will be equals to 2. This is equals to 2, and my frequency F is equals to 50 hertz, right? The machine is initially operating at steady state synchronous speed. Machine is initially operating at steady state synchronous speed. Okay, so it is initially steady state and delivering 1 pu of power. So power delivered is 1 pu, and the initial rotor angle delta naught is equals to 5 degrees. Following a short circuit fault at the generator terminals, so if a short circuit fault has occurred at the generator terminals, what will be the power delivered? Power will suddenly go to 0, right? P1 will be 0 because short circuit fault has occurred. It is a low power phenomena, so the power will suddenly go to 0, right? So there will be some accelerating power. So PA will be equal, so initially this was the power delivered, this is my PE naught, right? And initially it is at steady state, so PM naught also will be equals to PE naught, that is equals to 1 pu. Okay, so from here my accelerating power PA is equals to PM naught is equals to PE naught, that is equals to 1 pu, right? So accelerating power will be what? PM1 minus PE1. I know initially the mechanical power instantly I cannot change, right? They have told me mechanical input remains constant, so this will be equals to PM naught minus PE1. PE1 is 0, so this will be simply PM naught, that is 1. So the accelerating power is 1. Previously the accelerating power was simply 0 because it was in steady state. Determine the rotor angle delta at t equals to, I have to determine the rotor angle delta at t equals to 0.02 seconds. Okay, so one thing I know, a very basic formula in linear motion, that is S equals to initial S naught plus half AT square, right? If you remember this formula, do you remember this formula? Now in curvilinear motion, I will have the formula delta of t, right, will be equals to initial angle delta naught plus half angular acceleration, half alpha into t square, right? So what is alpha? I know this formula, that PM minus PE is equals to m into d square upon dt whole square, that is m alpha. So alpha from here I will get, it is PA divided by m. So I will replace my PA divided by m in this equation, right? So this is also another very important formula that will be used multiple times. So my delta of t will be equals to delta naught, the initial angle, plus half PA divided by m t square, right? Now this is a very important formula, and I have derived it as well, how it comes, right, related with the linear motion. So in the question, what will be happening, your PA will be given in per unit, right? PA is given per unit value 1 pu, right? 1 pu. Now how do I write this thing in per unit? Because I've already told you that m is actually not in per unit, right? But m times this whole thing is in per unit. M times this whole thing is in per unit. M times this whole thing is in per unit, correct? So its unit is second square by radian, and anyways radian does not have any unit. It is unitless, right? Radian is unitless. So if the unit of this is only second square, degree angle does not have any unit, it is unitless. Okay, second square. So how do I make it in per unit? How do I convert this in per unit value? So already this m has a unit of h by pi f, right? In if I want to write, m is actually h by pi f What is the unit? I have already divided by g, right? So what is the unit? The unit is secant square divided by radian, and radian is unitless. And already, what will be the unit of then? H by pi f, like I'm doing m by pi f, right? By m by t square, basically m by t square, right? So this has a unit of secant square by radian, this has a unit of secant square, so ultimately this unit becomes 1 by radian, and radian is dimensionless, it is dimensionless. So the conclusion is we get the quantity in per unit. If I'm dividing by time square, I'm getting the quantity in per unit, so I don't need to do anything. That is the beauty. So what will be m value? M value will be simply h by pi f, right? I don't need to do anything different, just put the values here. So h is what? H is 2 megajoule upon MVA, right? H is 2 megajoule upon MVA. So it is, again, it is already unitless. Dividing by pi, this is dimensionless. F I am dividing, yes, you are correct, I am dividing by f. But this whole thing has a unit of secant square. Already I will put here also time in seconds, the units will get cancelled. So automatically this value will be in per unit. So automatically this value will be in already in per unit, right? I don't need to do anything. That is the beauty. That is the beauty, right? So this will come out to be equals to 2 upon pi into 50, right? So what will be my delta of t ultimately? What is the delta of t at t equals to? They have asked at t equals to 0.02 seconds. So this will be delta naught. What is the initial angle? Now remember, they have asked me to determine the rotor. They have asked me to determine the rotor angle. So if you want to find out in radians, right? If you want to find out in radians, the delta value in radians, so you have to put this pi in radians. Okay. If you want to find this in degrees, then you put this pi in degrees. It's your wish. It's your wish, right? So if you, let's say, first of all, I want to find in degrees only. So 5 degree is given to me, so that is 5 degree. Right? I will do both ways. 5 degree plus half into PA. PA is what? PA is accelerating power, that is 1 pu. 1 divided by m, that is 2 upon, now I will not write here pi, I will write here 180. I will write here 180 into frequency, right? Because I am calculating in degrees, into t square. What is t square? So this comes out to be very large value. T square is how much? T is 0.02 seconds whole square, right? So in degrees, this value will come out to be 0.02 whole square divided by 2 into 180 into 50 plus 5. So in degrees, it comes out to be 6.8 degrees. In radians, if I want to calculate in radians, right? In radians, if I want to calculate in radians, this will be 5 divided by 180 into pi. So degrees will be converted into radians, 0.0826. Okay, plus this will be same half, this will be in per unit 1, this will be same 2. Now this will be pi, right? This will not be 180, this will be pi, because I am calculating in radians into frequency. Everything else will be same, 0.02 whole square. You will see, you will get the radian equivalent of this, right? So this will actually come out to be pi into 50 into 0.02 whole square divided by 2 plus 0.08726. So this comes out to be 0.11867 radian. Okay, so if I convert this back into degrees, right, this will be 180 divided by pi. Yeah, we are getting the exact same value, 6.8. So if you want to find in degrees, you will replace pi with 180 here. If you want to find in radians, you will replace pi with pi only. Okay, that is one conclusion that I wanted to give. So we have done all the assignment problems in today's lecture. In the next lecture, we will be starting with transient stability. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. So today we will be discussing about transient stability, right? Also, we will be discussing about critical clearing time and what do we actually mean by critical clearing time, and like what are the actual definitions, right? I think this lecture will be very helpful. Even if you have studied this previously, I know there might be few doubts that will come into your mind, so it's my duty to clear all those doubts. So trust me, after watching this video, every single thing will be cleared regarding transient stability. I have studied it myself. I was also having some doubts during my preparation as well. So I know what are the points which we need to focus on. So we will discuss about all those things. So first of all, let's discuss what is transient stability. So we have discussed about steady state stability, where we were gradually increasing the load. The load, or if the load or the input, the output or the input, we are gradually changing, right? There was gradual changes in steady state stability. But in transient stability, we are not gradually changing it. In transient stability, there are sudden changes, like some fault has occurred. Suddenly, it has gone to zero, right? Power has suddenly gone to zero. Generator input, I'm suddenly making the generator input to be zero. Suddenly I'm changing the generator input to a high value. So these sudden changes, we will understand what happens, like what happens to the delta, because I know, right, gradually I know that this is my stable point and it will oscillate around the stable point and it will come back. That is what our graph shows. So if our graph initially, we were initially at point A, if I was at initially at point A, right, here what was the speed at this point A? What was the speed at the point A? The speed at point A was omega r was equals to omega s. It was at steady state, and my delta naught, like pm naught, is pm naught is equals to pe naught initially, right, at point A. But let's say I suddenly increased my mechanical power. Suddenly what will happen? Yes, it will come to this stable point B. At steady state, it will come to B point. Yes, there is intersection. So this is the stable point. Of course, it will come to B. But in between, what will happen? We have not discussed about that, right? I just have given you a brief that in between it will oscillate. Yes, but how it will oscillate? What is the what are the different criteria that I need to keep in my mind, and how, like, what is the variation of this delta? How can I find it out? What is the maximum variation from delta naught to this value? What is this value? How can I find out this value, right? That is what we want to know. Okay, so okay, so let's understand slowly one by one, right? So if I suddenly increase the load here, what will happen? The delta angle, like the speed will increase because the accelerating area, like this is accelerating, right? Because pm1 mechanical input is higher than the electrical power output is still constant. So what will happen? The there is some acceleration, so omega r will increase and delta also will increase. So I can observe the delta is increasing. Here again, what will happen is that after this point B, what will happen? After this point B, your electrical power output will be more than the mechanical power input. Correct? This is my mechanical power input. Electrical power output will be more. And why it will increase? Why delta will increase? Because my speed is higher. Omega r is higher than omega s. At this point B, omega r is higher than omega s. So delta will still increase, right? Still increase. This we have discussed in the first lecture of stability, right? Delta r will still increase here, and it will go increase, and will reach till point C. Again it will reduce, come back here, and then again it will just oscillate. This things we know, this we have discussed already. Now how do I want to understand this variation here? So I know from this point, this is the point A, right, where delta was equals to delta naught, and this point will be what point? So at this initial point, my omega r was equals to omega s, and here what will be my omega r and omega s? Here again omega r will be equals to omega s. Why? Because after this point it starts to deaccelerate. Why? Okay, this is not exactly equals to pm1. This point will not be, like, C point will not be exactly cutting here. It is just for show purpose. Okay, so what happens after this? We have discussed this in the first lecture. What happens after this? So here my speed it is deaccelerating, although the delta is increasing, but the omega r is reducing because the electrical power output is more. So basically, what is the accelerating power? What is PA? So PA, yeah, accelerating power is what? PA is PM minus PE. So in this whole region, PE is greater than PM. PE is greater than PM. So PE is greater than PM. That means it will be negative. If it is negative, that means your omega R will reduce, because this is the accelerating power. If it is negative, that means it is equals to what? D omega upon dt. So d omega upon dt is negative. That means this will reduce. So here omega R was increasing, then omega S. Now here it is reducing till this point. It is reducing till this point, right? Omega R is reducing till this point. It has come up to this point. So here again we reach a stability point, omega R equals to omega S. But again we know that here omega R is equals to omega S, but this is not the stable point, right? Here my PM1 is not equals to PE, right? It is not equals to PE, right? So again it will deaccelerate, because why? It will deaccelerate further. Again your electrical power is more, so omega R will reduce. So if omega reduces, delta also reduces. The angle difference between the stator MMF and the rotor MMF reduces. So this thing is called a swing. This whole thing is called a swing, right? It's called a swing, and this whole, like from this delta naught to delta M, right? This is known as delta M. This will be called as the first swing. Okay. After this, if you observe, the change in delta, right, is always low. So if you see, from it went from delta naught to delta M, then here it is reducing from, like after this it will come here, right? So you will observe one thing you will observe, that this change, right, from delta naught to delta M will always be the highest change. Like during the first swing will have the highest variation. After this the swings will die down due to damping and other factors, right? So the first swing, like what I want to conclude is that the first swing, if the first swing is stable, then the all other swings will be stable. If the first swing is stable, then the rest swings automatically are stable, because the variation in delta will be lower in the upcoming swings, right? So why? Because the variations in delta will be lower. In upcoming swings. Okay, so the thing is that this is a stable system. Like we see that it reaches to delta 1. Delta 1 is this point, right? Finally at steady state it will reach to delta 1. It will reach to delta 1 at steady state, that we know. Okay, but before that it will have some oscillations. So we want to study these oscillations. We have not discussed about these oscillations as of yet. Okay, so if I have a system like this where the delta keeps on increasing, is this a stable system? No, this is a stable system. This is a stable system, right? But this is not a stable system. So first of all, this is definitely not a stable system, because the delta is always keep on increasing. So if after point A, so if due to sudden disturbance the delta keeps on increasing or keeps on reducing, that means definitely it is not stable, it is unstable, right? But here what do you observe, that yes, delta is changing, there is swing, but after a few cycles the swing has been reduced and it is reaching steady state. Okay, so now we want to analyze the swing equation. So at steady state what is happening? At steady state there is no change of delta with respect to time, so d delta upon dt will be 0. At steady state d delta upon dt will be simply 0. Okay, now let us analyze the swing equation further. This is my swing equation, right? This is my swing equation. So if I want to analyze this, so I know my PA analysis of swing equation. So PA equals to Pm minus Pe equals to M d square delta of T by dt whole square. Okay, this we know already. So what I can do, I can write what is my d square delta of T by dt whole square. It is equals to Pa divided by M. Okay, now I will do a bit of manipulation. I will multiply 2 into d delta by dt. Why am I multiplying? I will just explain in a second. So this will be 2 into d delta upon dt into Pa by M. Okay, now sorry, I forgot to write, so I'm multiplying it. This will be remaining here, right? Now a very important fact, right, to understand is that what is the differentiation of d delta, or what is the differentiation of f of t whole square? Can you tell me? It is equals to 2f into f dash of t, or df of t divided by dt, correct? So using that relation, what is the differentiation of d delta of t upon dt whole square? Okay, what is the differentiation of this? So this will be equals to this, right? I am differentiating this. This will be equals to 2 into d 2 into f, right? 2 into f, inside function. What is the inside function? Okay, this is d delta upon dt2. What is the inside function? Inside function is this. So differentiation of this, what is the, no, is it, sorry, it is simply I am differentiating this. So first of all, I will differentiate the outside function. If I differentiate the outside function, it will be d delta of t upon dt. Then I will differentiate the inside function, which is d square delta of t upon dt whole square. So first of all, I differentiated the outside function x whole square, that is 2x, right? Then I differentiated the inside function, that is d square delta of t upon dt whole square. Okay, d square delta of t upon dt whole square. Okay, so do you observe something? This is present actually here. So this value is actually equals to this differentiation of d delta of t upon dt whole square. So what I can write here is that this I can replace, right? This will be replaced with this value, d of dt d delta upon dt whole square, right, equals to, the right hand side will be same only, this Pa accelerating power by m into d delta of dt. So what we can do, we can cancel the dt out, right, and I can integrate now, because I want to see what is the variation. I want to see what is the variation, because remember your Pa is also changing, it is a function of time. Pa is a function of time, m is constant, 2 is constant. Okay, so I want to see the variation of delta, right? So we can differentiate on both sides. So if I differentiate on both sides, what will I get? Sorry, not differentiate, I will integrate on both sides, right? So if I integrate on both sides, so like if I have dx over here, right, d of f of x, and here I have something, right, P d delta, right? If I integrate both sides, what will happen? This will become simply f of x, right? Correct? If I hope you are not mistaken. So here I have d of d delta whole square. So if I integrate this, this will simply become d of delta of t whole square equals to 2 PA by m. Okay, into d delta. I'm integrating this, right? I'm simply integrating this. So let's say I will go like, what is the variation? I want to see what is the variation. So this will be equals to what? This will be equals to, like, I'm starting from what point? What are the starting points and ending point? I'm definitely starting from delta naught. Definitely I'm starting from delta naught, that is for sure, right? We're starting from delta naught. At this point we're starting. And where I am ending. So where is d delta upon dt 0? When is d delta upon dt 0? When there is no variation between the stator mmf and the rotor mmf. When is it? When there is no variation? When my omega r is equals to omega s. When my omega r is equals to omega s, and I just want to measure the first swing. I want to measure the first swing, right? This is the first swing. First swing, right? I want to measure the limits for first swing because I want to only analyze for the first swing. I don't want to analyze for the next swings because after that it will anyways be stable. After that it will anyways be stable, right? So here I will provide a point at point C. Let's assume that the maximum value of my delta is delta m, right? It reaches the maximum value delta m, right? So it will go till delta m. Now this is actually the equation uh, like that we want to understand, but here one very important criteria we want to see. What is the criteria is that I have told you that if omega r is equals to omega s, there is no variation of delta. If there is no variation of delta, that means your d delta upon dt will be 0, right? If you see here as well, when the system has reached steady state, we know your d delta upon dt will be 0, right? At this point, what is the d delta upon dt? 0. At this point, what is the d delta upon dt? At this point, exact point, what is the d delta upon dt? D 0. At this exact point, what is the d delta upon dt? 0. It is a maxima, right? It is point of maxima. So d delta upon dt at this point is 0. At point C, it is 0. At point C, the d delta upon dt is 0. So I can write it, right? I can make it, I can equate it equals to 0. This will be 0. At point C, after I reach point delta m, the d delta upon dt becomes 0. So I get a very important relation that, like, all these are constant. This 2m is a constant, right? So integration of PA, if I start from delta naught to delta m, d delta has to be equals to 0. Now this has many conclusions, right? Many hidden conclusions, okay? And this is actually called as the equal area criterion. This is called as the equal area criterion, okay? Now, what do I mean by equal area criterion? So we know what is your PA equals to. PA is equals to like, there are, I can break this PA in 2 points, two parts. How? So if I copy the graph here, right, I see what is PA between point A to B. Between point A to B, what is PA? Between point A to B, it is always greater than 0 because your PM1 is always greater than PE0, right? Or P, because your PM is greater than PE. Okay. Now, what about other points? What about B and C? In between B to C, what I am observing, my electrical, like this is the electrical power, right, is higher than the mechanical input. So of course PA will be negative. And if PA is negative, like what do you mean by PA positive? That means basically omega R will increase, because PA is proportional to d omega upon dt. So it is accelerating. Basically alpha is positive, right? Alpha is positive, that means it is accelerating. Accelerating. Right? And here I know PA negative, meaning PM is less than PM is less than PE. That means your omega R will reduce. Okay, your omega R will reduce. So if your omega R reduces, alpha is negative, that means it is deaccelerating. For a system to be stable, right, this has to satisfy for the for stability, it has to be equal to 0. So if I break this down, break this area into two parts, so I'm integrating PA. So I observe during the positive half it is always positive, during the from B to C it is always negative, right? So what is the area? Area also will be something positive, right? I'm integrating, let's assume this is the delta 1, I'm integrating PA, right? This graph I'm integrating, correct? So I'm integrating from delta naught to delta 1. Integrating delta naught to delta 1 PA. D delta. That is some area. This area is what? This area actually is called as accelerating area. Accelerating area. Okay, the magnitude, because in the next case it will come out to be negative. So I don't want you to get confused. Called as deaccelerating area. And the other part from B to C, right, actually PA is negative, so actually the area is negative, right? So if I take out the magnitude, right, delta naught into delta 1 PA d delta, this is actually called as deaccelerating area. Okay, here I have already written it. This is actually called as deaccelerating area, which is actually negative, right? It is actually negative. PA is negative, correct? Now equal area criterion, in other words also I can write, right? This will be what? This I can write like this, I can break down. So your this, right, delta naught delta 1 into PA d delta, which is already positive, right, minus delta 1 delta naught delta m, or let me write this as delta C only, otherwise there will be some confusion. I will explain you what is delta m. Later I will just explain in a second what is delta m, right? Give me 1 second, I will later explain what is delta m. For now just understand it is just delta c. For now it is just delta c. Okay, some point at point c the value of delta is delta c, and this is delta b. Let me write according to proper namings. Delta b, let me write this as delta b. Okay, so this will be delta okay, this will be delta b. So let me write this as delta b only. Let me write this as delta b. Okay, delta, this is delta b, delta c. So this will be PA. Why is this negative? Because I know it is PA is negative. I am taking the mod. So I know that what is the area minus 2 dt 0 to 2. It is minus 4, right? But what I am doing, I am taking the mod of the inside function, right? I am taking the mod and adding the negative sign outside. So what I am doing, taking the mod of minus 2 is what? Simply 2 dt. Taking the mod of this, right? Then adding the negative sign inside. So are these things same or not? 0 to 2. Okay, I'm running out of space. So what do I mean by this is like let me take another page. So here, right, I have this 2 angle dt, okay, minus 2 angle dt 0 to t. Is it same as this? Let me know. Is it, let me do it 2 minus 2 dt, is it same? Okay, let me know. I think it is same, right? I guess you are able to understand it is same. So here also, that's why I'm taking the negative sign here. Minus PA d delta equal to 0. So from this very important conclusion I get, right? From this very important conclusion I get, what is the conclusion? The conclusion is, what is this? What is this value? This value is actually the accelerating area. Area cannot be negative, right? Like it's a physical parameter. Physical area cannot be negative. If in the graph, yes, it can be negative, but if physical area cannot be negative, and this is, again, this is the deaccelerating area. This is the accelerating area. This is the deaccelerating area. So from here I can say my accelerating area is equals to deaccelerating area. So this is also another way to explain the equal area criterion. That's why it is called equal area, because both sides will have equal area. During the acceleration, the area, and the deacceleration, the area. So graphically, if I want to show you, I can show you, right? Graphically, if I want to show you, so what will be the accelerating area? So I have changed my PM naught. PM1 is here, right? P is still here. So difference is this much. So this is actually the accelerating area. Okay, and what is the deaccelerating area? What is the deaccelerating area? So the deaccelerating area will be this, right? This, where my PE will be greater than PM. So this much area is the not this, right? This whole thing, right? This whole thing. Okay, this whole thing will be my deaccelerating area, and this whole thing will be my accelerating area. And this is actually, we say it as, okay, let me use different color, otherwise you will be confused. Let me use here red color, right? It is deaccelerating. Okay, so this is known as A deaccelerating, and this is known as A accelerating. Okay, this is known as A accelerating, it is known as A deaccelerating. Okay, so I hope you have understood this point, right? So I hope it is clear. I hope it is clear, right? So this is also another way to, like, graphically I can explain what is the equal area criterion. Equation wise I can explain this accelerating area will be equals to deaccelerating area, or your what you can say directly, this equation also explains the equal area criterion. This we just, what do you do, we just uh, analyze the first swing. We just analyze the first swing. So this is the first swing, right? This is the first swing. In the first swing we're able to stabilize the system. If the system is stable in the first swing, then we don't need to check for the other swings. The other swings will be lower actually, this, right? It will not come down this low. Actually graphically it is shown wrong. It will not come down this low. The swing will be somewhat lower. Okay, swing will be much lower than this. Now who defines delta C? Who defines delta C? So there are two things. Delta C either will be given to you, right? The maximum point, right? Either it will be given to you in the question, or you have to find it out, right? You have to find it out. So first thing first, when is the system stable and when is the system unstable? Let us discuss that first, then I will discuss about the delta M and delta C. So what do we observe? If my accelerating area is greater than deaccelerating area, what will happen? So I can analyze this in a different manner as well. How can I analyze this? So I know this thing, that between these 2 points, right, point A to point B, point A to point C, what is the kinetic energy difference? So what was the initial kinetic energy in the system? Initial K initial was half omega r whole square into J, right, where omega r was equals to omega s, or I can write omega m at point A, right? Initial kinetic energy, and final kinetic energy here at this point, K final was equals to half omega m c square into J, right? It is just half mb square, right? Half mb square in linear motion, but in like rotational motion, your m becomes J and your v becomes omega. That's it. Okay. Now the important thing is that I know that for the system to be stable, there should not be any change in energy stored in the motor. Whatever extra additional, like whatever additional energy I gave, when I increase the input power PM1, suddenly that totally should go to the load, not stored in the motor. So delta Ke should be 0 if system is stable. Why? Because when it was accelerating, the kinetic energy of the, sorry, not the motor, when it was accelerating, the kinetic energy of the generator was increasing, right? So kinetic energy of generator was increasing, right? And whatever additional kinetic energy there was, that again was getting transferred to the load, right? Then kinetic energy of the generator here was reducing, and that was getting to load. So whatever additional energy I gave to the system, to the generator, that should go to the load, right? Then only my system is stable, right? Otherwise additional energy will be there in the generator, and my generator will always keep on oscillating. Not oscillating, sorry, the delta angle will always keep on increasing, right? Because the speed will be higher, right? Omega r will be greater than omega s. So delta Ke has to be 0. If delta Ke has to be 0, then that means this, right, has to be 0. And we know, right, at point A the speed is omega s, at point C also the speed is omega s, so this is 0. That is fine. But what if I am not able to stabilize the system? Okay, what if I am not able to stabilize the system? What do I mean by not stabilizing? So what if that my accelerating area is higher than the accelerating area? What will happen then? So I know during acceleration the kinetic energy increases. So if the increase in kinetic energy, if increase in kinetic energy of motor is higher then decrease in kinetic energy of motor, then we know additional energy is stored in the system. So my delta will keep on increasing. Okay, so that reflects that the system is unstable. That reflects that the system is unstable. Okay, so that basically means there is more increase. That means the accelerating area is higher than the deaccelerating area. So if the accelerating area is higher than deaccelerating area, then what will happen? Then basically the thing that will happen is that the system will not be stable. System will be unstable. Can I take a analogy here? So let's say I have a car. Right? I have a car here, very simple car. Right? And you are driving the car, right? You are there inside and you are driving the car basically. So let's say there are two people who are driving two different cars. Okay, this is you, right? Let's say you are Anish, right? And this is, let's say, Himanshu, right? So one guy here, like what I do, I am like very over smart. Okay, so I drive the car. I press the acceleration button like for a longer period of time, right? So initially the both of them were speeds at 0. Then I press the acceleration paddle, right, for a longer period of time. Let's say for 4 seconds, right? Then the speed increased to 100 meter per second. Okay, and here I have a wall, right? This is a wall. Now if the speed increased to 100 meter per second, acceleration is constant. A is constant, but I am accelerating for a longer period of time. So the speed increased here higher. Here the speed increased to, let's say, 50 meter per second. Now both of them, who will move more closer towards the wall? I will move more closer towards the wall. Now I have to put the brake, right? Because I cannot crash the wall, right? I have to put the brake. So even if I put the full strength of brake, will I be able to like skip this accident? No, right? Because I have accelerated so much during my time, I mean for so longer of duration, the acceleration duration was so longer that even if I put the brake at full speed, I will crash. But Himanshu, he was actually smart, not over smart. So he accelerated for, let's say, only 1 second. So his speed increased, or not say, let's say not 1 second, 2 seconds, right? So his speed increased only 50 meters per second, and he did not move much further. So I can also calculate the distance, right? What is distance? S equals to half AT square, right? Initially the distance was 0, half AT square. So it will be half. Let's assume that acceleration is, velocity become 10, right? Acceleration is 20. So 20 into 4 square, that is 60, right? So it is 20 into 8, that is 160. And this Himanshu, how much did he move? So he moved, this is my distance move, this is his distance move, right? That is half into a, like both of them acceleration is same, right? 20 meter per second square, but time duration is 2, right? So actually it should not be 50, it should be 40. Sorry, this should be 25, sorry. 25 into 8 is 200. Okay, so 200 meter only, and this will be 50 only. So 50. Okay, so this will be 25 into 4, so this will be 50 meter. So Himanshu only moved 50 meter, and let's say initially the distance between here and here was 300 meter, right? And my braking speed is also what is my braking speed? Same, minus 25 meter, right? So already I have crossed 200 meter, right? I've already crossed 200 meter, only 100 meter is left, right? And I have some velocity as well. Right? So here the assumption was initial velocity was 0, right? But now I have some velocity. So how will I calculate the distance? Do you remember the formula? I have forgotten the formula. It was v square minus u square minus 2as, right? So if you remember, there was one formula, v square minus u square equals to 2as. Okay. So here I know my acceleration. So I want to find out initial velocity is 100 meter per second, right? My car reached 100 meter per second. Fine. I want to see when I will be at rest, right? Because before reaching this wall, my car should be stationary, right? So acceleration is minus 25. So v final minus v initial, that is u square, sorry, v square final velocity is 0 whole square, because my car wants to be stationary. Initial is 100 whole square, and acceleration is what? Minus 25, it is retardation, right, into s. Okay, so from here I will be able to calculate what is the distance that it will travel, what is the distance that a car will travel before it comes to rest. What is the distance the car will travel before it comes to rest, right? I have covered 200 meters, 100 meters are left. Okay, so s will be equals to, like, we are studying physics, right? We are studying physics. I kind of love physics as well. So s is equals to, this will be 50, so 102 into 100, so 200 meter. So it's like a symmetric situation. So after 200 meter my car will come to rest. But how much distance I have? I have already covered 200 meters, and total distance is 300 meters, right? So I have only 100 meters distance left before the wall, I will encounter the wall. But you are telling me if the braking retardation is minus 25, then after 200 meters my car will come to stop. So we are too late. Right? We should not have accelerated till 4 seconds. We should have accelerated till only 2 seconds. Then everything would have been symmetric. Right? Or whatever the value is, I am not calculating. But Himanshu was smart, right? He will not crash. Why? Because how much has he traveled? He has traveled 50 meters, right? So how much distance is left? Still we have 250 meters of distance left, right? So again, if I calculate the same thing, how much will his car travel? What is his velocity? 50. So 50, 0 final velocity minus initial velocity equals to 2 into retardation into distance. So s will be equals to what? S will be equals to 50, right? It will only travel 50 meters. So still I have 200 meters of headroom left before I will encounter the wall. So something similar is here, right? So if I am accelerating so much for a longer duration, then the system will go unstable. Basically it will crash, right? So we should stop. Is this a problem? Right? We are not accelerating for longer duration. No, our life is still safe, right? Yes, there is some distance, like you are exactly not stopping at this wall, right? But you are stopping much before that, but that is fine. Our life is more important, right? So same is here, that accelerating area is higher than the accelerating area, system will be unstable, right? But if your accelerating area is equals to deaccelerating area, then system will be stable. Or if it is less than, then also it will be stable, because it is fine. Our life is more important, right? So the thing is, the conclusion is, if our accelerating area is less than or equal to deaccelerating area like is if it is less, it is stable, right? System is stable, and when both of them are equal, right, that is the critical condition, right, after which, just after which system becomes unstable. So that is also very important. When both of them are equal, right, this is the critical condition, because after this condition, right, system will go to instability, system will become unstable. Okay, very important point to understand, right? Okay, so I hope you have understood this point. So same thing is written over here. For quickly assisting assessment of the transient stability, we use the equal area criterion. Now before starting, one more point I want to say. What is the maximum value of this delta c? What is the maximum value of this delta c, right? So maximum value of delta c, if generally in the question it will be given that if, like, there are two cases, delta c, right, it will be given in the question, or it is not given. If delta c is not given, then how will you find out? So if delta c is not given, you will choose the maximum value, you will choose the maximum deaccelerating area, right? So if not given, choose the maximum value of delta c, after which, till which it remains stable. So basically you will be choosing the maximum deaccelerating area, because accelerating, I will be choosing the maximum deaccelerating area. Okay, choosing the maximum deaccelerating area. Now how to choose this? So for this I have to again come back to graph. So in the previous lecture we talked about stability, right? We talked about stability. So one thing is for sure, if my point is somewhere here, will it be stable? No, because this point is gone, right? Now my mechanical input is not this anymore, this is my mechanical input, right? After this I have told you, because if slightly delta increases, it will just keep on increasing, right? It will just keep on increasing. But here also, if slightly there is delta increase, it will keep on increasing, correct? But at this point, this is the maximum point of stability, right, after which it cuts the, like, this cuts the mechanical power, like the load line and the electrical power, both of them intersect each other at this point. After this my load line never intersects, right? So we will never get a operating point after this. Okay, so the maximum value of delta at which the electrical power and mechanical power intercept with each other. Okay, so the thing is, what is this point then? What is this maximum point? So actually it is equals to pm equals to p. What is p? P is equals to p max. So let me write this as p max, right? P max. P max sine delta, correct? So your delta will be equals to sine inverse delta will be equals to sine inverse p max upon p max. Okay, there is another solution as well, or it is pi minus p max upon p max, right? So this is the maximum value of delta m. So this is my delta m actually. After this, it will never come back to stability. Okay, so that's how you find out delta m, right? If you have the confusion about regarding delta m, that's how you will find out delta m. Generally delta m will be given, otherwise that's how you will find out. Like if it is not given, then this will be your delta m. Okay, with the help of this delta m, we'll be able to find out the critical clearing angle. With the help of this delta m, we'll be able to find out the critical clearing angle. Okay, now the thing is, okay, yeah, so if this integration, so another conclusion I can say, if accelerating area is greater than deaccelerating area, that means my integration of 0, no, not of 0, delta naught to delta c, right? Or delta naught to delta c. This is delta naught, right? Yeah, delta naught to delta c pa d delta. If it is positive, that means system is unstable. There is more acceleration, right? That's why it is positive. If it is negative, right, system is stable. Right, and from here I found out the critical value of delta m, right? At maximum, this is the maximum where at which my delta m can go. After this, my delta m cannot go beyond this. My delta m cannot go beyond this. So basically what I am trying to say is, this is the maximum deaccelerating area that I can calculate. This is the maximum deaccelerating area that I can that I can provide. So I'm choosing delta m to find out the maximum. So delta m, I'm choosing deliberately the maximum value of delta, right? So if your delta c is delta m, it will provide the maximum deaccelerating area. Okay, it will provide maximum deaccelerating area. If my delta c is equal to delta m, then it will provide me the maximum deaccelerating area. Then what can I say? What can I say? I can say that this is the maximum deaccelerating area, right, that I can provide. So this I will equate with the accelerating area. So if with the help of maximum deaccelerating area, still my integration, right, is coming out to be positive, right? That means system will always be unstable. I cannot do anything. I cannot do anything. System will always be unstable. So how to like make the system stability? So we have to actually have a condition that I will find out in the next few slides. Okay, don't worry. So just understand this: when my delta c is equals to delta m, that is the maximum possible deaccelerating area, because if my delta c is increasing, then this area is increasing, right? So that's why if I go beyond this, system will anyways be stable, right? So that's why this is the maximum possible deaccelerating area that I can provide. Okay, so this will be helpful while deriving the critical clearing angle. Okay, so this is the equal area criterion. Basically, the theory is given that accelerating area will be equals to deaccelerating area. What happens if the deaccelerating area is insufficient? That is, if the accelerating area is more, then the system will go unstable. Okay, so let's solve a few questions. Basically, find the maximum value of mechanical input in per unit for the system to remain stable. For the system to remain stable, what will be the maximum value? Okay, so remember here, right, they have not provided you any delta m. So we have to find out the maximum value of mechanical input PM naught that I can provide, right? Basically, like suddenly the load will change. It currently the graph is this, right? But if I provide a sudden change in mechanical input, right, so it will go to what? Let's say it goes to here, right? I'm providing some mechanical input. Right, I'm providing it some mechanical input. So if I'm providing it some mechanical input, what does it mean? It means that basically suddenly your graph will start, right? It will go here, it will reach here, right? It will reach this point, and then again it will go, right? So how much can I increase this PM1 so that my system still remains stable, right? If my system still remains stable, so this is my accelerating area, and for this accelerating area, how much maximum deaccelerating area can I provide? Because either my deaccelerating area must be greater than accelerating area, or it should be equal, right? So this whole area is deaccelerating area, right? So what is the maximum value that I can go? Already discussed, right? What is the maximum value? This will be pi minus sine inverse PM naught upon P mechanical upon P max. That actually is equals to my, so if this is equals to delta naught, right? If this is equals to my delta naught, then this will be equals to my pi minus delta naught. Okay, so this is equals to my pi minus delta naught. This is my delta naught, correct? So this value will be my pi minus delta naught. So delta naught is 15, so this value will be pi minus delta naught, that is 165. Okay, so this is the maximum possible deaccelerating area that I can provide, right? That can make the system stable. I cannot provide beyond this area. So this is the maximum possible deaccelerating area, right? So now I can solve this. So suddenly the load has increased to PM1. So what is initial PM naught? So delta naught I know. So I have to use the equal area criterion. What is equal area criterion for the system to remain stable? It is PA d delta equals to delta naught to delta m, maximum value, delta C is delta m this time, equals to 0. I have to equate this with 0, right? Equal area criterion I will use, right? So I will break this integration into two parts. I'll break this integration into two parts. During the initial phase, right, this was my area and this is my, I will break this down into two parts. That is, this will be equals to, here what is the value? PM1 is greater than PM2, right? So here basically it is PM1 minus P max sine delta, right? It is PE, right? PA is P max sine delta. It is going from delta naught, that is 15 degrees, to I don't know what is this value. I don't know what is this value, right? I don't know, this is delta 1. Okay, this plus it will go from delta 1 to 165 degrees. Again, this is what, this time my this graph is higher, right? This one is higher actually. So this is higher than this one, right? So I can write this area as this. This is the accelerating area, right? I'm just writing the area, so I'm writing just the positive terms. So now PE is higher than PM, so I will write PE first, then PM, right? Or you can directly solve this one integration also, that also is fine. Okay, either way is fine. If either, like, I will solve using both ways. First I will solve normal way. First I will write this, what is PA? PA is PM minus PE into D delta, right? Into D delta, and delta M is 165 degrees, right? This is my delta M, correct? Delta M is 165 degrees. So what is my PM1? Do I know what is my PM1? Kind of, yes. No, I have to find out PM1, right? I have to find out PM1. Okay. So I can break this. This has to be equal to 0, correct? This has to be equal to 0. So I can write this will be PM1 into 165 degree minus 15 degree. I have to write this in radian, so pi divided by 180 degree, right, equals to, here it is P max. P max is given, right? Maximum P max is 500 megawatts. So 500 integration of sine delta. What is integration of sine delta? It is minus of cos delta. Integration of sine delta is minus of cos delta, correct? So this will be minus of cos delta, and cos angle is going from 15 degree to 165 degree. Okay, so this will be equals to, so from here I can directly find out what is my PM1, right? PM1 will be, so this value it is 15, hold on a second, 150 into pi divided by 180. So this is actually 2.618, right, into 500. Minus sign can come outside, right? Minus sign can come outside. It is cos 165 minus cos of 15 and negative if I multiply, so this will become plus into 1.932. so this value, if I calculate this value from here, I can easily find out what is my maximum mechanical input that I can give, right? So this will be divided by 2.618 into 500. So maximum PM1 that I can provide is 369 megawatt. So suddenly, all of a sudden, I can get my mechanical input to 369 megawatt. Okay. So what was the initial PM naught? Initial PM naught. So initial PM naught will be what? It will be basically P max. Like initially, mechanical input and the electrical output were same. So it is simply P max sine of delta naught, right? So this value will be equals to P max is 500 megawatt into sine of delta naught, sine of delta, sine of 15, right? So 500 into sine of 15, so 129. So this actually comes out to be 129.4 megawatt. So initially I was giving some 129.4 megawatt. Suddenly if I increase my mechanical input to 369, this is the maximum possible sudden increase that I can provide to the system. After this, the system will go out of stability. Okay, after this, the system will go out of stability. Okay, sorry. Sorry. This, right? This will not be actually 165. One mistake I have made. Actually, this angle will be much lower, right? This is not 165 because this angle is different. Okay, sorry. Yeah, that's my bad. Because delta M, your delta M will change, right? Oh no, this is the maximum decelerating area, right, for which the system will remain stable. So is this correct? Actually, there is one huge conceptual mistake here, right? Huge conceptual mistake. So I told you that delta m, right, maximum delta m will be basically this delta naught pi minus delta naught, right? Actually it is wrong here, right? If I've told you that delta m is equals to pi minus, no, this is wrong. This is wrong. Okay. So your operating points are actually delta 1 because your mechanical load has changed to 1, not 0. So this will be delta 1 and this will be pi minus delta 1. Okay, new operating point because the operating point has changed now. The operating point has changed now. So if the operating point has changed now, so this actually can be crammed into one page only. We don't need two pages for this. We have already discussed about this, right? Let me copy this diagram. Yeah, this one. So if the operating point has changed, so will delta 1 also will be changed. This is not correct, right? So this is the point of this one actually. This 165.1 is actually with respect to this one, right? But I have to find out this one. What is this? This is actually pi minus delta 1. Okay, so your equation will be, it will start off from delta naught, okay, and this will be pi minus delta 1. So it will start off from delta naught, right? Start off from delta naught and this will be pi minus delta 1, right? And I will integrate PA d delta. That should be equal to 0. Now it is not that easy to calculate. Why, I will just explain in a second. So this will be like PA is what? PM1 minus P max sine of delta, right? Integration of delta naught pi minus delta 1 into d delta equal to 0. So I can write this as, this will be PM1 into, like this is in radians, right? So pi minus, everything is in radians, so pi minus delta 1 minus delta naught equals to, here P max, this will be minus cos of delta naught to pi minus delta 1. Okay, so what is this value actually? So what is cos of delta naught? I already know. What is cos of 180 minus theta, right? 180 minus theta. What is cos of 180 minus theta? I also have forgotten. What is cos of 180 minus theta? So okay, so my cos theta is something like this, right? So let's say this is my cos theta, let's say this is my 30 degree, right? So I have to find out cos of 180 minus 30, that is cos of 150. What is cos of 150? Cos of 150 will be somewhere here, just before this 180, right? So it will be actually root 3 by 2 minus root 3 by 2. So it will be minus of cos delta 1. I will just quickly confirm, right? I also have forgotten everything. So cos of 30 is root 3 by 2 and cos of 150 will be minus, yeah, minus root 3 by 2. So this is actually minus of cos of delta 1. Okay, minus of cos of delta 1, and already there is a negative sign here. Already there is a negative sign here over here, right? So let me bring the negative sign outside, otherwise you will get confused. So this will become minus P max into, like, cos of pi minus delta 1 minus cos of delta naught, right? Cos of pi minus delta 1 minus cos of delta naught, correct? So this will be equals to what? This will be minus of P max into cos of pi minus delta 1 is basically minus of cos delta 1. So minus sign will come outside and already a negative sign is there. So if I take the minus sign common, this will become plus. This will be cos of delta 1 plus cos of delta naught. Okay. So I have to actually find out what is cos of delta 1. How will I find out what is cos of delta 1? That will be difficult actually. You will not be able to find out cos of delta 1. I will explain why you will not be able to find it out. So this can be broken down. I'm not like simplifying the left hand side version. I'm just simplifying the right hand side version. This can be broken down into P max cos of delta 1 plus P max cos of delta naught. Okay. So what we know is, I know what is my sine delta naught, right? I know delta naught 15 degrees. P max I know 500. So I will be able to find out P max cos of delta, right? Cos of delta naught. So that will be equals to 15 cos into 500. So it comes out to be 482.96. So this comes out to be 482.96 megawatt, right? This value. But what about this value? How will I be able to find it out? Actually, you will not be able to find it out. One thing I know for certain, that my PM1 sine of delta 1, sorry, P max, PM1 will be equals to what? At steady state, right? This is a stable point where my this graph and this graph is intersecting. So it is P max sine delta. This will be equals to PM1. So this value, right? PM1 will be equals to P max of sine of delta 1, P max of sine of delta 1, right? So will I be able to, I don't know what is my PM1, I don't know what is my delta 1, right? How will I calculate? Okay, so what I can do, I can put my P max here. So sine delta 1 is equals to PM1 by P max. So can you tell me what will be my cos delta 1? Cos delta 1. So cos delta 1 will be equals to P max whole square minus PM1 whole square whole under root divided by P max, right? This will be my cos delta 1. Okay, so that I will actually, that I can put here, right? So it is basically equals to, so it is like what I'm doing, P max into cos delta 1. So P max will get cancelled. So it will be P max whole square, that is 500 whole square. Okay, 500 whole square minus this PM1 whole square, right? Whole under root, and on the other side I have this PM1, right? This is my, okay, I have PM1 into this value. So this actually becomes a non-linear equation. You will not be able to solve it, right? This is PM1 into pi minus delta 1 and minus delta naught. This actually becomes a non-linear equation. Okay, so yeah, you will not be able to solve it. But I hope you are able to understand like what do I mean non-linear equation, right? So in gate this question will not be asked, but this is helpful to understand the concept, what is happening. So as soon as I change the mechanical input, right, so the maximum deaccelerating area that I can provide is pi minus delta 1, right? This is the maximum point at which the system will be stable. After this, system will not remain stable. Okay, so yeah, that is the equation. Basically I should have asked you the find out the expression, of maximum value of mechanical input power for the system to be stable. Okay, right, that is my fault. The question, I have rephrased the question. Okay, this will be Yeah, this is correct. Okay. So now let's solve, let's understand, if we have a certain short circuit at the generator terminals, when shall I clear the angle? When shall I clear the when shall I clear the fault, right? So that the system can become stable, so that the generator can again remain stable. Okay, slowly I will explain. Slowly, don't worry, I will explain slowly. So if some fault happens at the terminals of the generator, what happens? The PE goes to zero, right? If some fault happens at the terminals of the generator, we know it's a low power factor low power phenomena, so your PE will go to zero. Your PE will go to zero, correct? So if your PE goes to zero, what will happen? If your PE goes to zero, then where will I lie in this graph? Where will I lie in this graph? So initially my point was here, right? I was at the stable operating point. If suddenly my PE goes to zero, the delta, right? Uh, Delta will not go to zero instantaneously, right? Delta will not go. So if P goes to zero, that means delta has to go to zero, right? Delta has to be zero because I have some terminal voltage, I have some reactance. These cannot be, like, this cannot go to zero. This has to go to zero. But delta will not go to zero instantly. Delta will not go to zero instantly. So what will actually happen? What will happen? I will start from point A and then I will go to point B, right? What is the point B here? Point B will be here, right? Just after the fault has happened, suddenly, like, PE was following this graph, right? This was my PE graph, but now just after fault, the electrical power will totally go to zero because it is not consuming any power, but delta will still be delta naught. So delta will still be delta naught. Just after the fault, delta will still be delta naught, right? So I will be lying at this point B where my delta is delta naught, okay, and my electrical power is zero, okay. And slowly what will happen? Delta will increase. Why delta will increase? Why delta will increase? Because what is the accelerating power here? What is the accelerating power of the machine? Yes, I know, it wants to go to, it has to, either delta has to go to zero, either delta has to go to 0 or 180. Why 180? Because we know that sine of 180 is also 0. So either it will try to either go to this side or this side, right? So we know that what is the accelerating power here? I am providing some mechanical input, so accelerating power is still 0, so motor will accelerate, so delta will increase, right? So delta will increase, so I will move along this point, delta will increase. It will increase, and let's say it increases till this point C, okay? After this, what happens? I suddenly clear the fault. After this, the fault is cleared, right? If after this the fault is cleared, then what will happen? Then at point C, right? At point C, fault is cleared. Now, if at point C fault is cleared, that means my PE is not equal to 0 anymore. Again, the the line is normal. So line is normal, so PE is not equal to 0 anymore because fault has been cleared, right? Fault has been cleared. What is the PE? PE will be, again, it will follow the whatever power it is taking at that point of time. What is the load angle? Load angle is this, right? So PE will again follow this curve, right? It will be EF Vt by X sine delta. So suddenly the power will jump to this point here. We'll touch the graph again. And during this, from A to C, what was happening during this A to C? What was happening during A to C? During A to C, your electrical power was 0 and your electrical power was 0, correct? Your electrical power was 0, right? And you have your mechanical power. mechanical power is still there, it is not 0. So your accelerating power is greater than 0. So during from A to B, omega r was increasing. Omega r is always greater than omega s. So if I am at this point, at C point, not B, sorry, at C point, omega r is greater than omega s. So here the rotor speed is greater than stator speed. So still the rotor angle will still increase. Although I will follow the graph now, but still the rotor angle will increase, right? Because omega r is greater than omega s. But after point D, what will happen? After point D, if you observe that this is my mechanical input and this is my electrical power output. So electrical power output is greater than mechanical input. So after D, let's assume that it goes till this point E. So from D to E, right? From D to E, what do I notice? From D to E, it will at max it can go this point. At max it can go till this point, right? Why this point? Because this is the last operating point where the load angle, mechanical input and the electrical power output intersect. So this is the maximum value, right? This is the maximum value. Again, this will be used. This will be very, very helpful. Okay. So this is the maximum value that we can reach to, right? So till point from D to E, what will happen? Till from D to E, I know my mechanical, like always the electrical power output is always greater than the mechanical. So my mechanical Pmech is always less than Pe, right? Pmech is always less than Pe, right? So my accelerating power will always be less than 0. Accelerating power will always be less than 0. So here omega r will reduce, but still omega r is greater than omega s. At point E, what will happen? That is the last operating point where omega r will be equals to omega s, right? But still delta will increase because omega r is greater than omega s. That is for certain, because omega, like here, right? Let's say initially this was the speed, let's say 1500 rpm. So here speed is increasing, let's say to 2500 rpm. So here the speed is 2500 rpm. But here, yes, accelerating power is negative, so omega r will reduce 2200 rpm, 2100 rpm, but still it is greater than omega s. Omega s is 1500 rpm. So that's why delta will still keep on increasing. Delta will still keep on increasing till this point. So this is the maximum value which I can go. After this, beyond this, I will not be able to go. Beyond this value, I will not be able to go, right? Beyond this, I will not be able to go. You're correct, right? Beyond this, I will not be able to go. Maximum value. So what is the deaccelerating area here? So deaccelerating area is this one, right? If I copy this graph, maximum deaccelerating area. So this will be my, like normally, ideally, what would I want? If let's say if the fault was cleared much earlier, right? If the fault was cleared much earlier, then the operating point E will be somewhere here. Okay. If let me write this point as EM. If fault was cleared earlier, if fault is clear earlier, right, what will happen? If fault is clear earlier, then this C point will be on the left hand side, correct? What is my accelerating area? This is my accelerating area, right? So C point will shift to C dash. Let me mark this point as C dash, right? Okay. So let me highlight this point. So C point will shift to C dash. C point will shift to C dash, okay, and I know that my so what will happen if C point shift to C dash? What will be the difference? The difference will be that the area will increase. So this is what this is the A accelerating, right? Accelerating area. So if C point shifts to C dash, all this will go backwards here. Okay, let me make it even more backwards. It will be somewhere here. Right? So what do you observe here? The observation is that my area, if you see, if you notice, right, the height is same, right? Height is same. So the area reduces. So the accelerating area reduces. Hence, the critical condition for stability is what? The accelerating area must be less than the deaccelerating area. So I have more headroom, right? This is the maximum value that I can go, but all of this is my deaccelerating area. But maybe I don't need this, I don't need to go till this point. Only this point is enough, right? So what happens? So we do the requirement sorry for the noise, actually the requirement of deaccelerating area reduces, right? So basically to satisfy equal area criterion, that basically means that for the system to be stable. Now what if the fault was cleared later? If the fault was cleared later, if the fault, I'm sorry for the noise, like they're doing some construction work, I don't know. Fault was cleared later, if the fault was cleared later, then what will happen? Then she like this, right? C point shifts, shifts left, right? Because it is cleared much earlier. So like we know that delta increases during the first swing, delta increases, right? Delta is increasing. So if I clear the fault much earlier, so here the C point will shift left. If I clear it later, what will happen? If I clear it later, C point will move to C double dash. C double dash basically means it will shift right. If it shifts right, then what you'll see, the maximum possible deaccelerating area will reduce. So if it shifts right, so now what is the maximum possible deaccelerating area? If I observe, this is my maximum possible deaccelerating area. Let me name this as deaccelerating maximum, because of course fault will be cleared here, but the maximum possible deaccelerating area that I can provide is A dx max, right? Okay, let me keep it here only, let me not add a page. But here what you will observe, that your maximum possible deaccelerating area will reduce. I will show you. So your point will move to C double dash. It will move rightwards because I am clearing the fault later. So delta angle has increased to a larger value. So this will move rightwards, right? This will move somewhere, let's assume somewhere here. It moves somewhere here. Okay. let me cut the 90-degree, moves to somewhere here. So what do you observe? We observe two things, right? This is C double dash. We observe two things, that the accelerating area increases, accelerating area, that is AX, right? AX increases, and your maximum possible deaccelerating area that I can provide actually reduces, right? It reduces. If you see here, I had so much of deaccelerating area, but here it reduced. So your maximum possible deaccelerating area that I can provide has reduced, right? Okay. So system can go to instability. So if I keep on delaying my fault, system can go to instability, right? So your like if I keep delaying the clearance of fault, the system can go to instability. Okay, so that is the thing that you have to understand. System can actually go to instability if I keep on delaying the fault. If I keep on delaying the fault, the system can actually go to instability. Okay, so that's why there will come a critical clearing time, okay, or critical clearing angle, after which I cannot delay it further, right? So there will be a critical clearing angle delta CR at that point, because I know my accelerating area is increasing and deaccelerating area is reducing. Initially I had my accelerating area is very low and deaccelerating area was very high, so system was totally stable. But there will come a point where I will keep on delaying my fault clearance, and the area will keep on increasing, accelerating area will keep on increasing and deaccelerating area will keep on reducing, right? So there will be a critical angle that is known as critical clearing angle. That is the definition of critical clearing angle. At that point my accelerating area will be equals to my maximum deaccelerating area, right? This is the maximum possible deaccelerating area that I can provide. Okay, so the point at which the accelerating area and the deaccelerating area are equal in values, that point is known as the critical clearing angle. Okay, so yeah, I hope it is clear what is known as the critical clearing angle. Okay, so basically this much only we have to understand. I think I have drawn it as well here, right? Okay, I have not drawn it. Okay, yeah. So yeah, that is the definition of critical clearing angle. The critical clearing angle is the maximum rotor angle up to which the rotor can swing during fault, such that after clearing the fault, it can still return to stable condition, right? How it is stable? If the accelerating area and deaccelerating area are equal, then it will return to the stable condition. Otherwise, it will not return to the stable condition. Okay. So this you have to find in question. You have to actually find in question. So what will be your delta M? What will be your delta M? Now it is interesting because you are not changing the mechanical input. As you are not changing the mechanical input, can you tell me what will be the delta M here? As you are not changing the mechanical input and after clearing the fault, the electrical characteristics is also same. So your delta M also will be equals to pi minus delta naught. Now this will be correct because your PM naught and PE are same before and after clearing the fault. During the fault they are different, but before and after clearing the fault they are same. Okay, but remember this can change. This can change. Okay, so your delta M can be either pi minus delta naught if before and after clearing the fault your mechanical input and electrical output remains same. Okay, it can be something else as well, right? Can be something else depending on the question. It can depend on the question as well. Okay, so what you have to do, you simply have to use this formula, right? You simply have to, like, this slide only you have to understand, right? If you want to remember, you can remember this slide. So if I integrate from delta naught to delta M, right, of my accelerating power, remember your accelerating power is actually changing, right? Remember your accelerating power is not same, it keeps on changing. Okay, accelerating power, it is variable, it is not constant. Okay, I'll explain what do I mean by it is not constant. This has to be equal to 0, right? By applying equality criterion, if this value is equal to 0, then your system is stable. So can you tell me, just after fault what is happening? Just after fault what is your PA? Just after fault, right? Just after fault, right? After fault, your PA is equals to what? PM naught, right? Because your PE is 0, right? And your delta value, delta will go from delta naught to delta CR, critical clearing angle, right? Because this is the critical angle after which if I even clear the fault, system will not come to stability. So I want to find out this delta CR. I want to find out this critical clearing angle, right? So during this fault is happening, after delta CR fault has been cleared. So after clearing fault, your PA is what? It is PM naught, mechanical input is still constant, minus P max sine delta, right? Remember your delta is variable, delta is changing, right? Because your PE is changing. So if you see, after fault your PE is suddenly gone to 0, right? So this is your area. Okay, one mistake I have done. This whole thing is not your area. I'm sorry, I'm extremely sorry. Only this much is your area, right? Area is what? Below PM naught, whatever is the below PM naught value. So this is the below PM naught. So this is the area. Okay, I'm sorry, this is the area, right? And here also, yeah, here I have done it correctly. This is the area because it is below PM naught. Here I have made a mistake. This is the area, right? Not this. This much is not the area. It is below PM naught, right? And this is above PM naught. So this much is the area. So how? So basically, what is the after clearing fault? If you see here, right, your delta is varying, right? Delta is changing. I'm moving at this point, so delta is changing, right? So if delta is changing, then what is happening? If delta is changing, I cannot directly write a single expression. It will not be constant. It will be a function of delta. Okay, so I will just draw the direction of flow, right? That will be easier for you to identify in the notes. So direction of flow will be something like this. Right, this will be my direction of flow. Okay, this will be my direction of flow. And this will be my direction of flow. Okay, so after clearing fault, this will be happen. And what is the delta? So delta will go from delta CR to delta max. So this equation, delta naught to delta M, or I can write here pi minus delta naught PA d delta has to be equal to 0. This can be, I can break this integration down into two parts because the definition of the function is changing. So basically it is a discontinuous function. So PA as a function of delta is equals to, it is a discontinuous function. So I have to break this integration down into two parts. So it is equals to PM naught when my delta is less than equals to delta CR, right? And it is equals to PM naught minus P max sine delta when my delta is greater than delta CR, right? So there is discontinuity. So if there is discontinuity, then I have to break this integration down into two parts. That's why you see we break the integration down into two parts. So finally, now if you have understood the concept, because I know there is huge doubt in this whole critical clearing angle whole thing, right? I know there is like huge confusion. I know you have studied from 1000 resource and it is not cleared by, like, I know it is not cleared in your brain. So if it is clear, make sure to hit the like button. If you're enjoying this, please make sure to hit the like button so that I can understand my efforts are going somewhere, right? So yeah, P delta into 0. So this will be actually equals to, I can break this integration down into two parts. So this will be delta naught to delta CR PM naught d delta plus this will be delta CR to pi minus delta naught to PM naught minus, PM naught minus P max sine of delta. This has to be equal to 0. So this is what, this is the basically the accelerating area and this is the deaccelerating area, right? So don't need to remember this equation, no need to remember this equation, just understand the concept, that's it. Just understanding the concept is enough, because equations will not help you. I have seen other educators, they will derive a formula from here and you will remember the formula, but that is actually not good, right? That is actually not good. If you just mug up the formula, they will change something in the circuit, right? And that formula will not work, but this will always work. This is always valid, right? This formula is always valid, no matter what, no condition, always valid, always valid. Okay, so this first definition is always valid actually. For the second part, right, your circuit can change after clearing the fault. Maybe the Pmax has changed, right? So it depends on question. So this depends on question. So just be careful that maybe your Pmax has changed after clearing the fault, right? It is not same as the previous Pmax. It is not same as the previous Pmax. Okay, so just be clear, just be careful regarding that. If it is not if it is not same, right, then things will change here. And we will solve those kind of questions, don't worry, we will solve those kind of questions. Okay, so this is the critical clearing angle, we have already discussed, right? I think, yeah, critical clearing angle already we have discussed. Okay, now what is the critical clearing time? What is the critical clearing time? If I want to find out the critical clearing time, I know my delta of t will be equals to delta naught plus half PA by M T square, right? And during fault, what is the PA? So during fault, right? During fault, I know PA is always equals to PM naught, right? So this equation can be replaced. I can find out the critical clearing time. Delta CR, I know they will give me the delta CR. I will know delta CR. Delta naught plus half PM naught divided by M into TCR whole square, right? So this is the time, critical clearing time before which if I clear the fault, right? So my delta angle will be equals to, like, it will be somewhat lower than the delta CR. If I'm not able to clear before this time, let's say 1 second, delta will increase. So my delta is greater than delta CR. So the deaccelerating area will be less than accelerating area. So system will go unstable. So I have to anyhow clear the fault before this time. If I am not able to clear the fault before this time, then the delta will go higher than delta CR and the system will go unstable. So there are two definitions: critical clearing angle and critical clearing time. Both are interrelated with each other. Okay, both are interrelated with each other. So now let's solve a very basic theoretical question. Okay, very basic theoretical question. So which one of the following statements is correct? Steady state stability limit is greater than the transient stability limit. Okay, what do I mean? So steady state stability limit, what is the steady state stability limit? So here they are talking about transient and stability, right? Steady state, that means they are talking about angle, because transient stability we mainly refer with angle only. So they are discussing about the angle, not about the Pmax. Okay, so I know that the steady state stability limit is delta equals to 90. If I go beyond delta equals to 90, the system will go towards instability. Okay, what will be a critical clearing angle? So your critical clearing angle generally and in most cases you will see actually happening like this is your delta steady state limit, right? Delta steady state limit. Okay, and your delta critical will most cases will always lie in this region. It will never go here, because here the deaccelerating area will be always lower, right? Here the deaccelerating area will always be lower, right? Okay, because your delta naught will start from here. If your delta naught, let's say, starts from here, right, then you have to anyhow clear the fault before this, right? If I don't clear the fault before this, the deaccelerating area will increase. Okay, so generally the steady state stability limit will always be higher than the critical angle. We will solve in questions as well. Okay, and you will see. So the limiting condition is delta CR equals to delta steady state limit. That this is the limiting condition. Right? But generally we'll keep our, like, generally the critical clearing angle you will see always is less than delta steady state limit. So this is actually a ESA question, that's why it's a theoretical question. Okay, so your steady state stability limit is greater than transient stability limit. Yes, option A is correct. Your steady state stability limit will always be greater than the transient stability limit. Okay, so yeah, that's the answer for this question. Like, it's a theoretical one, and don't worry, if you did not understand, we will solve few questions, and through there we will identify like what is our critical clearing angle. Through there you will understand, like, generally our critical clearing angle is less than like steady state stability limit. Okay, so let's solve this question. A synchronous generator initially delivering 1 pu of power. So your pm naught, initial power p naught was equals to 1 pu, which is equals to your pm naught, right? And its steady state stability limit is 2 pu. That means your pmax is 2, right? That is the steady state stability limit. Following a sudden short circuit fault, the maximum rotor swing is observed to be 110 degrees. What do I mean by maximum rotor swing? So initially it was at delta naught, it went to delta max, right? Or delta C or delta max, whatever you want to say. And this difference, delta m minus delta naught, is given to me as 110 degrees. Okay, determine the fault clearing angle, or actually I should have asked, determine the critical fault clearing angle. Critical fault clearing angle. So here also have to change. This will be critical fault clearing angle. Okay. So can I find out delta m from here? What will be my delta m? So what is my delta naught? Delta naught will be simply equals to sine inverse PE naught, that is 1 PU, upon P max, that is 2, right? Because I know that my PE is equals to P max sine delta. Okay, so 1 by 2. So your delta naught comes out to be pi by 6, right? Delta naught comes out to be pi by 6, right? Because sine inverse 0.5 is pi by 6. Yeah, pi by 6. So what will be your like it is equals to 30 degree, right? What will be delta m? Delta m will be basically 140 degrees. Okay, so the question hidden information will be given regarding delta m, right? Either I have told you, either you will by yourself find it out, or in the question delta m will be given. Okay, so now how will I find out the critical clearing angle? So again I will use this formula. So I will use the equal area criterion. If I use the equal area criterion, that it will go from delta naught to delta m, and this integration must be equal to 0, right? D delta must be equals to 0, right? So what can I say over here? I can say that what is my PA? PA before fault, right? Till like after fault, right? During fault, it will go till delta CR and it will be equals to PM naught only, because PE is 0 into D delta. After fault, it will be delta CR to delta M, and this will be PM naught. This will not change, mechanical input is not changing, they have not mentioned it, and this will be P max sine delta, okay, into D delta equal to 0. So now what we can do is, what is your PM naught, right? PM naught, like PM naught I already know, PM naught is equals to PE1, that is 1 PU. So this will be basically delta CR minus delta naught, right? Okay, this will come out to be a non-linear equation. Okay, so you have to solve the non-linear equation, you will not be able to solve it. Okay, some information also must be given, so some other information also must be given, and it will be given, don't worry. Okay, here it is not given, so we will not be able to actually solve this. We will not be able to solve this non-linear equation. Will you be able to? No, we will not be able to solve it. So delta CR into PM naught. PM naught is 1 PU into pi divided by 180. This will be equals to, here P max is 2, right? 2. This will become minus of cos delta. Oh, okay. I think delta CR will get anyways cancelled. Oh, okay. That is good, no? Okay. It is still good. So what I can do is, let me keep it pi by 180. Okay. Delta CR anyways will be cancelled. So plus, right? If I integrate this value, what will be this? So this will be first term. If I integrate, this will be 1 into delta m minus delta CR into pi divided by 180. So actually no, it is not a non-linear equation, it is a linear equation only, because your delta CR and delta CR will get cancelled. Luckily, you are lucky. Okay, delta CR and delta CR will get cancelled, and this will become actually 2 P max into cos of delta from delta CR to delta M equals to 0, right? So your delta CR will get cancelled. This will be delta M minus delta naught. So what is delta M minus delta naught? Delta M minus delta naught is 110 degrees, that is given to me. So 110 degrees divided by 180, okay, into pi into pi and plus 2 cos of delta m. So what is delta m? Delta m is 140, right? Delta m is 140. Cos of 140 cos of 140 will be equals to minus of this, right? Minus of 2 cos of delta CR. Okay, so let me calculate this value. Let me calculate this value. What is this value? So this is equals to cos of 140 into 2 plus pi into 11 divided by 18. So it comes out to be 0.38. So it comes out to be 0.38. I'm doing this correctly or not? 2 into cos of delta, yes, cos of 140 minus this. Oh, sorry, it is a minus, right? It is a negative, so it will become plus here. This will be plus only. It is cos theta m minus theta r, so it will go on the right hand side. This will become plus. So yeah, 0.38 divided by 2. So your cos of delta CR comes out to be 0.194. So cos inverse of this comes out to be 678.82 degrees. Okay, but my answer is wrong. Okay, because I have solved it here. I am getting some different answer. So maybe I have done some mess up. So 1 2 delta m. Okay, let me see the delta m. Delta m is no, I have done correctly only. The maximum swing of the rotor is 110. Okay, one thing I have made a mistake here, right? Actually they are telling me the maximum swing of the maximum rotor swing. By maximum rotor swing, actually they are mentioning the, this also I have done this mistake. It is not delta m minus delta naught. By maximum rotor swing, they are mentioning the maximum difference of the rotor angle, right? Maximum the rotor is like maximum rotor angle with respect to rotor mmf. So it is actually talking about the delta m. Okay, maximum rotor swing actually means it is talking about the delta m. So this is not correct. So delta m actually is equals to 110 degrees. This is your delta m. Okay, my bad. So your delta m will be 110 degrees. So this will be actually wrong. So this will be actually 110 minus initial 30. So this will be 80 degrees. This will be 80 degrees and this will be 110. Okay, so maximum swing means like how much have this maximum swing, right? How much has it swing? How much has it swing with respect to reference axis? So the swing has been observed with respect to reference axis, not with respect to delta naught. Swing has been observed with respect to the reference axis, and reference axis is at angle equal to 0. So swing will be observed with respect to reference axis. Okay, so this equation will become 8 divided by 11 into pi plus 8 divided by 11 into pi plus cos of this into 2. This becomes 1.6 divided by 2.8. This is again wrong. Okay, something again I'm messing up. Give me 1 second. Pi by 180. So this is 30. So delta m minus delta r. So minus 30 is 80. So 80 divided by 180 into pi plus 2 into 110 cos. Yeah, now I think it is correct. Divided by 2. Yeah, this comes out to be 0.356. And if I do the cos inverse of this, it comes out to be delta CR comes out to be 69.1 38 degrees. So that's how you will solve these kind of questions. This is my critical clearing angle. This is my answer. So this is the like maximum clearing angle that I can afford, right? So can you find out the TCR? So that is the homework for you, right? Find out the critical clearing time, after which I will not be able to clear the fault because okay, M is not given. So M, right? Let me say what is your H. H is equals to, let's say, 2 megajoule per MVA, and your frequency is 50 hertz, right? These data are given, and with respect to this data, can you find out the critical clearing time? What is the time after which if I clear the fault, it is of no use, the system will be remaining unstable. So that is the definition of critical clearing time. You can go and have a read. After, if I clear the fault after the delta CR, right, after this critical clearing time, if I clear the fault after critical clearing time, the system will lose synchronism. The system will simply lose its synchronism. Okay, that is the important point that I want to mention over here. Okay, so critical clearing time depends on a lot of things. So today it's like a lot of things are happening. So in the next lecture we will continue with this homework question, and few more things we will understand like regarding critical clearing time, and we will solve few more questions. Okay, so thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the lecture 16 of our stability. So in the previous lecture, we stopped in between, like there was a question that I gave you as homework, and we will continue with that, right? We will continue along that flow. And also in today's lecture, we will understand what is, like, if two machines are connected in a power system, right? Then what is the equivalent inertia constant? Only valid, like we will find out the equivalent inertia constant only for two machines, right? I cannot find it out more than two machines. For that, there are some other like software that will find it out. So using like our normal numerical analysis, so we will only be able to find out the equivalent inertia constant of two machines, right? Also we will see what are the different methods to improve transient and improve stability, basically improve both the steady state and the transient stability, basically improve the stability. And then of course we will do numericals. So this will be the part 1, right? And in the next part we will do the remaining numericals. Okay, so let's start with the point where we stopped. Actually, basically here we stopped, right? Here we stopped. I told you to find out the critical clearing time. So what is the formula for critical clearing time? I know I have found out my delta CR, right? So delta CR will be equals to delta naught plus PA by 2m into TCR whole square, right? What is M? I have to find out M, right, in second square, right? M in second square will be, it will be, normally it is GH by pi f, but I am finding it out in second square, so I have to divide by G, so it will be in H by pi f, right? It will be H by pi f. So H is given to me, that is 2. Frequency is given to me, that is 50 hertz, right? Okay, okay. One more thing, maybe I have forgotten, because okay, here it is also in per unit, right? Okay, power is also in per unit. Okay, my bad. So actually I should have given the power as well. Okay, I should have given the power as well. So this will be what? So the power, how do I add the power as well? So how do I add power? Power. Okay, so actually in the question, right, I should have mentioned what is the S base, or S base I should have mentioned actually. Let me take it as 2 MVA. In the question I should have mentioned this. So here, right, my S base is 2 MVA. Otherwise you will not be able to solve it. So if your S base is 2 MVA, right, then this will be 50 into pi. This will be same here. What is your accelerating power? What is your accelerating power? Your accelerating okay, sorry. Oh, maybe we don't need it, right? Oh, sorry. Already this rating will automatically be yeah, okay, sorry. We don't need this as base. Sorry, what am I talking about? It is already in per unit. Okay, sorry. We don't need this. It is already, like, the unit of this is what? Only second square. So that will be simply cancelled out by this, right? I don't need to do anything. Okay, sorry, I don't need to do anything. So whatever I gave was actually correct. So here delta CR is 138, but in degrees, right? So if I am putting here values in degrees, right, this will be equals to delta naught is initial angle. What was the initial angle? Initial angle was have they given? Okay, initial angle, okay, I will be able to find out. It is 30 degrees, right? So delta naught is 30 plus PA. That what is the accelerating power during fault? What is the accelerating power during fault? It is PM naught. What is PM naught? It is simply 1, right? PM naught is simply 1. So it will be 1 upon 2. Remember, here I have to write pi as 180. Why I have to write pi as 180? Because here I have to write pi as 180. So because everything is in degrees, right? Every single thing is in degrees. So this will be m. So this will be 2. 2 is already 2 is there. 2 into 50 into 180 into TCR whole square, right? So from here I will be able to find out my TCR whole square. So this will be 69.138 minus 30, and this will be into 4 divided by 50 divided by 180 whole under root. So this comes out, your TCR comes out to be equals to 0.132 seconds, right? Okay, within this fraction of second you have to clear the fault, otherwise it will like lose synchronism. Okay, now if I want to solve, let's say you say that sir, you are putting degrees, I want to solve in terms of radians. Yes, it will work in terms of radians also, it will work. So what is 69.128 in radians? So 69 is a good number. 0.139 in radians, so it will be 1.2 67 radians, right? And what is your delta naught in radians? Delta naught in radians will be simply pi by 6. So pi by 6, right? Pi by 6 is simply 0.5236 radians. Okay, so basically I am just solving it with different method. So this will be what? So here, right, I will use the same equation but in different format. So this will be delta CR will be 1.2067, delta naught will be 0.5236, and this will be plus 1 into 50. This time it will not be 180, it will be pi, because everything is in radians. 2 into 2 into TCR whole square. You will get the same answer, right? This plus 1.2067 into 4 divided by 50 divided by pi whole under root. Yeah, you are getting the exact same answer, that is 0.13189, that is 0.132 seconds, right? So either way you will get the same answer, same result. So within this is the critical time within which I have to clear the fault, otherwise system will go out of synchronism. Okay, that is the significance, meaning of critical clearing time. So because your delta naught will increase from delta naught to delta CR, within this point of time I have to clear the fault, right? If I don't clear the fault after this point of time, what will happen? It will go out of synchronism, because the accelerating area will be higher than the deaccelerating area. Okay, so yeah, that was about the critical clearing time. I hope it is clear. What do we mean by critical clearing time? Okay, so now how can I improve it? How can critical clearing time be improved, right? Because like you if you see here, the critical clearing time is very low. What is critical clearing time dependent on? It is like almost, if delta CR is high, right, then critical clearing time also will increase, right? So I have to somehow increase delta CR because I need more time. You need more time. Everyone needs more time, right? So we are crunch on time. We have only 0.132 seconds to clear the fault, but I need more time. I need more time. So if I need more time, what do I do? What do I need to do? So, so if I need more time, I have to increase TCR. So how will I increase TCR? So what is TCR dependent on? So TCR, if I find out what is TCR dependent on, TCR is equals to what? This formula, right? It is delta naught plus 1 by PA divided by M into TCR whole square equals to my delta CR. So this critical angle I don't have much control on, right? I don't have much control on critical angle. I don't have control on the initial starting point. It depends what was the initial operating point, right? Of course, the user has the control. I cannot control this, right? I can control M because I can control the machine parameters. So I can only control this M, right? So what is my TCR equals to? If I rewrite this equation properly, TCR will be critical clearing time will be under root 2m by PA into delta CR minus delta naught. Okay, so this is my critical clearing time formula. So what does it depend? What does it depend on? So it depends on, actually, first of all, it depends on PA. Also it depends on M, right? So if my M is higher, right, my TCR will be higher. So thus basically the transient stability will be improved, right? This we'll use in today's lecture only. The transient stability will be improved. Okay, transient stability will be improved. Okay, yeah. So these are the few things about critical clearing time. I have derived the formula as well. Now, uh, uh, what can I say? So how can I further improve it? How can it be improved further? So further, right, one thing we can do, if I have just a single generator, right, and that is connected to the line, correct? If a single generator is connected to line, right, so let's assume that it is delivering some PE amount of power, PE amount of power. So P naught is this, right? P naught is this, and your I have a single generator, only G, right? What is PM naught? PM naught is equals to P naught, right? So this is the case one. So in both cases, I will derive the uh, critical clearing time. I will analyze the transient stability. So case two, right? What is case two? Case two, case one and case two. Okay, case one and case two. So in case two, I will have two generators, right? Again, to the load, I will deliver one PE power only, but I will have two generators now, right? So what will be the advantage? So if suddenly some fault happens, this will be more stable than the case one. Okay, so let's say like I'm delivering here one PU amount of power, right? But of course two generators are there, let's say G1 and G2, they are identical, right? And they are delivering, of course they are identical, so the load also will get divided. PO1 will be simply 0.5 PU, right? And PE O2 will be 0.5 PU. okay, 0.5 pu. Okay, I hope it is clear. So here if some fault happens at the terminals of the generator, what will happen? Your PE will go to 0, right? Your PE will go to 0 if some fault happens here. So your PE will go to 0. So what will be your accelerating power for this case? It will be simply PM naught, which is equals to 1 pu, right? Right, which is equals to 1 pu. But what is accelerating power? Let's say if some same fault happens across the generator terminals, what is the accelerating power here? Here PA will be equals to PM naught of 1, which is what? Which is simply 0.5 pu, which is simply 0.5 pu, right? So your PA reduces. Does it help? Does reducing PA help me? Right, PA reduces. Does it help me? So this I can verify from here, right? From this formula I can verify, right? What did I derived the formula for P critical angle? Somewhere I derived, right? Oh, what is it? Yeah, here in the previous page only. So what do I notice here? So if PA reduces, your critical time increases, right? So that is actually good. I am getting more time. So this is good. This system is better, right? So that's why we connect multiple generators in parallel. So there are obviously multiple reasons. This is also one of the reasons why we connect two generators in parallel. Okay, this no one has explained you. I know this no one will explain you today, right? So this critical clearing time of case 2 will be higher than critical clearing time of case 1, which is good, right? I am getting more time to clear the fault. Okay, so I hope these things are clear, right? These things are clear. So same analogy, right? Critical clearing time is a time maximum delay that you can give to the brake before you will crash, right? Same analogy like the car crash. So it is the maximum delay that I can provide before pressing the brake pedal, right? Like let's say 2 seconds. 2 seconds is TCR. So I can not press the brake pedal and let the car go on, right? After 2 seconds, if I press the brake pedal, it will not be able to stop from the crash. It will crash to the wall, right? If I don't press the brake pedal earlier, it will simply crash the wall. So that is known as critical clearing time, and critical clearing angle is basically the distance. How much distance the car can move, okay, forward, after which if I press the brake pedal, it will not be able to stop from the crash. Like how much distance can the car move if I stop before the brake, sorry, let's say this car has moved from this point A to B, right? A to B. So between these 2 points, if I press the brake pedal, then it's fine. It will not crash to the wall, that is point C, right? But if I press the brake pedal somewhere here, the distance it has moved beyond B, then if I press the brake pedal, it will simply crash to the wall, right? So this B point, this distance, right, AB is like, it is linear distance, but in angular distance, it is known as critical clearing angle, and the time, like till it reaches B, right? After this point, if I press the brake pedal, it will simply crash. Okay, I hope like just giving an analogy, I think it is already clear what is critical clearing time and critical clearing fault. So let us find out the expression for the critical angle and the critical clearing time for a three-phase fault occurring at point F. Okay, this is the point F. I forgot to like mention the point F. Sorry, I should not have put the ground terminal here. I should have just put the point F here. Okay, so this will be my point F. So if some fault is occurring here, they are asking me to find out the expression for critical clearing angle and critical clearing time for the three-phase fault. So when fault was not there, before the fault, what was the like initial, because they have to ask me to find out the expression, they have not asked me to exactly calculate the delta CR, right? They have not exactly asked me to calculate the delta CR. So I just have to find out the expression. So before fault, pre-fault condition, case 1, pre-fault. Pre-fault condition. Okay, now this fault is there, right? Pre-fault, yeah, things will change. Now here, right, remember here the fault is not occurring at the generator terminals, so PE will not be exactly equals to 0, right? PE will not be exactly equals to 0. Okay, here the fault is not exactly occurring and at the generator terminals, so PE will not be exactly equal to 0. That I will prove it to you as well. Okay, now slowly we are taking this level 1 up. Okay, also clearing the fault means removing the faulty section from the power system. Clearing the fault means remove. So if I'm clearing the fault here, right, previously in the generator case it was, if I cleared the fault it would have delivered the power as it is, right? But here if I'm clearing the fault, it basically means I have to remove the faulty section from the power system, right? I have to remove the faulty section from the power system. Okay, why? I will explain why is that the case. So here if you notice one thing, here the fault was occurring at the generator terminals. The fault was occurring at the generator terminals. Okay, so if the fault is cleared, that basically means it will deliver as it is, right? Fault is occurring at the generator terminals, right? At this point, if the fault is cleared, it will deliver as it is because VT will not change. All these things will not change. Just I was assuming if the fault is happening somewhere here, right? If the fault is happening somewhere here, then what will happen? Okay, but here clearing the fault basically means we have to remove the faulty section. So the faulty section will be removed. So this part will be removed. This line totally will be removed. Okay, so that is one the key point that you have to understand. Okay, so yeah, now now let's basically solve this question, right? So here, what is the pre-fault condition? Pre-fault, what is the equivalent x? It is 0.2. This is also 0.2. So this will be 0.1. So here I have 0.1, right? J.1, and here I have J.04, right? Okay, J.04, and here I have the terminal voltage VT to be 1 angle 0, and here I have the EF, right? That is 1 angle delta, correct? Okay, so this is the pre-fault condition. So in pre-fault condition, what is my PE naught? I don't know what is my PE naught, right? I know PE naught will be simply 1 into 1 divided by XS, that is 0.14 into sine of delta. Delta value they have not given me. What is the delta value? So I will assume this as delta only. Okay, let me take it as delta naught, otherwise there will be a bit of confusion. Delta naught. So let me assume this as delta naught. Okay, and this will be equals to my PM naught, right? Now if fault has occurred here, what will happen? If fault has occurred here, what will happen? Will it deliver some power? Of course it will deliver some power here, it will deliver some power here, it will deliver some power here as well, right? So in 3 places it will deliver power. In 3 places it will deliver power, right? So we have to convert this from delta to star to understand this better. Okay, so during fault, case 2, during fault. So during fault, what will happen? During fault, this will be short circuited. Now if this is short circuited, what will happen? If this is short circuited, the connection can I find out how much power is this sending, right? I just need to find out how much power is this sending. So the connection diagram is somewhat like this. So I have a delta over here, and then this is connected, and then this is connected, and then this is shorted, right? Okay, and then I have here a this reactance 0.04, right? And then I have this Eg. That is one angle delta naught, correct? And here I have the potential, here is 1 angle 0, right? So it's kind of a star delta kind of thing. So can I convert this? Anyways, I could have easily able to, I could have been able to convert this, but do I need to convert this? That is what I'm thinking. So how do I find out the power here? So this point potential is 1 volt. If I am able to find out the potential here, then this will be a cakewalk for me. So this point potential is 1, right? So I just need to find out the potential here, right? I just need to find out the potential here. Will I be able to find out the potential here? That is what I'm trying to, that is what I'm trying to think. Is there any other better way? If some fault is occurring at point F, what will happen? So yeah, if I convert this into star, yeah, this will be better. Yeah, so first of all I will convert this into from star to delta, right? Delta to star, then again I will convert it back. So yeah, let's first convert it. So this is J0.2, right? This is J0.1, J0.1. So I'm converting it from delta to star, so I have to divide. It is division, right? So division means everything will be divided. J0.4 will be here, and if I'm talking about this one, so it will be this times this divided by the whole number, that is 0.4 summation of everything. So it will be 0.2 into 0.1, and j will be here, right? So this will be 2, right? So this will become j0.05. okay, here I will have j0.05. as it is symmetric, this side also will have j0.05, and this side will have what? It will be just the half, right? So it will be j0.025. so j0.05. so I will have this is j0.04, this is j0.05. okay, then again I will have j0.05, and then again I will have here j0.025. this will be Vt, right? 1 angle 0, and here I have 1 angle delta, right? Now what I can do is I can again convert it back into delta. Okay, why? I will explain. So this together will become 0.09, right? It would be better actually if I keep it 0.05. that is the best thing. I will change the question for my easier calculation. This will be, let's take this as 0.05. okay, so this will become 0.15. this will be 0.5. so this will be j.1, j.1. okay, right? So this will be j.1. then I will have here j0.025, and this will be j0.05. now again I will convert it into delta. So I will have this delta format. This will be one of the reactants, correct? My drawing is really bad. This will be the other reactants, and this will be the other reactants, correct? So what will be this one? So delta, right? Now it is delta, so it is delta to star, right? Sorry, it is star to delta, so it is summation. Summation means I will have, if I want to find out this, I will add this and this, right? So j 0.1 plus, like j will always be there, it is purely inductive, 0.1 plus 0.05 plus multiplication of these two divided by the opposite one. So 0.1 into 0.05 divided by 0.025, so this actually comes out to be times 2, so this will be 0.2, so 0.15 plus 0.2, that comes out to be j 0.35. so this value, right, this value comes out to be j 0.35, and this is only the important one. Why? Because this point potential is what I know, this point potential, that is 1 angle delta. I know this point potential, what is the potential here, that is 1 angle 0. So I will be able to find out my equation of power, right? I just need the potential across 2 points, right? I will easily be able to find out the equation of power. So what will be PE now? During fault, what is PE? So PE is actually equals to 1 into 1 divided by this reactance. It becomes 0.35. So your PE actually shifts down into sine delta, right? This is how my delta is varying. This is how my delta is simply varying, right? This is the PE of the case 2. Now in case 3, what is happening? In case 3, when the fault is cleared, right? In the case 3, when the fault is cleared, fault cleared. So fault cleared basically means what? If fault is cleared, basically your line is removed, right? How will line be removed? So basically there will be few circuit breakers that will be connected here, right? Circuit breakers will be connected here and here. So those circuit breakers will simply break the circuit. Only the top path will remain. All the other path will simply go away. Okay. Other parts will not be there. Okay. Okay. So if the fault has been removed, then what will be PE3? So PE3, right? If the fault is cleared, then simply this line has been totally removed. Only this much, the top line will be there, right? Only the top line will be there. So this will be removed totally. If top line is there, what is the equivalent circuit? Equivalent circuit will be, so here I have J 0.05 and J 0.2. So the equivalent circuit will be J 0.25. Okay, and this will be 1 angle 0, this will be 1 angle delta naught. Okay, so what will be the PE here? Remember, your mechanical power is not changing. Here my PM, so PM2 is what? It's simply PM naught. It does not change. Mechanical input power is constant throughout, right? Here what is your PE, right? What is your PE? P3. P3 will be simply 1 angle 1 into 1 divided by 0.25 into sine of delta. Okay. So what do you notice here? What do you notice? So basically you notice one thing, that your P max 1 is the highest, right? If you see, what is the P max 1? P max 1 was this divided by P max will be where did it go? P max is 1 divided by 1 divided by 0.15, right? So what is here P max? So P max 1, if I see, right, if I find out the P max 1, if I find out the P max 1, so it will be 1 divided by 0.15, which is 6.67. 6.67. So I'll just write down the value. So here, right, what is Pmax 1? Pmax 1 is 6.67. I'm sorry. What is the Pmax here? Pmax 2 in the case 2. It will be 1 divided by 0.35. So which is equals to 2.857. Okay, 2.857 pu. This was 6.67 pu, and here at the end, right, pe3 Pmax 3, right, equals to 4 pu. So the thing is that this is 4 pu, right? Yes, this is 4 pu. That is, yeah, that is in between. So here, what is the comparison? Comparison is your Pmax 1 is highest, 6.67. Then your Pmax 2, Pmax 3, that is after the fault getting cleared, and during fault, of course, your electrical power will always be the lowest. So intuitively also you can say that Pmax 2 has to be lowest, because even though it is not going to 0, but during fault always your power output, electrical power output, will always be the lowest. Okay, that is what is happening. So if I draw the three curves, right, I will have 3 curves, right? So Pmax 1, so in case 1, my power PE1 was what? It was Pmax 1 into sine of delta. What was Pmax 1? That is whatever the value we calculated. It was 6.67, right? It was 6.67. Am I correct? Yes, we are correct. This will be 0.5. So I will have 3 graphs, 3 sine graphs. Okay, because all of them have different peaks. All of them have different peaks. So this is my PE. Okay. And this is the first one whose peak is the highest, right? Whose peak is the highest. Okay, then I have the, let me color it to different color, to blue color. Then I will have the blue color whose peak will be bit on the lower side. Then I will have the green color whose peak will be the even lower, right? Okay, so remember your PM naught is here. PM naught is here, right? This is my PM naught. And if during certain stage your PM naught is never intersecting with the graph, then of course there is a problem. But it will always, like, this is my PM naught, right? And very key point for the system to remain stable, right? For the system to not lose synchronism, there needs to be, like, it needs to intersect basically. It needs to intersect. How did it intersect? So it should always intersect with all the 3 graphs, right? So which one is the most vulnerable? This one is the most vulnerable, right? So my PM naught should always be lower than the lowest value of Pmax of all the 3 cases. So for the system, because it must intersect. If it does not intersect, then there is a problem. If it does not intersect, then that means there is no stable point, right? There is no operating point. So it must intersect the graphs. It must intersect the graphs. Okay. So what I can say is, my, otherwise it will lose out of synchronism. For machine, synchronous machine to remain in synchronism, for the synchronous machine to remain in synchronism, your Pm naught, right, must be less than the maximum of, minimum of all the Pmax, right, must be lower than that value. Pmax 1, Pmax 2, Pmax 3. Okay. So this is my Pmax 1, right? This is my Pmax 2, and this is my Pmax 3. Okay. So now they want us to find out the expression, so we have to find out the expression, right? We are actually not doing the thing, we have to find out the expression. So how do I find out the expression? So one thing I know, that initially I will copy this graph. So what is the scenario, what is happening actually? So initially I was at this point, right? So let me do this in actually full only, because this is not changing, right? No, this is fine, let me do it full. Yeah. So this is my delta naught, correct? So this is my Pmax 1, the initial operating point. So this is the initial graph, right? So here my initial angle was here, delta naught. This was the point A. Let's assume this is the point E, right? After this, suddenly fault happened. If fault happened, my graph, the electrical power output will shift to this one, right? Electrical power output will shift to this one, this graph, right? So initially, like if you see during fault, what is PE? So PE, if you see during fault, what is PE? PE2 is actually the lowest value, that is 2.87, 2.857. PE3 is actually highest, right? Not highest, in the middle. So this is the PE, this is the PE, sorry, this is not, sorry, I made a mistake, sorry. This will be my 3, and this will be my 2. Okay, this will be my 3, this will be my 3. Okay, so suddenly what will happen, a fault has occurred, right? So if a fault has occurred, what will happen? This will, okay, why is it not? This will simply connect to this graph, right? It will reach to this point. Let's say this is point B, and it will now what is happening? Suddenly what is the accelerating power here? PA. So PM naught is not changing. PM naught is here, and your electrical power output is this, right? It is in the bottom. So of course PM is higher than PE. So PA will be greater than 0. If PA is greater than 0, there is some acceleration. If there is some acceleration, delta will increase. So I will reach this point because I have to follow the electrical characteristics of the synchronous machine, and after this what will happen? Delta will increase. Delta will increase, delta will increase, and there will come a point after which I have cleared the fault, right? So let's assume that at this point I have cleared the fault, that is delta CR. At this point I have cleared the fault, that is delta CR. Correct? So this is my delta CR basically. So if this is my delta CR, right, what I can do is, after this fault has been cleared, if fault has been cleared, so at point C fault has been cleared. If fault has been cleared, which characteristics I will follow? I will follow the third one, case 3, right? When fault has been cleared. So when fault has been cleared, what is my PE3? It is this one. It is the PE3. PE3 is this one. So I have to follow this graph now. I have to follow this graph. So I will move to this graph. For the same rotor angle, I will move to this graph. If I move to this graph, now what do I see? So understand this thing here, my PA, like in this region my PA was always positive. So omega R was increasing, and here omega r was reducing. It can reduce. Okay, then at this point suddenly fault has been cleared, so I am following this graph. Okay, and still let's assume that omega r is much higher than omega s. If omega r is much higher than omega s, still the rotor angle will increase. Still I will follow this graph. I'll go on. How much maximum I can go on? I can maximum at max go till this point, right? This is the point. This is the last stable point till which I can go. This is the last stable point till which I can go. If I move beyond this point, I will not be able to come back to stability. If I move beyond this point, I will not be able to come back to stability. So this is actually my delta m. So what is the delta m this time? So delta m this time is not simply pi minus delta naught. It is not pi minus delta naught. What is delta m? Delta m actually is equals to pi minus sine inverse p m naught, right? Of course your mechanical power is not changing, right? Mechanical power is same. So pm naught where it intersects with the second graph, right? So like basically your power, right, pe3 must be equals to pm naught, right? It must intersect these points. It is intersecting at these 2 points. It is intersecting, right? This is the point where it is intersecting. This is the point where it is intersecting. So pa3 is equals to pm naught. So this will be equals to, what is my p3 equals to? So p3 is, what is p3? p3 is simply this graph, right? P max 3 into sine delta. P max 3 into sine delta. So this P max 3 into sine delta, right? Sine delta m. Okay, I want to find out m, delta m basically. That is equals to Pm naught. So if I want to find out delta m, what I have to do? I have to do pi minus sine inverse of Pm naught divided by P max 3. So that is what I will put here, pi minus sine inverse of Pm naught divided by P max 3. Okay, so this is my delta m basically. This is my delta m. Okay, so it's very tricky. Okay, very tricky thing. So we have to solve this basically. So we have to follow the equal area criterion. So can you tell me, can you identify what is the deaccelerating area, accelerating area? So here, right, I will copy this graph because I don't want to mess this graph again, right? So let me keep this graph on the side here, and with this graph I want to identify the accelerating and deaccelerating area. So in this graph, what is the deaccelerating area? So the deaccelerating area is this one, right? Sorry, not this one. So my PM is here. So this is my this is my accelerating area. This is my accelerating area. Okay, so this graph, this point is my accelerating area. Which color shall I choose? So let me choose highlighters. So this part is my accelerating area, and this part is deaccelerating area, and this part is also deaccelerating area. So this whole part here, right, it seems like the deaccelerating area is much larger, right? But it can be lower as well. Okay, one point I made it clear. I will explain what I made. What did I do wrong? I will explain one thing, that one conclusion I wrote wrong. So this is my, okay, let me use some other color. This whole area, right? This whole area is basically the deaccelerating area. Okay, so here the deaccelerating area is much higher than the accelerating area. So you might feel, sir, kya hi matlab? Okay, so I do understand that this will be always stable. Deaccelerating area is much higher, but like here I made a mistake here. For the synchronous machine, right, I should have wrote here, for the synchronous machine to remain in synchronism. For the synchronous machine to remain in synchronism, what needs to happen? So basically the thing is, before fault is cleared there is a stability point. After fault is cleared, right, that is my P max 3, your PM naught must be lower than this. otherwise there will not be any intersecting point with the third graph. So it does not matter when the fault is there, it does not matter whether it intersects or not, okay, because anyways the machine is going out of synchronism, right? It does not matter. But your your mechanical power input must be less than the Pmax 3. If it is less, then it will intersect the blue graph, right? If let's say it is greater, if it is somewhere here, if it is greater, right? So when the fault is there, then there is no problem. When the fault is there, then there is no problem. It will directly go to this graph and it will go like this. As soon as the fault is cleared, right, I will follow the graph 3, blue graph. So if I follow the blue graph, I am observing that there is no valid operating point for the particular mechanical input, right? So it will never intersect the blue graph. If it never intersects the blue graph, then which point I will go? I need to go to the stable point. Where is the stable point? Where is the operating point? It is never intersecting the blue graph. If it is never intersecting the blue graph, then it will go out of synchronism. It can never go, it can never remain in synchronism. It can never remain in synchronism, right? So that is the problem. If your PM naught is greater than the peak value Pmax 3, steady state limit of the system when the fault is cleared. So basically your mechanical input, right, this is my mechanical input, must be this is the steady state limit, steady state stability limit after fault is cleared. Okay, so I hope these things are clear by you. Okay, so that conclusion I wrote actually wrong. So I will explain, right? So here, right, here it is observing, yeah, deaccelerating area is much larger than the accelerating, so it is always stable. So what if I change the initial starting point, right? What if I change the initial starting point? So where is the 3 graphs? So the 3 graphs is here, right? So let's take the graphs, okay, and let me increase the, not delete this, let me increase the initial starting mechanical input. Okay, so it is not here, let me place it somewhere here. Okay, if I place it somewhere here, very large value, very near to PM naught basically. So here, right, this is my delta naught, correct? And of course suddenly fault has occurred. If suddenly fault has occurred, this is the graph, electrical power output graph. I will follow this graph, so I will suddenly jump down to this point, right, from point A to B, and then I will follow this graph till what time? Till the fault has been cleared, right? Let's say at this point of time, delta CR, at this angle the fault has been cleared. So again I will follow the blue graph now, because after fault getting cleared, this is the electrical output characteristics. Okay, I will follow this graph, so this will be point C, this will be point D, and ultimately again the angle will increase because still omega r is greater than omega. If you see here, the speed is like your PA accelerating power is always positive, so here still omega r is increasing. So here, yes, omega r will reduce, but omega r is greater than omega s, so delta will increase. So delta will still increase, and this is the maximum value, right? After this, if I go after this, right, system will go out of stability. So here this is my delta m. Again the expression for delta m is same, right? It is pi minus sine inverse PM naught upon P max 3. But what do you observe? You observe that the accelerating area, if you observe one thing, accelerating area has increased and deaccelerating area has reduced, right? So now I hope you are able to understand that this is a problem, right? It's a problem. We have improved the stability quite a lot, because still while the fault, the generator is supplying something, so that has been improved, right? It is directly not going to 0, so otherwise the accelerating area would have been this whole thing, right? But that has been improved, but still there is a problem. Okay, so what is the expression? what is the expression for delta CR. Okay, they have asked us the expression for the finding out the critical angle and the critical time. Okay, critical clearing angle and the critical clearing time. So what is the delta CR value? So delta CR value, we have to use the equal area criterion, right, for the system to remain stable. PA d delta, simple, this is simple equation. Power system is simple, right? D delta, I will start from delta naught, right? I will go till delta m, and it must be equal to 0. This must be equal to 0. So I have to break it down. I have to break my PA delta into 3 parts. Not 3 parts actually, 2 parts, right? 2 parts. So your PA, it is again a discontinuous function. It is equals to PA is what? It is PM minus P. So PM naught minus during the fault. When the fault has occurred, then what is the electrical characteristics? It is P max to sine delta. So it will be P max to sine delta when my delta is between delta naught and delta CR. Okay, and just after delta CR, the mechanical input has not changed. It will still be PM naught minus P max. Now it has gone to P max 3, the third graph, right? So P max 3, because electrical fault has been cleared, so electrical power expression will be changed now. Sine delta, and this is the range where delta is between delta CR and delta M. So delta CR we have to find out, right? So your delta M will be what? Delta M already have written. Delta M is equals to pi minus sine inverse PM naught upon P max 3, right? What is P max 3? P max 3 already have derived. I will not say it over again. And delta naught is what? Delta naught, like this also I have written previously as well. Delta naught is equals to sine inverse PM naught divided by P max 1. Okay, so you put these values, like you integrate this equation, and you will be able to, from this equation you will be able to find out delta CR, and if you are able to find out delta CR, you will be able to find out the TCR, right? It's very simple. Okay, so that's how you solve this, right? That's how you use the equal area criterion in this equation. Okay, it's very simple, not that difficult to understand. Okay, so so find the expression for critical angle and critical clearing time for the three-phase fault occurring at F1 and F2. Now if some fault is occurring here and here, what will be the expressions? Okay, if already they have given me, already in the question they have given me what are the expressions during normal operating condition, right? What is the graph? During fault condition, what is the graph? And during fault at F2, what is the graph? Okay, so what will be the do I need to find out the, I can directly find out the critical clearing time and okay, I can directly find out the critical clearing what do you call, I can directly find out the critical clearing angle actually. Yeah, I can directly find out the critical clearing angle. Yes, I can directly find out the critical clearing angle and the time as well if the H is given. So inertia constant H is given as 2 megajoule per MVA and frequency is given as 50 Hz. If these two things are given, then I will be able to find out not just the expression, I will be able to find out the critical clearing angle. I will directly be able to find out the critical clearing angle. Okay, so your okay, so now how will I find out the, again I will use the same, right? So during, let's analyze for the case during fault at f1, okay, then I will calculate for the fault at f2, okay. So what happens when I have a fault at f1? So if I have a fault at f1, what will happen? If I have a fault at f1, so I can directly write, okay, this pmax are same, right? If this pmax are same, then so there is no point, then there is no point. This must be something different. I have to change this, right? Let me change this, to 1, otherwise what's the point? Okay, okay. So if I have a fault at f1, what is my, like, delta naught will not change. What is my delta naught? Delta naught will be sine inverse 0.5 upon 2.4. So this will be 0.5 upon 2.4 sine inverse. So this is actually 12.025 degree. Okay, so this value is actually 12.025 degree. Okay, this is my delta naught. Now I will directly solve it, right? So the expression will keep on changing. So in the first case, if fault is occurring at f1, so I'll copy this graph, copy the graph of PE and PM naught, right? So we'll have a fault occurring here. Okay, I will delete the input power. This took 1 hour. I have not even started today's lecture. That's funny. This is the end. Oh, there is more question. Oh my god. So I think I have to add another lecture. I have to add additional another lecture. This stability is like going long. Lamba ja raha hai bhai, marathon. Okay. So yeah. So this is the initial. So this graph is the basically the initial power. So this is the Pmax 1, right? This is Pmax 1. Okay. Then after this, during fault, the graph will be something like this. During fault, let's assume that it is 1.2, so it is just half, right? So it is half. If it is half, it will never, yeah, it will obviously intersect. So 0.5 actually should be much lower. It should not be this high. It should be much lower actually. Somewhere here. Now here it is fine. It should be here. Graphically it does not make sense, right? Okay, so it will obviously intersect here as well. So during fault, and if after fault is cleared, of course again it will come back to normal operating condition. If they have not mentioned like after fault is cleared whether this line will operate or not, so you have to assume that normal operating condition is this one only. Okay, so this is during fault, right? And the graph here is Pmax Pmax 2. Pmax 2 is 1.2, right? So basically it will come here. So I will start from this point, right? I will start from this point. Start from this point. This is my delta naught. And then again, when the fault will occur, I will come down here. Then I will accelerate, and then there will be some critical clearing angle. And after the fault is cleared, again I will come back to this position, and again it will increase, and it will go on till here. Okay, till delta m. So in this case, delta m will be simply pi minus delta naught. In this case, because there was no third graph. But actually, I should have also added a third graph. That would be better actually. I should actually add a third graph. So I'm making the question while I'm while I'm creating all this, right? Okay. So that's my bad. So actually I should okay, let me reduce the size of this. pre-fault condition. Pre-fault condition, and I will add another graph, right? That will be basically, let's say that is post fault condition. Okay, so this is post fault. So to copy, sorry guys, I have to change the whole question. I'm really sorry. Yeah. Yeah. Now it is fine. So post fall, the graph is changing. So post fall, I don't need to add the page. Post fall, what is happening? It is going to another graph, right? It is not same anymore. Let's say it is somewhere here. 1.5 will be somewhere here, right? Change the color to something like this. Yes. So post fall, this will be the graph. So it will not directly go here. It will go to the third graph, post fall, right? So third graph it will go, and then it will increase. What will be the area here? So I will have some delta m. This time your delta m will not be pi minus delta naught, because I wanted to make it different, right? So your delta m will be what? Delta m will be pi minus, but it will be sine inverse pm naught. What is your pm naught? 0.5 upon p max 3. What is p max 3? 1.5. P max 3 is 1.5. This value is, peak value is 1.5. That is given in the question. 1.5. So this will be 1.5. Okay, so this will be 0.5 divided by 1.5 sine inverse. So this comes out to be 180 minus this. So this comes out to be 160. 160.53 degrees. 160.53 degrees. This will be my delta m, right? So from here I can easily find out my critical clearing angle. It's very easy. I can break my PA down into two cases. So again it will be 0.5 minus P max 2 during the fault. During fault, what is P max? It is 1.2, right? This is 1.2 during fault at F1. Okay, it is 1.2. So this will be 1.2 sine delta, and this will be 0.5 during what? During delta, between delta naught and delta CR, which I have to find out. Delta CR is what I have to calculate, and it will be 0.5 minus, the graph changes again, it is 1.5. So 1.5 sine delta between delta naught, delta CR, and delta m. Okay, so you will put, again you will apply the equal area criterion. Okay, PAD delta equal to 0 from delta naught to delta m equal to 0. So you will get basically, this will be, if I want to calculate this value, right, this will be, okay, so I will break it down. So this will be 0.5 is always common, right? So like I am directly solving the integration. I hope that's fine by you guys, or is it not fine? I don't think it is fine by you guys. You guys will not be able to handle integration, right? I know. Okay, you guys will cry in the comment section. Okay, so 0.5, so I will break this down. So this will start from delta naught to delta CR, PA angle d delta. Why am I breaking it down? Because there is a discontinuity, right? That's why. this will be delta CR to delta M PED delta equals to 0, right? So in this period, what is the definition of PA? This, right? So I will copy this and I will integrate this from delta naught to delta CR d delta plus delta CR delta M, and in during the second phase, what is the magnitude? It is delta CR, right? 1.5 d delta. This has to be equal to 0. So ultimately, what comes down is simply here delta CR automatically will get cancelled for this 0.5. So this will be 0.5. Like I hope this much you can handle, right? This much itna handle to kar loge. So this will be delta M plus delta naught, right? Now this is minus sign of delta. Minus sign becomes plus 1.2. This becomes plus cos of delta, right? Minus is plus cos of delta. Cos of delta CR minus cos of delta naught. Okay, and here also we'll have another plus 1.5 cos of delta M minus cos of delta CR equal to 0. So from here I can directly write what is my cos of delta CR. So cos of delta CR, this is 1.2, this is 1.5. So 2.7 cos of delta CR equals to, now this value will be what? This value will be 0.5 into this radian, right? So okay, 160 in radians. What is delta M in radians? So delta M in radians, right? So in radians this will be pi divided by 180. It comes out to be 2.8 radians, and your delta naught what does your delta naught comes out to be? So it is 12.025 into pi divided by 180. So it is 0.2, 1 basically radians, right? So this plus 2.8 is 3 basically. This is 3 actually. 3 into 0.5, 3 into 0.5 is actually 1.5. So this value is 1.5. This whole value is 1.5. Now what is this 1.2 into delta cos of delta naught? So delta naught is 12 degrees, right? 12.025. Cos of this is 0.978 into 0.1 into 1.2. So 1.2 is, this will be plus 1.1736, right? Then plus 1.5 into cos of delta M. Delta M is 160. So 160.53 cos into 1 point into 1.5. So this will be minus 1.412. So this, right, this will be plus 1.5 plus 1.1736 divided by 2.7. So your cos of delta CR, cos inverse of this, right? So this is 0.46634. So your delta CR actually comes out to be equals to 62.2. So I have told you that your delta CR will mostly always be less than 90. So you will see always your critical angle is mostly lower than 90 only. Okay. So this is the for the case 1, right? So for the fault at F2, I am giving you homework. Okay. Lecture is extending. So we have to finish in the next lecture, the whatever we are discussing. So fault at F2 will be your homework. This is your homework. I'll do it in the here workbook, but this is your homework, right? Let's finish the next question. Find the expression of delivered. Find the expression of critical. Okay. So critical clearing time, I hope you will be able to find out, right? Critical clearing time. Yeah. Let's actually calculate the critical clearing time. Again, it will take us time. So critical clearing time TCR will be what? It will be basically. Like I generally I forget this expression. I just remember this expression that delta CR will be equals to delta naught plus half PA by 2m into TCR whole square, right? So so your delta CR minus delta naught, which is basically 2.8 minus 0.21, so 2.59, right? It is basically 2.59. Sorry, half is already there, right? Into 2, yeah, divide by into 2 into m. M is what? M is basically h upon pi f. So pi f will be, it is in radian, everything is in radian, pi into 50, right? And this divided by actually PA. What is accelerating power? Accelerating power in per unit. So during fall, what is the accelerating power? Okay. Here, right? Actually, you will not be able to find out the critical time. Not that simple. You will not be able to find it out because your accelerating power itself is a function of time. Your accelerating power is not constant, right? It is a function of delta. Okay. You will not be able to find out the critical clearing time. Why? Because your accelerating power is not constant, right? During fault, it is a function of delta. It is changing. Like delta is already in the expression, right? So you will not be able to find out the critical clearing time. So it's not possible, right? Whenever you're like, that analysis will be difficult, right? So we will ignore that. So this is also very important to understand, like when you will be able to find out the critical clearing time, when you will not be able to find out the critical clearing time. So I have changed this question like 1000 times now. Okay, really sorry, but that's what you do, right? Like it shows that like I'm trying to see all the angles, and in any other channel, right, no one will explain you all this, right? You go and see, no one will explain these doubts. Okay, yeah, apologies, like I just noticed that the quality of the video, actually the tablet was actually low because for some reason the screen got reduced, right? So I had to like expand it. I just noticed right now, so I'm really sorry for the, I think for 1 hour like the quality was distorted. So now it's okay, and like I hope like I'm thankful that you're patient, you have watched throughout that bad quality. So let's restart where we. So I was telling that the critical clearing time you will not be able to find out, right? Because here your PA is not constant. Okay, so where was I writing the critical clearing angle? Yeah, here only, right? So here you will be able to find out critical clearing angle, but here you will not be able to find out critical clearing angle because your PA is not constant. So one more where is it, conclusion that I want to talk about the critical clearing time, that if, only if, so critical clearing time TCR will be equals to this, like whatever formula we derive, right? This has a condition attached to it. What is the condition? Condition is PA is constant. PA is not a function of delta. Okay, that is the condition that has been attached. Okay, please be careful. So here I will write a note here that PA is constant. If PA is not constant, then there will be problem, right? If PA is not constant, I will not be able to use this equation. This equation is not valid because PA itself is varying with respect to delta, right? So this equation will not be valid. Okay, just be careful regarding that. Where were we? So yeah, we found out our delta CR. We will not be able to find out our this F2 you will find out. This is homework. Okay, now let's move on to the next question. I think this is the last one. So, and also one more topic we will do, that is the frequency of oscillation. Okay, so now what are they telling, that if I have we have to find out the expression for the okay, not delivered, right? We have to find out the expression for the power delivered. Actually, this should have been power delivered for a three-phase fault at point F1 and F2. Okay, okay, this is actually fairly straightforward. What are they asking? We have to find out the expression of power delivered by the synchronous generator, right? At if the fault occurs at point F1 and F2. Okay, so H and F are actually are not any use to me, right? Because we will only be able to find out the critical clearing angle. So power, okay, so so here what is the power delivered? So if I notice at the, like, the fault is occurring at the terminals of the generator, what is the power delivered here? What is the power? So if some fault is occurring here, what is the equivalent circuit, right? If some fault is occurring at F1, then will the PE be 0? Okay, will the PE be 0? That is what I am trying to identify. So let's first take the case 1. If the fault is occurring at F1, so what will be the equivalent circuit? Equivalent circuit will be, here I will have the generator reactance, right? Then directly this is short circuited, right? The bus end is short circuited directly. Then this I can totally write the equivalent reactance. This will be what? This will be basically J 0.3, J 0.7. So this is some Jx, right? Jx equivalent, I don't care, right? And then here I have one angle delta. This is the generator reactance, right? That is J 0.04. And here it is one angle 0 degree. Okay. So here fault is occurring. So the voltage at these two nodes are fixed. The voltage at these two nodes are fixed. The voltage here is 0, voltage here is 1. So I will be able to find out the power delivered, right? Because if voltage is fixed, I will use my formula. What is my formula? PE is equals to 1 into 0 divided by whatever is the reactance, 0.04 into sine of delta. So luckily I see that it is 0. So it simply comes out to be 0. Right? If fault occurs if at one of the burst terminals, then PE always will be 0. So this is also a very important thing to note. Okay. So this will be case 2. So case 2, when fault occurs at F2, if fault occurs at F2, so if fault occurs at F2, what will happen? If fault occurs at F2, basically what can I say? I can say that your fault is occurring at F2. If fault is occurring at F2, then again if I draw the equivalent diagram, I will have some, so between this point, between the before the generator terminals and this point, right, I can totally convert this reactance into some equivalent reactance, right, Jx, and this point is totally short circuited. It is not 1 angle 0 anymore, it is totally short circuited, right, and this point is 1 angle 0, right, 1 angle delta. So again the power delivered, right, PE will be simply 1 into 0 because this point is short circuited. So 1 angle 0, 1 into 0 divided by x into sine of delta, again it will be 0 only. So if short circuit fault occurs at the bus, right, this is the bus where the lines are interconnecting and this is the terminal point. If some short circuit fault occurs, PE always will be equals to 0. That is the conclusion. Okay. So like this is very important conclusion that you can, like, it's not like always it will happen, sometimes it may not happen, right? Because if a fault occurs at the middle, you see PE is not going to 0, but if a fault occurs at either sides of the terminal, PE always will be equals to 0. That is also a very important conclusion. This we understood through a question. Okay, through a question we understood the concept. Okay, now let's come to the, like, one more theoretical topic, that is frequency of oscillation of rotor. What is the frequency of oscillation of rotor? That is what we want to derive. Okay, how will I derive it? So we will use it, we will use swing equation, using swing equation. Okay, so if I use swing equation, this will be Pm naught minus, so I know Pm naught minus Pe naught, or Pm minus Pe is equals to m d square delta dt whole square. Okay, it is d square delta dt whole square, right? So I want to find out the frequency of oscillation. So we will see small changes. So let our Pe increase to Pe plus delta Pe, right? Then what will be your change in, small change in delta? So your delta will change to delta plus del delta. Okay. So what I can write down over here is that this will be what Pm, like initially what is your Pm? So it is like, I can write this equation again, this will be equals to Pm naught minus P naught equals to m into d square delta upon dt square, right? And initially this is 0, of course, because P naught is equals to P naught. But as soon as there is a small change, right, as soon as there is a small change from P to P plus delta, this, right, there will be variation of d delta, right? And we want to write this relation, right? So what can I write over here is that your Pm naught will be constant, of course, and there is a small change in the electrical power. Electrical power is P naught plus del Pe. Okay, electrical power is P naught plus del Pe equals to m. Now your delta, so let me write this as P naught, and then let me write this as delta naught. Okay, so that you will understand this better, because it Pe has changed to P naught, has changed to P naught plus delta. So initially when like Pm naught and P naught are equal, so this will be delta naught upon dt. Delta naught is just a constant number that is equal to 0. That's why my Pm naught and P naught are equal, right? But as soon as I change my, this equation always will be valid. As soon as I change my Pe to P naught plus delta Pe, so there will be variation. So it will be delta d square dt square. Delta has also been changed. Delta naught has also been changed to delta naught plus del delta. Okay, no need to remember the derivation. This can be asked in ESE, in GATE, very rare chance of asking this, but still I am covering all the bases here. So this, right, this is a constant, right, this will go away. So, and this, right, P naught and Pm naught are equal, so automatically your, what equation I am getting is that delta Pe, right, delta Pe is equals to m into, again this differentiation is just a constant, this is a function of time, right? The change in delta is a function of time, so I cannot simply make it 0. This will be d square dt into del delta, right? So this is the change in delta angle, that is a function of time. Okay, that is a function of time. Okay, now again negative sign will be there, because I forgot to write, there is a negative sign here. Now what can I write this? This can be actually written, this is just a constant number, right? This is just a constant number, that is a function of time. This is a function of time. Okay, now what can I write this? What is this actually? This actually del PE can be written as delta PE upon with differentiation of dP upon d delta into del delta at when my delta is around delta naught, because there will be very small variation. Okay, I know this is a bit tricky to you. Ignore the derivation. Okay, ignore the derivation, not that important. But if someone has studied bit of partial differentiation, they will understand these things. Okay. Okay, so I will replace this equation actually. I will replace my delta P here, right? So if I replace my delta P here, what will happen? That this equation will be formed that m d square del delta, right, which is a function of time itself, into dt plus delta PE, that is dPE upon d delta into del delta at delta equals to delta naught. Okay, now this is equals to 0. So can I convert this into Laplace format? Can I convert this into Laplace format? Yes, I can. So what I can say is this value, right? Delta P upon del delta at delta equal to 0 or delta equals to delta naught is just a constant. So I can write this as K. Okay. So your equation will be formed like this, right? So equation will be m d square delta, right, upon dt. So this is the dt square plus K into del delta equals to 0. So if I convert this into Laplace domain, this will be m s square into delta of s, right? Delta of s plus k into delta of s, correct? K into delta of s equals to 0. So I have to find out the frequency of oscillation when it is oscillatory, right? When it is oscillatory, then you will not have any. When system will oscillate, system will oscillate when it is marginally stable. Okay, this you will learn in control system, marginally stable, right? So your what I can tell here is that this will be, if I take common delta of s, right? Delta of s I will take common, right? So basically the roots I have to replace, like this will be the roots, right? Delta of s into m s square plus k, right? So if the system is marginally stable, basically s will be replaced with j omega. So you will see minus of omega square will be equals to k minus of k upon m. So you will directly say that omega, your frequency of oscillation, right, omega will be equals to under root k by m. Very famous equation actually. This is equals to, what is k? K is equals to, this is useful for ESE, not useful for gate. Okay, k will be equals to del P upon del delta at delta equals to delta naught divided by m. Okay, important for ESE, not important for gate. Okay, just remember it as a formula. So it's my work to do the derivation. If you did not understand the derivation, ignore the derivation. Okay, because no one will ask you. Okay, so yeah, let's do one basic question on frequency of oscillation, and then we will finally wrap up today's lecture. Okay, so we have been given a like a 50 hertz synchronous generator, right? 50 hertz synchronous generator. Okay, whose generator reactance xg is 0.3. Transmission line reactance xl xtl is j 0.2. both no load terminal voltage of the generator and the infinite bus voltage are 1 pu. Okay, so both the no load terminal voltage and the infinite bus voltage are 1 pu. So basically your Eg, so here like I will draw the system basically. So I will have a Eg angle delta, then I will have Vt angle 0. So both the voltages are 1 pu, right? That are telling me this is 1 angle 0, 1 angle delta, this will be 1 angle delta naught, and this will be 1 angle 0, and the xg is already given, xl is I have already written. Now the generator has an inertia constant of 3 megawatt second per MVA, right, which is basically 3 megajoule per MVA, right? Inertia, that is H, is given to me, that is 3 megajoule per MVA. If the generator is loaded 75% of its maximum power transfer capability. Okay, so what is the maximum Pmax power transfer capability? Pmax, so I have to find out delta naught. So delta naught will be simply sine inverse Pm naught or P naught upon Pmax. Okay, so they are telling me that I am operating at 75% of the maximum. So P naught will be what? I don't even need to calculate the Pmax. P naught will be 0.75 Pmax, right? So it is working at 75% of the maximum capability. So this will be sine inverse 0.75, right? .48 0.6 48.59 degree. Okay, now they're telling me a small disturbance is introduced, determine the new natural frequency of oscillation. So what is the natural frequency of oscillation? Okay, natural frequency of oscillation, right? So your natural frequency of oscillation is omega n. So this is actually omega n, natural frequency of oscillation, right? Also known as undamped frequency. If there is no damping, how it will oscillate. So omega n, right, is this formula basically. Omega n is, like I will directly use the formula, that is dpe upon d delta upon m. Okay. So what is dpe upon d delta? What is dpe upon d delta? So dpe upon d delta, right? What is my p? P is simply Pmax sine delta, right? So dpe upon d delta will be what? Remember, there is delta equals to delta naught as well, right? So dpe upon d delta will be equals to Pmax cos delta, and at delta equals to delta naught, this will be Pmax cos delta naught. So what is my Pmax cos delta naught? So cos delta naught, right? Delta naught is what? Delta naught is 48.45. What is Pmax? So Pmax, for Pmax, what will be Pmax? So Pmax will be the terminal voltage divided by the reactance, right? Overall reactance, that is 0.3 plus 0.2, that is 0.5. So this is 2. Pmax is 2. So this will be 2 into cos of 48.59 degrees. So cos of this into 2 comes out to be 1.32287. Okay. Now what is m? M is equals to, like in per unit, right? M is equals to h upon pi f. Okay, all the units will be sorted, don't worry, automatically. This is just a formula based question. Frequency of oscillation, it will come in ESE, it will not come in gate. So it will just a formula based question. So h, it is given to me, that is 3 megajoule per MVA, right? H is given to me 3 megajoule per MVA divided by pi, okay, it is in radian, okay, into f, that is in by second per second, that is 50, right? So I will replace here, right? I will replace all the values here. So this will be 1.32 1.32287 into pi into 50 divided by m. M is equals to 3, and already that is there, under root. So this is omega n, but they have asked the frequency of oscillation in hertz, right? So I have to actually find out Fn. What is Fn? Fn will be 1 by 2 pi of this, right? Because this is radian per second, so it will be 1 by 2 pi. So this will actually be, if I divide by 1 by 2 pi, right? So automatically this will be, another pi will come here, right? Basically this pi will come. Anyways, I will directly calculate. So this value will be 1.32287 into pi into 50 divided by 3 whole under root divided by 2 divided by pi. 1.3248 hertz. Okay, so this will be the answer for this question. This is the frequency of oscillation. Now, is this important? No, forget, this is not at all important. Okay, so for ESC this can be important, so that's why I had to solve a question. So I solved a question. Okay, so that's it for this lecture. In the next lecture we will actually do the whatever was decided in this lecture, what we will do. So a few more theoretical topics are there, we will solve those, and then obviously we will solve the assignment problems. Thank you, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. So today we will start with lecture 17 of our power system. So today we will discuss actually the equivalent inertia constant of two machines. Okay, if two machines are connected, if they are swinging together or if they are not swinging together, what do I mean by swinging together? I will explain, right? And what are the different methods to improve the stability, right? Both the transient and the steady state stability, and also we will do questions. So first of all, what is the equivalent inertia constant if I have two machines, right, and both of them are swinging together, or both of them are coherent, right? What does swinging together means? So here I have one machine that is swinging like this, and here I have other machine that is swinging, like both of them are swinging together. So basically the delta of t is same. So delta 1 of t equals to delta 2 of t. So the swing of both of them are same, right? Basically that means their, sorry, not delta 1 of t, sorry, their change in delta 1 of t with respect to time, right, is same as d delta of 2 with respect to time. Their initial position might be different, but they're swinging in, like initially this is like this, right? Two machines, but once it swings to right, this also swings to right. If it swings to left, this also swings to left, right? Initial positions are different, orientations are different, right? But if it swings in the clockwise direction, this also will swing in the clockwise direction. If it swings in the anti-clockwise direction, this also will swing in the anti-clockwise direction. So their d delta upon dt is same, right? That is what we mean by swinging together. If their d delta upon dt is same, what do I mean? I mean then their double derivative also will be same. That means their d square delta 1 of t dt square will be equals to d square delta 2 of t dt square, right? So what is the swing equation for the, so here I have Vt. What is the swing equation for the machine 1 and what is the swing equation for the machine 2, right? So the swing equation for the machine 1 is P m1 minus Pe1 equals to m1 d square delta 1 divided by dt square. Okay, so this is my pm1 minus p1 equals to m1 d square delta 1 divided by dt square. Now what is my swing equation for the machine 2? For the machine 2, pm2 minus pe2 equals to m2 into d square delta 2 dt divided by dt whole square. Now if I convert this whole power system into an equivalent single machine, right? So I will convert this into an equivalent single machine, okay, which will have its inertia equals to M equivalent, right? And it will deliver P equivalent, PE equivalent, and it is taking in power as PM equivalent, right? Am I correct? So what is the input equivalent power to this whole system? It is PM1 plus PM2, because individually I am giving the machine 1 power as PM1 and individually I am giving the machine 2 power as PM2. So PM equivalent. So what is the swing equation of this equivalent circuit? It is PM equivalent minus PE equivalent equals to M equivalent into D square delta of T divided by dt square. Okay. Now, if what is ME equivalent? I have already discussed what is ME equivalent, PME equivalent, right? It is simply what is the overall power I am giving input. What is the overall power I am giving input, right? So it is equals to PM 1 plus PM2. Now what is P equivalent? So P equivalent is equals to P1 plus P2, that is the overall equivalent output power, right? So together they are giving P2 plus P2 plus P1, right? So where can I find it? So if I add these two equations, let me write this as equation 1, right, and equation 2. If I add these two equations, 1 plus 2, what do I get? I will get basically PM1 plus PM2 minus P1 plus P2. So PM1 plus PM2 minus P1 plus P2 equals to M1 d square delta 1 dt square plus M2 d square delta 2 divided by dt square. Now I have told you system is coherent. That means they are swinging together. If they are swinging together, their d delta 1 dt is same. Or also I can say what is d delta 1 dt? D delta 1 dt, if you remember, right? If you remember, it was equals to omega r minus omega s. So basically, in other words, I am telling you indirectly that if they are coherent, their relative speeds are same at a particular time instant. Okay. So d delta 1 upon dt and d delta 2 upon dt are same. That is equals to, let me write it. It is equals to basically d delta of t upon dt. Okay. So here this is same as d delta upon t, this is same as d delta upon t. So this will be equals to m1 upon m2 into d square delta t square. Okay. So this is equals to what? This is equals to my PM equivalent, right? and this is equals to what? PE equivalent. Okay, and this is my d delta upon dt, and what will be this equal to? So this will be equals to my M equivalent, right? So equivalent M of the system will simply be added. It's like a series connection, right? Okay, so your M equivalent, like this is not derived for only two generators. If I have multiple generators, right, if I have more than two generators, then also this equation always will be valid. So your M equivalent, right, will be equals to M1 plus M2 plus M3 and so on, right? Whatever amount of generators I have, it will be equals to that. Now this is one of the formula if they are swinging together. Okay, another formula is there regarding H equivalent. So what will be H equivalent? I know M is equals to what? M is equals to GH equivalent upon GH upon pi f, right? So it will be equals to, if the generator ratings are different, right, then they will not be in series, then this equation will change basically. So M equivalent will be equals to G equivalent, overall G of the system, right, into H equivalent divided by pi f. Okay, and obviously pi and f of all of them are constant, so this will be equals to, this G equivalent is the overall rating of the system, right? This will be equals to G1 H1 by pi f plus G2 H2 by pi f plus G3 H3 by pi f dot 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 dot. Okay, or I can write this as, so my H equivalent will be what? Basically H equivalent will come out to be like, basically G equivalent into H equivalent will come out to be this formula G1 H1 plus G2 H2 plus G3 H3 and so on, right? And it will go on. Okay, so this is what my G equivalent into H equivalent is, right? So I hope you have understood this point. I hope you have understood this point. Okay, now we will do a question. For a power system, the inertia constant are H1 is 1 pu, H2 is 1.5 pu. Find the equivalent inertia constant of the system if both the machines are swinging together. What will be the equivalent? What will be the equivalent inertia constant? Okay, they are asking me what is the equivalent inertia power constant. So what will be the equivalent inertia power constant? So what can I write this? So if I divide by G equivalent, right, let me explain, let me do one thing. Let me assume that G equivalent is the base, right? G equivalent will be what? G equivalent will be the base of the system, right? Base, right? So if I divide by G equivalent on both sides everywhere, so this if I divide by G equivalent, what will happen? G1 upon G equivalent, right? So H equivalent will be G1 upon G equivalent, that is in per unit, right? So it will be H equivalent will be equals to H1 per unit plus H2 per unit plus H3 per unit and so on, right? Okay, if the G is G equivalent, right? So I can derive my H equivalent in terms of per unit values, correct? So your H equivalent PU will be what? H equivalent PU will be what? H equivalent PU will be, if I divide this by G equivalent, right, on both sides, this will be converted into per unit. So this will be H1 PU plus H2 PU plus H3 PU, and it will keep on going, right? So simply that other term goes away. So in per unit, simply the inertia constant H will simply be added. So as they are in per unit, I just have to simply add them. If they were not in per unit and the G1 and G2 also were given, then I have to individually find out G1 and G2, and I have to find out the overall system G, and then I have to divide. Okay, if they are given in per unit, I don't need to do all this, right? I don't need to do all this. Okay, I think in the next question only, yeah, next question only that example is there. So in per unit, if they are given, so simply what you will do, your H equivalent will be simply H equivalent in per unit will be equals to H1 pu plus H2 pu. So this will be equals to 1.6, 1 plus 1.5, right? So this will be 2.5 pu. This will be the answer. So basically this formula, right, is only valid when the base ratings are not given. Base ratings are not given. Okay, but use this formula when generator ratings, not base ratings, sorry, generator ratings are given. And this kind of question will be asked in ESE. This is like, this kind of question will not be, will never be asked in GATE. Okay, given generator ratings are not given. Okay, so here if generator rating is given, so what will be my, I will equate with M1. So M1 will be equals to what? M1, M equivalent will be M1 plus M2 and so on, right? It will be added. So here I have two machines, so it will be M1 plus M2. Okay, so here they are asking me find the equivalent inertia constant of the system if both machines are swinging together. Okay, if I forgot to add this line, that if both machines are swinging together and the equivalent rating of the system is 250 MVA. Okay, this has to be given, right? G equivalent has to be given, right? Otherwise you will not be able to solve, because how will you find G equivalent? So it has to be given, right? So that is the thing over here. So I will yeah, I will, where is it, this one. And the equivalent rating of the system is 250 MVA. Right now we can solve it. So M equivalent will be this. So M equivalent will be equals to what? G equivalent into H equivalent divided by pi f. Pi f will get cancelled simply. Right. This will be equals to G1 H1 plus G2 H2. Okay. So from here I can easily find out what will be my H equivalent. Right. So H equivalent will be G1 H1, G1 H1, G1 is 100 MVA, H1 is 1, so 100 into 1 plus G2, G2 H2, G2 H2 is 200 into 1.5 divided by G equivalent, that is given to me, G equivalent is 250 MVA. So this will be, this value will be what? So this value 100 plus 300 divided by 250, so it comes out to be 1.6. So your H equivalent will be 1.6, right, which is quite different than the previous answer, right? So just be careful when to use what kind of formula. Okay, these are mostly, this will be mostly asked in ESE, never these things, right? This H equivalent, these basic topics will never be asked in GATE. GATE asks conceptual questions, right? In GATE we are asked conceptual, not all this formula rectifying things. So this is important for ESE. Okay, so yeah, these are done. Now if the machines are not swinging together, then what will happen? If the machines are not swinging together, that means that my d delta 1 upon dt is not equals to d delta 2 upon dt. Both of them are not equal. That means basically they are not coherent, right? They are not coherent, or their relative speeds are not same, not coherent. Okay, or the relative speeds are not same. Okay, their relative speeds are not same. So how will I find my so what is happening here? Basically the thing is, there will be some power flow between the two generators, and I want to find that power flow. So there will be like delta 1 of t, basically your change in d delta 1 of t minus d delta of t, right, is not equal to 0. That means d delta 1, like these are not equal, right? So that means this, if I take this on the left hand, okay, just hold on. If I take this on the left hand side, right, this will be minus d delta 2 upon dt is not equal to 0. If I integrate on both sides, right, if I integrate with respect to time, what I can say is delta 1 of t minus delta 2 of t, right, if I integrate this, is not equals to 0, right? I'm integrating, it is not equal to 0. That means there is some phase difference, there is some power flow. Whenever there is angle difference, there has to be some power flow. So there is some power flow between the generators. Okay, this time what will be the equivalent delta? So the equivalent delta will be actually, so this will be my equivalent delta basically. So the difference is the equivalent delta, right? Because this is providing some, yes, some power is going to the line Vt angle 0, that is correct, but I am not concerned about that. I am concerned what is the power that is flowing from here to here. Okay, that is what I am concerned about. I will also explain why am I concerned about this. So again I will write down two equations, right? What kind of two equations? I will write down the swing equation of machine 1. Swing equation of machine 1 will be Pm1 minus Pe1 M1 d square delta 1 of t upon dt square, and Pm2 minus Pe2 equals to M2 d square delta 2 of t upon dt square. Okay, now I know, of course, right, we know this, that what is my equivalent delta? What is my equivalent delta here? That is what I am trying to find out, because there will be some power flow. Okay, so this will be difficult actually to calculate. Okay, so what you will do is my equivalent delta, right, like your d delta upon dt this time around, this will be equals to, because there is a phase difference, I want to measure that phase difference, and that will be the equivalent delta, like differentiation of delta. So that will be d delta of dt minus d delta 2 of dt, right? This again is important for ESC, not for gate. For gate you can totally ignore this. For gate you can totally ignore this discussion. Okay, so this will be equal to this, right? So now I can say, so if I differentiate this again, right, so this will become d square delta of t upon dt square equals to d square delta 1 of t dt square minus delta 2 of t by dt square. Okay, so if I now do this, so what is my d square delta 1 by dt? So d square delta 1 by dt will be this, and d square delta 2 by dt will be this, right? So now I will simply subtract these two, because I want to compare with the equivalent, like I want to find the what is delta, because I want to compare with my equivalent equation. So that will be Pm equivalent minus Pe equivalent equals to M equivalent into d square delta of t dt square. Okay, I know this is the boring part, like you guys can skip this derivation, this is not important, this will never come, this will never come in ESA as well, this will never come, this will in gate as well, this will never come, but we have to teach, right? We have to teach everything. So this will be equals to yeah, so now I will do the subtraction here, right? So if I subtract these two equations, right, 1 and 2, if I subtract these two equations, what do I get? I get Pm1 minus P1 divided by M1, right, minus Pm2 minus P2 divided by M2 equals to d square delta by dt square, right? So here this will be M1 M2 into M1 Pm1 plus minus Pm2, okay, into this will be M2, this will be M1, right? Minus this will be M2 P1 minus M1 P2 divided by M1 M2, okay? So this I can rewrite, right? This can be rewritten, right? I will multiply M1 by M2, okay, on both sides and divide by M1 plus M2, right? So this will become, I'll reduce the size over here, okay, I will copy this. What will I do is I'll multiply by M1 by M2 on both sides. So this will become M1 into M2, right? Here it will be M1 into M2, and then I will divide by M1 plus M2 on both sides, M1 plus M2 on both sides, okay? I will multiply by this term on both sides. If I multiply by this term, what will happen is this will be M1 plus M2, and on the other side also M1 plus M2 will be there, right? So now I will reduce this size, okay, I will increase this size, I will increase this size. Now if I see that simply what is happening is that here my just hold on, that I will put this here I have space, right? So this will be basically, if I so what is this equation? So this is my P equivalent, so this is my Pm equivalent, right? This is my Pe equivalent, and this is my M equivalent. So what is my M equivalent? I can see M equivalent is just a parallel combination. It is just a parallel combination, right? So M equivalent is basically, if I take the inverse of this, 1 by M equivalent, right? This is my M equivalent, right? So 1 by M equivalent will be equals to, if I take the inverse, it will be simply 1 by M1 plus 1 by M2. It is similar to parallel combination, right? So similarly, if I have other machines connected in parallel, it will be plus 1 by M3, right? And dot 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 dot, okay, it will go on. It will go on. Now similarly, if I have, like, if the ratings of all the machines are same, then G will be same. If G is same, ultimately other terms will get cancelled, pi f will get cancelled. So 1 by H equivalent will be 1 by H1, 1 by H2 plus 1 by H3. So now we will come down to our actual questions, okay? We will finally solve questions. All these things are done. Now the important point comes, okay? So a generator having a H of this, right, megajoule per MVA, H is this, H value is given, right. Another generator of H is given as 4 megajoule per MVA connected through a reactance. Okay, I have two generators and they are connected through reactances. Okay, and the generator is delivering a power of 1 pu to the motor. Okay, sorry, a generator is connected to a motor. Okay, this is a generator and it is connected to a motor, and the generator is delivering 1 pu power. Pe is 1 pu to the motor. When a fault occurs which reduces the delivered power at the time when the reduced power delivered is 0.6, so Pe naught is this, Pe1 during fault it becomes 0.6 pu. Determine the angular acceleration of the machine with respect to motor if the frequency is 60 Hz. They're asking me what is the angular acceleration. So what is angular acceleration? If you remember, what was angular acceleration equals to? So again I will come back to the swing equation. So I know Pa was equals to m into alpha, where alpha was the angular acceleration, right? Okay, alpha is the angular acceleration. So they have given me h, and power is also in per unit, right? So what is your m? M also I will write in per unit. It is equal to simply h by pi f. H by pi f. Now see, it is h by pi f. Okay. So yeah, your alpha also will be, it is not in degree, so it is pi f only. So what will be your alpha angular acceleration? It will be Pa. So what is Pa? Pa will be, remember, a fault has occurred, right? Input to the motor has not changed. Input to the motor has not changed. So what is the input to the motor? Input to the motor is equal to, right? Input to the motor is equals to what? Input to the motor is equals to Pm naught, right? That is equals to P naught initial power. Initially it was stable, so it is 1 pu. And during fault, your Pe1 becomes 0.6. Pm1 is what? Pm1 is 1 pu only. It will not change, right? Now, remember there is some power flow between the motor to between the generator and the motor, right? There is some power flow. If there is some power flow, there is some angle difference. If there is some angle difference, that means they are not in coherent. So both machines, the conclusion is, as there is power flow from generator to motor, right? Hence I can say that machines are not swinging together. Okay, if machines are not swinging together, because I will need to find out the H equivalent of the system, right? I will need to find out the H equivalent of the system. So H equivalent of the system, if they are not swinging together, is simply 1 by H equivalent will be 1 by H1 plus 1 by H2, right? So which is equals to, what is 1 by H1? H1 is basically 1 by 6 and 1 plus 1 by 4, right? So 1 by 6 plus 1 by 4. So this will be equals to 1 by 6 plus 1 by 4, which comes out to be 0.4167. Okay. And I have to take the inverse of this, right? I have to also take the inverse of this. So this will be 2.4. So your H equivalent is basically 2.4 second. Okay. This is your H equivalent, right? But I have to find out the alpha, angular acceleration. So alpha will be basically this H equivalent divided by pi f. So 2.4 divided by pi f, automatically the unit of is also second square, so it becomes second square here, right, into pi into 50, not 50, sorry, 60, because frequency is given to me 60 hertz, and this will be basically what is PA? PA will be PM1 minus P1, that is 0.4. Okay, so this will become this is 6, right, this is 6, this is 6, this is 10, right, so 10 pi, it is basically 10 pi. Okay, and okay, actually this is okay, here E0 basically means E0, they're defining E0, this basically means electrical degree, it is not in radians. So if it is in electrical degree, then I have to convert this pi into 180, right? So this pi will be converted into, because this is per second square, this is radian per second square, because pi is there, right? As pi is there, it becomes radian per second square, but I have to convert this into electrical degree, so this pi will be converted into a 180 degree, right? So this will become electrical degree per second square. Okay, so this will be equals to 1800 electrical degree per second square. So 1800 electrical degree, that is option C. Okay, this kind of question will be asked in ESE, in GATE. दिस लाइक ये भाईयात क्वेश्चन गेट में कभी नहीं पूछेगा, ठीक है, सिंपल स्ट्रेट बता रहा हूँ क्योंकि कोई सेंस नहीं है इसका, इस क्वेश्चन को कोई सेंस नहीं है, ठीक है. तो या दिस इज जस्ट फॉर्मूला, नो कॉन्सेप्ट, जस्ट फॉर्मूला. Okay, but I have to teach everything because you have to crack, maybe you want to crack ESC, right? So I have to teach according to that as well, right? So I'm trying to cover every single base from every exam. Okay, so that is the purpose basically. Okay, another question is there, again it's like kind of equivalent swing only, that for a power system the inertia constants are this, and these are the values basically, inertia constant E1 E2, all these values are given. Okay, find the equivalent swing equation of the system for frequency f equals to 60 hertz. What will be the equivalent swing equation? So equivalent swing equation, they are asking me what will be the equivalent swing equation. Okay, so what is my, if you remember, what was my PM equivalent? What was my PM equivalent? So your PM equivalent was actually equals to, your PM equivalent was actually equals to PM1 into M2 minus PM2 into M1 divided by M1 plus M2. Okay, so also your, what will be your P equivalent? P equivalent also will be same. P equivalent also will be same. So the H1 H2 are given. H1 H2, is it same as G1 G2? Yes, because I have to assume it is same as G1 G2 only, because they have not mentioned anything, right? They have not mentioned about the G. If they have not mentioned about the G, I can assume the G to be same for everyone. So basically my M1 will be what? M1 will be G1 into H1 divided by pi f, correct? I can write this as G into H1 divided by pi f, if I'm not mistaken. So what I will do, this will be, this M2 will be replaced with what? This M2 will be replaced with G by pi f, right? G by pi f into H1 into H2. This will be replaced with G by pi f into H1. So this will be replaced with G by pi f into H1 minus PM2 G by pi f into H2, and at the bottom I will have H1 G by pi f plus GH2 by pi f. Okay, So this value will come out to be equals to, so automatically G by pi f will get cancelled, right? So automatically this will be PM1 into H, sorry, this will be H2, right? Sorry, this will be H2, this will be H1. H2 minus PM2 H1 divided by H1 plus H2. Similarly for PE also this will happen, this will be happening. So PM1 is given to me, right? 1.5 PU. So this will be 1.5 PU into H1. H1 is given to me, that is 4. Sorry, into H2, right? That is 6. 6 minus PM2. PM2 is 1. H1 is 4, right? This will be 4. H1 plus H2. H1 plus H2. H1 plus H2 is 4 plus 6, that is 10. So this will come out to be 1.5 into 6 minus 4 divided by 10. So it comes out to be 0.5, right? So your PM comes out to be 0.5 PU, right? Everything is in per unit. So this also will be in per unit. This is your PM equivalent. Now what is PE equivalent, right? What is PE equivalent? So PE equivalent will be basically the power transfer, right? Whatever is the power transfer, that is my PE equivalent. Whatever is the power transfer. So it will be equals to EF. So here, right, whatever is the power transfer. So E1, E2 upon X sine delta. E1, E2 upon X sine delta. And remember, x1 dash and x2 dash are given. So individually the reactance will be like addition of these two reactants. E1 is given, E2 is given, but delta is not given. How can I find out the delta? But their magnitudes are given. So from this I can easily find out my delta, whatever will be my delta. Delta is not given, actually it will be a function of delta only. You can find out the delta, or can you? Yeah, because this is angle 0, right? You can find out the angle delta, but it has to be a function of delta only, right? So what is the power transfer? Power transfer will be E1 E2 by X sine delta. So that is equals to, what is E1? E1 is 1.1, E2 is 1.1, so E1 is 1.2, E2 is 1.1, and X is basically 0.36. Okay, am I correct? Yeah, X is 0.36. Actually, okay, no, one mistake I have made here. X, the value of X actually is, X is given actually 0.3, right? These are their internal reactants and X is already given, right? So overall what will be the reactance that is connected between these two voltage sources? 0.36 plus 0.3, 0.66. So this will be 1.2 into 1.1 divided by 0.66 into sine delta. Okay, so this will be equals to 1.2 into 1.1 divided by 0.66, right? That is equals to 2. So this becomes 2 sine delta. Okay, so this becomes 2 sine delta. So this is my P equivalent. I know what is my M equivalent, right? What is my M equivalent? Here everything is in per unit, so M equivalent also is in per unit. So I will divide by generator rating, so it does not matter, it will be H equivalent upon pi f. Okay, so which will be equals to, H equivalent is what? H equivalent will be 1 by, H equivalent will be H1 H2 divided by H1 plus H2. Okay, so H1 is given to me, that is here, right? That is given as 4 6, right? So 4 into 6 divided by 10, that is 2.4 megajoule per MVA, whatever is this value, megajoule per MVA. Okay, so this will be 2.4 by pi into 50, right? Now we'll put in the swing equation. What is the swing equation? It is M PM equivalent minus PE equivalent equals to M equivalent into d square delta upon dt square, right? So this will come out to be equals to PME equivalent is, I have already calculated the value, PME equivalent is 0.5 pu. So 0.5 minus PE equivalent, that is 2 sine delta, equals to M equivalent is 2.4 into d square delta upon dt square. So this is the swing equation of the motor. So I hope now like this topic is clear. Like I just had taken few questions, right? So that like I know this is not that important, like this will generally will not be asked in gate, but yes, in this can be asked. So I hope this topic is also cleared. So I am trying to clear every single topic. Wherever you have doubt, I will try to clear every single thing. Okay, sorry, this will not be 50 actually. This will not be 50, this will be 60, right? This will be 60. Okay, so sorry, this is not M equivalent, is not this, right? M equivalent is this by 60. So this will be some very low value, right? This will be 2.4 divided by pi divided by 60. 2.4 divided by pi divided by 60. So it comes out to be into 10 cube. So it comes out to be 12.73. So this will be actually 12.73 to 10 raised to power minus 3. Okay, so this is my equivalent, where delta, remember this, right? Delta is in radians. You have to put delta in radians. If you don't put delta in radians, then this equation will not be valid. Okay, if you put degree, then you have to convert this also into degree. That means your pi will be 180. So now let's come to the next topic, that is how can I improve steady state stability. So we will discuss like all kinds of stability, transient and steady state stability. So in steady state stability, what is the like mainly steady state stability depend on? My steady state stability limit is dependent on the Pmax. Of course, I cannot change the angle. Angle will always occur at 90 degrees only. It depends on Pmax. And what does the formula of Pmax depend on? Formula of Pmax depends on the EF Vt by X, right? So of course, I cannot change the voltages. Excitation, that is not under my control, but this X is under my control, right? So if I reduce my reactance, right, of the transmission line, then automatically the peak will go up. That is the steady state stability limit will go up. So stronger, like we can increase the excitation, right, but that is a tedious process, right? We don't generally follow it. We can increase the terminal voltage, again we will not change the terminal voltage. Terminal voltage is constant. Okay, so what we can do, we can reduce the reactance. So there are many ways to reduce reactance. One of them is by using bundled conductors. Okay, what is bundled conductors? So bundled conductors reduce line inductance and increase surge impedance loading. Okay, but like I will not explain here. Bundled conductors we will study in PSA 1, right, in transmission line parameters. There if I use bundle, like I will have many conductors together, bundled together, right, and they will form a single conductor. Okay, and currents will flow via these paths, many conductors, many small conductors. So what will happen basically is that it will improve the steady state stability. Why? Because the inductance of the overall, if I just would have used a single conductor without bundle, right, L1, and let's assume that here the inductance is L2, the inductance L2 will be lower if I use bundle conductor than L1. Hence your reactance also will be lower than L1. Hence of course if your reactance is lower, your line reactance reduces, hence it will improve the steady state stability limit. Also, it will help reduce the corona loss that we will discuss in the like basically in the transmission line parameters, not here. Okay. Now, if I add a series capacitive compensator, okay. Now this is not preferred, right? If I add a capacitor, right, in series with the inductor, what will happen? If I add a capacitor in series with the inductor, basically it will reduce the overall reactance of the system, because already there is some inductance. Overall reactance will become X minus Xc. So overall reactance will go down. So your power will improve. Okay, that we know, right? But we actually don't prefer it, because due to the subtransient resonance, right? There can be what can happen? What can happen? We know at resonance, like at resonance, what happens? XL becomes XC, right? So there is a probability of resonance condition happening here, and you know at resonance what happens? Either your voltage goes very high, or your current goes very high. So there is a possibility, because at some frequency, because we know that during fault the frequency also like is very high, because your waveform changes very fast, right? So maybe at some frequency, your XL becomes equals to XC, and at that frequency what will happen? Resonance will happen, and if resonance happens, it will further amplify the current or voltage. Further it will amplify, because we know at resonance we amplify voltage or current, right? So due to this fault, right, fault frequency, I don't know what is the fault frequency, it can be anything. During fault the cycles move very fast, so due to this fault frequency the XL might be equals to XC, and we can get a resonance condition which is very dangerous. Okay, by using, like, this is the most preferred one, by using parallel transmission line. So if I have only a single transmission line, let's say initially it was, we are providing what was the x only, right? If I have two transmission lines, now what is the overall x of the system? X by 2. So x has reduced, hence the steady state stability limit will also improve. Other way also we can understand, I took an example, right, for the transient stability, that if I have two transmission lines, if I have two machines, right, then also the transient stability will improve, right? So here I have two transmission lines, so if some fault occurs here, right, still I can send the current through here. So intuitively also you can understand that it is good basically. So basically it is good that it is improving the steady state stability limit. Last one is the static VAR compensator. This is also used, mostly used in today's real world. So mostly used nowadays, right? So if you remember, I used to tell you that if I have controlled this voltage, right, I cannot directly find out the steady state stability limit. I have to individually find out this Pmax, and then solve accordingly, right? So what we'll do with the help of static VAR compensator. Why static VAR compensator? I know that the reactive power controls the voltage, right? This much information I know. So if I use a static VAR compensator, that how much of reactive power is required by the load, if I am providing by myself, right, then I can control the voltage at this node. If I am able to control the voltage, then I will be able to control my Pmax 1, right? Pmax 1 and Pmax 2, and from there I can calculate whatever is the required steady state stability limit. Okay, so basically individually I will control my Pmax 1 and Pmax 2. It will depend on what? It will depend on this V, it will depend on this Vt. So I have introduced a extra variable V through which I am controlling the steady state stability limit of the line. Okay, so yeah, this is how we can improve our steady state stability limit. These are the 5 methods. Now let's discuss about transient stability. So I know transient stability depends on this swing equation, right? So how can I improve? So transient stability, right, we already know that my TCR is proportional to under root of m, if you remember it properly, right? So if TCR is proportional to under root of m, I have to, I need more time to clear the fault. Everyone needs more time. You need more time to study. Like if I say you that tomorrow is your mathematics examination, you will say, no sir, at least give 2 days, at least give 3 days. So everyone needs more time. So here also we need more time to clear the fault. So which will provide this inertia? If I increase the inertia constant, okay, of the machine, then I will get more time. So increasing the rotor inertia or H constant will help me in increasing the steady state stability limit. Okay, so designing generators with higher inertia allows them to resist sudden changes in speed. So speed changes will be slower, right? So this is the first way with which we can improve our transient stability. Next one is damper winding, because I know during transient there will be many oscillations. Who helps reduce these oscillations in delta? Damper winding, because damper winding just opposes the oscillation. It produces a torque that opposes the oscillation. It induces an EMF that depends on how much the oscillations are. If the oscillations are very high, the induced EMF also will be very high in the opposite direction. So damper winding opposes the oscillations. Okay, I hope it is clear. By using flywheels, so what are flywheels? So flywheels are nothing but like they are just used to store the extra mechanical kinetic energy that the input is providing. So I will connect a flywheel. Okay, flywheel will just be a rotor kind of thing, right? That will actually store, I told you, right, additional kinetic energy we provide, because the generator is delivering some electrical energy, suddenly it has reduced and the input is still constant. So that additional energy delta, right, which the generator had to store, now it will be stored in flywheel, right? So additional kinetic energy will be stored in flywheel, which will keep the delta of generator to be constant. Okay, now single pole switching. What do I mean by single pole switching? Okay, so what happens is that, let's say it's like whatever we send three-phase supply, right? So I have my generator over here, correct? Now I will not draw the single line diagram, I will draw the three-phase diagram. If I have a generator over here and there is three phase, right, A, B, C, okay, and then here I have my circuit breaker. Okay, and after this I have my load. Right, so what do I know? I know this, that my let's say a fault has occurred in phase C. So if a fault has occurred in phase C, what will happen? It will simply trip, as it's a three-pole circuit breaker, right? It will simply trip all the lines. So this circuit breaker will trip all the phases. Hence your PE will totally go to zero. Your PE will totally go to zero. But if I use single pole circuit breaker, right? This is a three-pole circuit breaker. Let me do one thing. Bigger. Now I have a single pole circuit breaker. Okay, so if I have a single pole circuit breaker, what will happen? If I have a single pole circuit breaker, then the circuit breakers will be connected like this. I will have the lines, and in each phase I will have circuit breaker. Okay, each phase I will have circuit breaker. This will be, let's say, circuit breaker of A phase, circuit breaker of B phase, and then I have circuit breaker of C phase, right? Then I have the load connected over here. Okay, then I have the load connected over here. So now if a fault occurs in this phase C, right, I have A, B, C. If a fault occurs in this phase C, then simply this only this faulty line will be removed. Now what is the power output of the motor this time? So PM naught is basically PE by 3 plus PE by 3 plus PE by 3, because individually it is sending power to three phases, they are balance supply, right? So if they are balance supply, what will happen then? I will just remove this circuit, right? So still PE1 will be what? PE1 will not be absolutely 0. Here PE1 was 0 because I had to remove the whole three phases, but here PE1 will be equals to PE1 will be equals to 2PE divided by 3. Okay, 2PE divided by 3. Yeah, so now what the thing is, your PE does not reduce, PE does not go to 0, so your difference PM minus PE or your accelerating power actually reduces, right? Accelerating power reduces. So if accelerating power reduces, that means your d square delta upon dt square reduces, that means your oscillations reduce, oscillations will reduce, right? So that is the advantage of using three pole circuit breaker, but there are many disadvantages as well, right? So which we will not discuss here. Okay, oscillations will reduce. So like we can use three pole, like it's good to know that we can use single pole circuit breaker to remove the transient, like to improve our transient stability. Okay, and the last one is fast acting governor. So governor systems quickly regulate the prime mover input to counteract the speed deviation. So here I will control the PM, right? If I sense, right, there will be governors that will sense the electrical power output. So the governors will sense the electrical power output, then they will control the mechanical power input to the generator, they will reduce it, right? So if I reduce it, this also will reduce the accelerating power, that also will reduce the oscillations. Okay, these are few ways with which I can actually improve my transient stability. Okay, so now we will discuss about the summary, like few key points to note here, right? So we derived a formula delta T equals to delta naught plus PA by 2m T square. This we already know. So this can also be written as delta naught plus half alpha T square, because what is alpha? If you remember what is alpha, alpha is simply what? This was the formula, right? PA is equals to m alpha, correct? PA is PM minus PE, right? So your alpha, like your PA by m, right? PA by m is simply equals to alpha. So alpha is equals to PA by m, or PA by m is simply equals to alpha. So I can replace alpha over here. I can replace alpha over here with PA by m, right? And then of course I have all these things are same. Now one more key point to note here, this formula is only valid when PA is constant. So only valid when PA is constant. Basically your acceleration is constant. If your acceleration is not constant, then this formula will not be valid. Okay, now this already we know that this is PA equals to md square by dt square. This is the swing equation of generator. For a motor it will just be opposite. Why? Because for a motor, what do I give as input? I give electrical power as an input, right? So that's why electrical power will come first, then the mechanical power. Okay, this generally will not be asked, but it's good to know what is the swing equation of a generator, what is the swing equation of a motor. In here, what is m? M equals to gh by pi f, right? H is the inertia constant, megajoule by MVA. Now this pi, I have already mentioned this, that we can either write this in pi only if everything is in radians, if delta is in radians. If delta is in degrees, then I have to replace this pi with 180 degrees. Then I have to replace this pi with 180 degrees. Okay. Okay, that way that is clear. H is this formula. What is kinetic energy? It is megajoule by MVA. So it is kinetic energy stored in the generator by the rating of the generator. So that is equals to half J omega m square divided by g. Okay, so yeah, that is what my so one thing, so here write omega m square. You don't have to calculate ns and then convert it back into omega m. I know what is my omega m. Omega m is 2 by p into omega I, basically the relation between electrical and mechanical angles, that is equals to 2 by p, 2 pi f equals to 4 pi f by p. Okay, so I hope that is clear now. So yeah, that is what my omega m is equals to. Okay, so yeah, these are the few things to note here. And another thing, what is my torque? Torque is equals to I alpha. It is similar to in the rotational, in the linear motion. In the linear motion, what was my torque equals to? Torque was equals to your mass, not torque, sorry, your force. Force was equals to your mass into acceleration, correct? But in rotational motion, we don't have anything known as force, we have torque. So it is basically the rotational force, right? So torque will be equals to mass in like mass in rotational motion is inertia, and alpha is the acceleration, angular acceleration, right? So this can be written as alpha will be dw by dt will be equals to I small change in delta w by small change in delta t. Now why am I telling this? This will be used, right? This formula can be used, this formula can be asked, okay, using like a concept can be asked using this formula. So it's good to know this formula. What is power? Power is simply 2 pi nt by 60, okay, that is equals to omega m into t. So power is omega into t, that does not change, that will remain constant, okay. So just like in linear motion, what was the power equals to? Power was equals to your force into velocity. Like why constantly I like try to relate everything with linear motion? Because I know you remember the linear motion formulas. I know you remember the linear motion formulas, but I know you tend to forget the rotational motion formulas. So if you ever tend to forget the formulas of rotational motion, just write down the linear equation, right? Their equivalent linear motion formula, and then from there you write the rotational motion formula. So I want you to build this habit, because there are so many formulas, you have to make a way to remember. How can you remember these things? That's how you can remember these things, okay. So yeah, now me alpha, so alpha, right? Alpha, the unit of alpha can be anything, okay. By default it will be electrical radian per second square, okay. So if it is electrical radian per second square, you will replace your pi with pi. Wherever there is pi, you will replace with your pi with pi, just like here I replace my pi with pi if it is in radians, electrical radians. If it is in mechanical, if it is in electrical degree, I will replace my pi with 180. I will replace my pi with 180 if it is in electrical degree, right? Here if it is in electrical degree, I will replace my pi with 180. If it is in mechanical degree, I will replace my pi with not this, theta m. So what will be theta m? So I know this formula, right? I know this formula, theta e equals to p by 2 of theta m, right? And I know electrically it will be 180 degrees, right? Electrically pi will be 180, but mechanically it will be 2 by p. So I will replace everywhere theta e with 2 by p into theta e if it is in mechanical. I will replace my theta e equals to p by 2 of theta m. I will replace my theta e, wherever there is theta e, right? I will replace it with p by 2 into theta m, okay. So I hope it is clear. I hope things are clear here. So just take care of the units, that's the conclusion. Like you might get confused with units, that's why, right? So now conversion of alpha to rotational per minute per second, right? So your alpha, right? Alpha is per second square, like radian per second square. It can also be converted into what? Omega per second. So alpha is d omega by dt. Alpha is d omega by dt. So it is speed by second. So that is what is written. Speed is the rpm by second, right? Now this rpm, this is in radian per second, but this is in rotational per minute. So omega is radian per second, but 2 pi n by 60 is like n is rotational per minute, right? So if I want to convert my alpha from radian per second square to rotational per minute per second, rotational per minute per second, how will I convert it? Okay, so I know this, right? That we will use this formula simply. So omega equals to omega naught plus alpha t. So again the same formula, that my v is equals to u plus at, right? Linear motion formula. So omega is equals to final velocity equals to omega naught plus alpha t. So if everything is in radian, if everything is in rotations per minute, right? Then alpha also has to be in rotation per minute, right? So alpha is equals to omega minus omega naught divided by t. So how will I convert it? How will I convert my alpha from radian per second to this rpm per second? So here, how did I convert my omega from radian per second to rpm per second? What did I do? I just simply multiplied 2 pi by 60, right? So what, like if I want to put here rpm, right? Like if I solve this equation, what will I get? My alpha will be equals to omega minus omega naught divided by t, correct? So omega minus omega naught has to be in rpm and t has to be in seconds. Then only I will be able to convert into rpm per second, right? So here I have to convert my omega from radian per second to rpm. How will I do it? So I will cross multiply here. I will get my n value. N value will be 60 into omega divided by 2 pi. So if a value is in radian per second, right? If I want to represent it in rpm, I have to multiply this factor. If a value is in radian per second and I want that value in rpm, I have to multiply by 60 by 2 pi. Does it make sense? It does make sense, right? So this is in radian per second. Radian per second. So I have to find out revolutions per minute. Revolutions per minute. So it is moving. So how many radians is one revolution? So one revolution is 2 pi radians, correct? So how many radians is one revolution? How many radians is, like, 1 radian is equals to how many revolutions? It is 1 divided by 2 pi, right? So your radian will be replaced with 1 divided by 2 pi. So have I replaced 1 divided by 2 pi here with omega? Yes, 1 divided by 2 pi is here, right? 1 divided by 2 pi. And how many, like 1 second equals to how many minutes? 1 divided by 60 minutes, right? Because a minute consists of 60 seconds, so it will be 1/60 of a minute, right? So I will replace my 1 second in the denominator with 1 by 60. So simply I will replace my radian with 1 by 2 pi and I will replace my denominator, that is seconds, to 1 by 60 to convert it into minutes. So this will be 60 divided by 2 pi, that's it. So this factor you have to multiply to convert any value from radian per second to revolutions per minute, from radian per second to revolutions per minute. Okay, so don't have to mug this up, just understand the conceptual meaning behind it and you will be able to convert this in the examination hall. Okay, now let's solve this question. A round rotor generator with internal voltage E1 equals to this. So E1 is this, right? 2 pu, X is 1.1 pu, connected to a round rotor synchronous motor with E2 equals to 1.3 pu, right? So I will draw the circuit over here. I will draw the circuit. I will have E1, right, that is 2. I don't know the delta yet. They have not mentioned me the delta. The reactance is 1.1 and here I have a motor. Okay, its internal EMF is 1.3 and it has to be like some angle. I don't know what is the angle right now. Let me name this as delta G delta M. Okay, and its reactance is 1.2. Now the reactance of the line connecting the generator to the motor is 0.5 pu. So in between them they have another reactance that is connecting these two, like this generator and this motor is J 0.5. okay. When the generator supplies 0.5 pu of power, so power supplied is 0.5, the rotor angle difference between the machines will be, so if this is delta G, if this is delta M, right? So what is the power formula? Power formula is equals to E1 E2 divided by 2 overall X into sine of the angle difference, delta G minus delta M, delta G minus delta M. Okay, so what is E1? E1 is 2. What is E2? E2 is 1.3 divided by x. X will be overall, this will be 1.2.3, 2.8 into sine. Now, isn't this what they have asked? They have asked me the angle difference. So this is the delta del delta that they have asked actually, and this is equals to, they have given me, is equals to 0.5, right? So from here I can easily find out my, what will be my delta G, del delta, right? So this will be 0.5 into 2.8 divided by 2.6 sine inverse, so it comes out to be 32.58 degrees. So your del delta will come out to be 32.58 degrees. So these are like, this is an old question, so these kind of questions have came like, this is a IT gate question from IT Madras, right? Old question, but still this, like, we are doing this for practice, so we are solving numericals. So like, we have learned the hardest of things, right? Now we are solving numericals, and trust me, the numericals will be a cakewalk to you. The gate numericals will be a cakewalk to you, because we have learned every single thing in full detailing. Okay, so let's solve this next one. A generator with constant 1 pu terminal voltage supplies power through a step up transformer of 0.12 pu reactance. Okay, so I have a generator here. They have not mentioned me the reactance of the generator, but I have a step up transformer here that has a reactance of J 0.12 and a double circuit line to an infinite bus bar. The infinite bus voltage is maintained at 1 pu. So the infinite bus voltage here is maintained at 1 angle 0 pu. They have mentioned it. It has to be reference, so it's infinite bus bar. And generator has a terminal voltage of 1 angle delta. Okay, neglecting the resistance and susceptance of the system. Okay, steady state power limit of the system is 6.25 pu. So they told me, okay, they have not mentioned any reactance in the generator, so we'll assume generator does not have any reactance. And I have the double line over here, and both of the double line has a reactance of X. Okay, next what they're telling me, uh, the steady state stability limit of the power system is 6.25. What do I mean by steady state stability limit? Steady state stability limit is basically the P max, right? Which is the P max of the system. What is the P max? P max is equals to E1 E2 upon the reactance between them. What is the reactance? It is J 0.12 plus X by 2. This is the parallel combination. So this will be 1 into 1 divided by 0.12 plus X by 2. Okay, if one of the double circuit is stripped, then the resulting steady state power limit will be what? Okay, so from here, first of all, I will find the value of X. Now if one of the double circuit is stripped, that means fault has happened, so I have to remove one of the circuit. It is stripped, so I have to remove. So now what will be my steady state stability limit? So this is the P max 1. P max 2 will be what? P max 2 will be simply 1 into 1 divided by the overall reactance, that is 0.12 plus X. 0.12 plus X. Okay, so now from here I can easily find out the value of X. So what will be the value of X? Value of X will be 6.12 into 6.25 0.75, right, plus 3.125x equals to 1. So my X will be what? So this plus 1 divided by 3.125, X comes out to be 0.0 0.08, right? So I will replace my x in this equation. So I will be able to find out my new steady state stability limit. So steady state stability limit new, it will be 1 divided by 0.12 plus 0.08. So this will be 1 divided by 0.2, which is simply 5 pu. So of course your steady state stability limit will be reduced if there is some fault occurring in the line. Okay, so it will be 5 pu. So the resulting will be 5 pu, that is present in the option D. Okay, option D will be the correct answer for this question. Now let's solve this next question. Okay, here bit of normal equation will be used, right? Torque equation. Okay, that's why I have made a summary, made a note, right? So a variable speed drive rated for 1500 rpm and 40 newton meter is reversing under no load. So I have a variable speed drive. So motor, it's a motor. Drive basically means it's a motor. And the rating of the motor is 1500 rpm. Okay, so this is the speed of the motor and 40 newton meter, that is basically the torque of the motor, is reversing under no load. So I am reversing the direction of rotation under no load. Okay, figure shows the reversing torque and the speed during transient. Okay, so previously it was rotating, let's say, in the clockwise direction with speed 1500 rpm, but let's say I want to reverse the direction of the motor. Let's say you are driving a bike, right? But you want to go in reverse direction. So you have to reverse, like first of all, initially your bike is going in the forward direction with 10 meter per second. So it has to reduce the speed. So it has to provide a force in the backward direction. So I want to reverse the direction here. That is 500 rpm. So I have to provide a torque in this direction constantly. It can be constant or variable torque, so that the speed reduces. It's just like force, right? If a object is moving in the forward direction with 10 meter per second, but let's say I want it to move in the backward direction with 5 meter per second, what you'll do, you'll provide a force, right? That will be constant force. Initially it will reduce the forward direction velocity, then again it will increase the backward direction velocity, right? That is the purpose. So here also I am providing a torque in the opposite direction. Okay, the moment of inertia of the drive is, what is the moment of inertia? So again, that's why I told you, right? This physics will be used. Physics will not leave you. So we know that my force, I am observing that it's a constant torque, right? It's a constant torque, right? So when the torque is this formula, right? This formula, whatever we have derived, this formula will be applicable here if the alpha is constant. How is alpha constant? Alpha is constant if basically the torque is constant, right? So here I will use this formula. So I know force is equals to mass into acceleration. So what is the rotational equivalent? It is torque equals to inertia into alpha, right? Have they given me alpha? What is alpha? Alpha is simply d omega upon dt, right? So during this whole period I am actually applying the torque, right? So here what is d omega upon dt? It is basically change in y, that is the speed, that is omega, upon dt, right? So d omega upon dt is what? D omega upon dt, here if I see, it is basically omega f minus omega initial, because it's a straight line I can do like this. It is t final minus t initial, right? So this will be equals to final is 500, initial is minus 1500. So 500 minus of 1500 divided by t final minus t initial. So t final they have not given me, but the difference is given to me, that is 0.5 seconds. This will be 0.5 seconds. Now here you will make a mistake. Remember, this is in rpm, right? This is in rpm, but here everything is in SI units, kg meter square, Newton meter. Okay, so I have to convert this also in SI units, right? It cannot be in rpm. I have to convert this in radian per second. How will I convert? This in radian per second? So what do I know? 1 one rotation, one revolution is how many radians? 2 pi radians. 1 minute is how many seconds? 60 seconds, right? Simply I will multiply. So this is in revolutions per minute. So one revolution is 2 pi, so 2 pi per minute. Per means in the denominator minute. 1 minute is 60 seconds, so I replace it with 60. That's it. That's how simple it is, right? So from here I'll be able to find out my acceleration, angular acceleration. So this will be 2000 into 2, right, divided by 60 into 2 into pi. So this will be 418.88. Radian per second square. Now I will use this in the torque equation. So torque is given to me, it's a constant torque 20 Newton meter, right? So torque is equals to 20 Newton meter, 20 equals to I that I have to find out into this acceleration 418.88, right? So I will be able to find out my moment of inertia, correct? So moment of inertia will be this into 20, so 0.048, 0.048. Everything will be in kg, everything will be in SI units, so kg meter square, which is present in the option A. So option A will be the correct answer. So trust me, in GATE they will ask you conceptual questions, even basic. This is a very basic question, but still trust me, 70% of the students will not be able to solve this basic because their basics are not clear. They are just running behind formulas. And I have seen what they teach in other places, right? They teach only formulas, they don't clear the basics. What was the graph, how the graph moves, what are the important conceptual points. They don't explain when the formula will not be valid. We explain when the formula is not valid as well, right? Okay, so I hope it is clear. Now let's move on to the next one. I think this is the last question for today's. Okay, for today this is the last question, then we will start with the next like in the next lecture we'll do the questions. So a 50 hertz synchronous generator having a reactance of 0.15 pu. So whenever these kind of questions come, right, bigger questions, you start drawing the circuit. Okay, so it's a 50 hertz synchronous generator, right, which has a reactance of 0.15 pu, okay, is connected to an infinite bus through two identical parallel transmission lines having reactance of 0.3 pu each. So I have additional transmission lines, each are connected to 0.3 pu, right? And here I have the infinite bus. Generally the voltage of the infinite bus is assumed to be 1 angle 0. In steady state, the generator is delivering 1 pu power to the infinite bus. So P E naught is equals to 1 pu. For a three-phase fault at the receiving end of the line, calculate receiving end of one line. Okay, receiving end of one line. Okay, so a three-phase fault occurs at the receiving end of one line. What does it mean? What does the receiving end of one line mean? Receiving end means here, where it is receiving the power. It is not sending. Sending means it is sending to the load. Receiving means it is receiving here. What are they telling me? For a three-phase fault occurring at the receiving end of one line. Okay, so receiving end means here, right? This is the receiving end, and let's assume that here the fault has occurred. Here the fault has occurred, right? Calculate the rotor angle at the end of first time step of 0.05 seconds. So they're asking me what is the value of the rotor angle at t equals to 0.05 seconds. First step meaning during the first swing. First step meaning during the first swing. Okay. Assume that the voltage behind the transient reactance of the generator is 1.1 pu. So this is 1.1 pu, angle delta naught, initial angle. Okay, and the infinite bus voltage is 1 pu, and the inertia constant H is 1 megajoule per MVA. Okay, so these are the information that is given to me, correct? Now they're telling me in steady state, assume in steady state generator is delivering 1 pu power for a 3-phase fault occurring at the receiving end of one of the line, at the receiving end of one of the line. Okay, so before fault, pre-fault condition. So let me draw the circuit pre-fault. What is pre-fault condition? So pre-fault condition is here. I will have the reactance here. There is no fault. So this is basically J0.15. So overall reactance will become J0.3, and I will have the infinite bus here, that is 1 angle 0, right? And here I will have the 1.1 angle delta naught. From here I will be able to find out my delta naught, because initially it was delivering power 1 pu, right? So 1 pu. So delta naught, so this will be equals to, right, 1.1 divided by 0.3. okay, and this is here 1, so inverse of this, right, sine inverse. So your delta naught comes out to be 15.826 degrees. Okay, now this is my delta naught, right? So during fault, what is happening? During fault, there is a 3-phase fault at the receiving end of one of the lines. At the receiving end of one of the lines, there is a 3-phase fault. So the circuit, if I draw the circuit, J 0.3, J 0.3, J 0.15, and here I have 1 angle 0, and here there is a fault. If here there is a fault, what will happen? If here there is a fault, what will happen? If here there is a fault, I know, if I have told you, right, if a fault occurs at each end, any ends of the parallel transmission line, the delivered power will be simply 0. I have taught this, I will not derive it over here. I have derived this, right? We have wasted our time, so I will not derive. So here, why? Because this potential is fixed to 0 volt, and these two potentials are fixed. These two potentials are fixed. So what will be the power delivered? It will be 1.1 into 0 divided by J 0.15 into sine of whatever the delta angle is. I don't care. It is 0. So PE becomes 0. PE1 becomes 0. So your, what will be your accelerating power? It will be PM1, which is equals to the previous mechanical power, that is PM0, which is equals to the previous PE0, right? PE0 and PM0 are equal, right? What is it equals to? It is equals to 1 pu. So this will be 1. So your accelerating power is 1, right? And what is your M? M is equals to simply H upon pi f. Remember, because everything is in pu, I will not write G. Okay, so this will be H is given to me as 1, right? 1 megajoule per MVA upon pi. Remember, your pi is 180 because my delta is 15 degrees. It is in degrees. Okay, so I will use this formula. Here PA is constant. I can use the formula. What is the formula? Delta of T will be equals to delta naught plus half PA pi m into T square. So I have to find at T equals to 0.05 seconds. So 0.05 seconds. So your delta naught will be equals to 15.826 degrees. Plus 1 by 2, PA is 1, that is P naught, divided by M. M is basically 1 divided by 180 into 50 into 0.05 whole square. So this will be coming out to be 180 into 50 into 0.05 whole square divided by 2 plus 15.826. So it comes out with 27.076. So 27.1 degrees, or in radians if they are asking, into pi divided by 180. So this will be 0.4725 radians. Okay, this is your answer. So that's how simple questions come. So we solved few older gate PYQs. Now we will in the next lecture we will solve the recent gate PYQs. So like trust me, we have built up the base, right? That's why the questions are cakewalk. That's why you are solving the questions in a second, right? Because already I know if a fault occurs at either the receiving end and the sending end of the transmission line, the power delivered will directly go to 0. Okay, so I've already explained this, but still I am explaining it over here, right? So it means you have to revise. You are not revising. सुन नहीं रहे हो आप मेरी बात, ठीक है? Okay. So it's done for today's lecture. In the next lecture, we will do the remaining questions, and we will learn another topic, that is the power transfer with calculation of power transfer with admittance parameter. Thank you, and I will see you in the next lecture. Until then, happy learn. Hi everyone, so let's start with today's lecture. So today we will start with the like remaining problems, assignment questions that were remaining in the previous lecture. Also we will discuss about power flow using admittance parameters. Okay, I was just writing something, power flow using admittance parameters. So like I will show you the questions first, right? You can try, like this is the first one, second, third, fourth, fifth. There are a lot of questions. Sixth, like I think you will be able to solve it. They are nothing difficult. We have already solved every single thing, right? Whatever can be asked, we have already solved every single thing. This is the last one, I guess, not the last one. This one, then this one, right? I think yeah, this one is the last one. This one is the last one. After this, I think we are doing the y. Yeah, we are doing the y parameter. So you can try all these questions by yourself. Now I will solve. Okay. So here the per unit parameters for a 500 MVA machine on its own base are given. So M is equals to 20 pu, that is given to me. M equals to 20 pu. Reactance equals to 2 pu. The per unit value of the inertia and the reactance on 100 MVA common base. So if you remember, your MPU actually is inversely proportional to the S base, right? So what will be your MPU new? MPU new will be your MPU old into S base. It is inversely proportional. So here what will come? Here S base new will come, right? Not old. S base new will come, because it is inversely proportional. S base new upon S base old, right? So MPU old is 20, that is given to me, right? Into S base new base is 100 MVA, right? And old base is 500 MVA. Okay, so basically your new inertia constant, right? Okay, am I doing this correctly? Am I doing this correctly? That is what I'm thinking. It is inversely proportional, right? So oh, sorry, what I'm telling. So this will be new, right? So what I'm doing. So basically your MPU, right? MPU is equals to K times S base. So if I take the ratio MPU new upon MPU old, right? S base new will be in the bottom. What I am doing? Sorry. This will be in the bottom, right? And this will be in the top, because it is inversely proportional, right? So your new MPU will be inversely proportional. So that's why this will be in the bottom. Just take the ratio. I also am doing something wrong. Okay. So just be careful. Don't do these silly mistakes. So this will be 500. This will be 100. So it will come out to be 100 per unit. Okay. So this is the new MPU, right? Just simply take the ratio, right? Simply take the ratio. You will see it is coming out to be. So I'll just explain. So your MPU new will be what? It will be K divided by S base new. Your MPU old will be what? It will be K divided by S base old. Okay, so if I take the ratio of these two, what will happen? MPU old, MPU new, MPU old. So S base old will go in the top, S base new will still remain in the bottom, right? That's it. Now what about your reactance? So if you remember, your reactance XPU is directly proportional to the XPU is directly proportional to S base, right? I hope you remember what was XPU equals to. XPU was equals to X actual into S base upon V base whole square. I hope you remember this formula, right? So yeah, so XPU new will be equals to XPU new will be equals to XPU old into S base. Now here S base new will come, right? Because it is directly proportional to S base, divided by S base old. This will be equals to what is the previous XPU? So what is the previous XPU? Previous XPU is 2. So 2 into S base new. S base new is it's 100 MVA. Old S base is 500. So this will come out to be 1 by 5. That is 0.4 pu. So your reactance becomes 0.4 pu and your inertia constant becomes 100. So 100 and 0.4, that is present in option D. So option D will be the correct answer for this question. Let's now solve the next one. So a 50 Hz synchronous generator is initially connected to a long lossless transmission line. Lossless basically means your resistance is 0, okay, which is open circuited at the receiving end. Okay, with the field voltage held constant, the generator is disconnected from the transmission line. Which of the following may be said about steady state? So they're telling me that when it was like before disconnecting from the transmission line, it is telling me that it was connected through a long transmission line while the receiving end was open circuited. Basically the current was 0. If current is 0, then the power delivered is 0, right? So what will happen? If previously pre-fault condition, if the current was 0 pre-fault, if the current was 0 and the power delivered was 0, what will happen post-fault, right? What will happen post-fault? Okay, so they are telling me like there are many options here. So first option is that magnitude of terminal voltage decreases, the field current does not change. The magnitude of terminal voltage increases, the field current does not change. The magnitude of terminal voltage increases, the magnitude of terminal voltage does not change, field current decreases. Okay, so which one will be correct? Okay, so here like just one thing you have to trust me, this will be proved in the transmission line parameters in PSA 1. Just you have to trust me one thing, that under no load transmission lines behave as capacitive. Okay, transmission lines behaves as capacitive. How? So a long transmission line is modeled with a pi model. So I have this Jx and I have this Cc, right? C by 2, C by 2. Okay, under no load, the current is 0. Current through the series line, right, is 0 because overall the load is open circuited. So yeah, current is very small in this series connection. Bit of current flows through here. Bit of current will flow through here as well. That is correct, right? And here the terminal is connected. Here the generator is connected, right? This is 1 angle 0. Okay, just intuitively I am saying what will happen. So in long transmission line, the transmission line is modeled with a pi model. So here, right, bit of current flows through here. So overall, what is this current? This current is leading current, right? This current is lagging current. So overall the line behaves leading. And what do you remember if in case of a generator, if the load is leading? Do you remember something? If the load is leading, that means it is overexcited. So load leading for a generator. So every single concept will be used. So from machines to power system, it is totally linked. If someone says that study power systems first and then machines, they are not teaching you well. Okay, trust me. So here I will say that if load is capacitive, right? Load is capacitive, then your machine is overexcited. Then your machine is overexcited. Yes, you are correct that yes, it is open circuited at the terminal, but still transmission line is connected, right? So some current will flow through the transmission line due to this parallel reactance. Some current will flow through the transmission line, so it will behave as a capacitive load. The transmission line is behaving as a capacitive load, even though here the current is zero, right? But here the current is not zero, correct? Here it is not zero, here there is some current. So then your machine is overexcited, right? Your machine is overexcited. So basically your resultant flux, right? Resultant flux is the field flux. The armature flux is added. The armature flux is additive in nature if the load is leading, right? All these things are taught very well in synchronous machine. So it will be phi f plus phi ar. Okay, it will be additive. Armature reaction will be additive in nature. Additive in nature. But they're telling me as soon as I will remove this, like remove the generator from the transmission line also, then what will happen? Then here this will become open circuit. This will become totally open circuit, right? This will be open circuit, right? So if this is open circuit, then what will happen? Then the current suddenly becomes zero, right? Then what happens? Then there is no excitation at all, right? No excitation. Current is totally zero. Here the current, yes, I do agree, current is zero, but here, but transmission line as it is long transmission line, it will take some current, but here current totally goes zero, so there is no armature reaction at all. So after disconnecting, after disconnecting the terminals of generator, the current totally goes zero. So if the current totally goes zero, right, that means your armature reaction, there is no armature reaction, so your phi ar is zero. So what is your resultant flux? Resultant flux is phi f only. So your flux reduces, your phi resultant reduces. If it reduces, what is your ef, the terminal voltage? It is proportional to phi resultant. It is basically root 2 pi f phi resultant into n, right? So your phi resultant reduces, so your terminal voltage ef also will ef reduces, terminal voltage also will reduce. Terminal voltage of the generator will reduce, so magnitude of the terminal voltage will reduce. Okay, so either this one, yeah, only this one is present, magnitude of the terminal voltage will reduce. Okay, what about the field current? Will the field current change? No, field current will not change. Field current decides the field flux, right? If is decided upon phi f, right? We are not changing, we are not changing phi f, so if will be constant. Okay, so that is the case over here. So here option A is the correct answer for this question. Like this is a very elegant question. So GATE always asks some conceptual things, right? Here also they have asked many conceptual things. Many guys will skip this, right? So this is also a very important question. Okay, so let's now solve the next question. So the next question I will just zoom this. Right, this will zoom. This I will zoom. These things can be zoomed, right? So a generator feeds power to an infinite bus. A generator feeds power to an infinite bus through a double line. Have we done this question already? No, we have not. Through a double circuit transmission line, a three-phase fault occurs at the middle of the one of the lines. Right? Again, similar question. Three-phase fault is occurring at the middle of one of the lines. Right? What they are asking? What the infinite bus voltage is? 1 and 1 pu 1.1. So here I have the generator, here I have 1 pu angle 0, infinite bus voltage is 1.1 angle delta, okay, delta naught, and I have the double transmission line. Okay, so the transient internal voltage of the generator is 1.1 and the equivalent transformer admittance during fault is 0.x. So xf, right, they have not told me what is xf. X during fault equivalent admittance have they told me, or reactance? Equivalent admittance, they have told me equivalent admittance, right? What is reactance? So 1 by xf is given to me as minus j 0.8 pu. Okay, the 100 MVA generator. So what are they telling me? The infinite. So the three phase fault occurs at the middle of one of the lines. So here the fault occurs at the middle of one of the lines. Okay. The 100 MVA generator has an inertia constant of 5 megajoule per MVA. So inertia constant is given to me 5 megajoule per MVA, and it was delivering 1 pu power prior to the prior of the fault with rotor angle 30 degrees. So your delta naught is 30 and your PE naught is 0.5 pu, right? P naught, sorry, 1 pu. The system frequency is 50 Hz. F is given as 50 Hz. What are they asking? They are asking me the initial accelerating power will be. What is the initial accelerating power? So during fault, what is PM naught? Initial mechanical input, it is 1 pu, right? What is PE1? During fault, they have told me during fault the equivalent admittance is this, right? Equivalent admittance is this, right? So what is X fault? What 1 by X fault, magnitude of 1 by X fault is simply 0.8, right? J 0.8. Now what is the initial accelerating power? That is what they are asking, right? Initial accelerating power. So what will be the initial accelerating power? It will be basically PM1 minus PE1, right? That is equals to my accelerating power. PM1 is simply equals to PM naught, right? Mechanical input will not change. That is 1 pu, right? That is equals to 1 pu. What is PE1? So PE1 at the instant during which fault happens, delta cannot change instantly. Delta will not change instantly during fault. It will take some time for the delta to change, right? So your PE1 will be equals to what? EF Vt upon X during fault, right? Into sine of delta naught, right? So EF I know that is 1.1, Vt I know that is 1, 1.1 into 1. What is 1 by X fault? 1 by X fault is given to me 0.8. So I will directly multiply 0.8. I will not divide by 0.8. 1 by X fault is given as 0.8, right? So this will be into 0.8, 1 by x followed, right? So into sine of delta naught. What is sine of delta naught? So it is delta naught is 30, sine of delta naught will be half. Sine 30 is half. So this value will be 1.1 into 0.8 into 0.5. So this comes out to be 0.44 pu. That is what your PE1 comes out to be. Now what is your initial accelerating power? Initial, right? After this, of course, the delta will change. So things will change, right? But what is your initial accelerating power? Initial accelerating power will be 1 minus 0.44, right? PM naught minus PE naught, PM naught minus PE1. So this will come out to be 0.56, right? 0.56 pu. So this will be your initial accelerating power. After this, it will change. So 0.56 will be answer. Option C is the correct answer for this question. Now it is a common data question, right? Next, what have they asked? They have asked, it's a common data question. They have asked the initial accelerating power. If the initial accelerating power is x pu, the initial acceleration in electrical degree per second square. Okay. X pu is given to me. Right. I will zoom in this one as well. If the initial accelerating power is x pu, so PA is x pu, right? They're asking me the initial acceleration in electrical radian per second, right? What do I know? PA is equals to m alpha, right? So alpha will be equals to PA divided by m, right? Electrical, they have asked in electrical degrees. Remember, they have asked in electrical degrees. And the inertia constant in megajoule second per electrical degree will be. Okay. So what is m? In pu, it is, I will divide by h, I will divide by g, so it will be h upon pi f, right? Now they have asked in electrical degrees, so I'll convert my pi into 180 degrees. That's it. H is given to me. H is given to me, that is 5 MVA per 5 megajoule per MVA, right? 5 megajoule per MVA, that is given to me. So this will be 5 divided by 180 degree into f, that is 50. Okay, this I will replace in this equation, so I will be able to find out my acceleration. So PA is given to me as x, right? X divided by 5 into 180 into 50, right? It comes out to be 1800. So it comes out to be 1800 x. So 1800 x is only present in option B. So this is one of the answer, right? And what else they have asked? They have asked the inertia constant. What is the inertia constant in megajoule second per electrical degree? So inertia constant is this, right? Megajoule second per electrical degree. So this is already in electrical degrees. So if I write this value, I will get back this value, right? So this will be 1 by 1800, which is 5 into 5.56 into 10 raised to power minus 4. So 10 raised to power minus 3, 10 raised to power minus 2. So 0.10 will go, 20, 30 will go, 0.005. I'm getting 0. Something I'm messing up, huh? 5 1 divided by 1800. They're asking me megajoule second per electrical degree, inertia constant. Megajoule second per electrical degree. Okay. 5. So what is your m, right? Megajoule second per electrical degree. So it is actually not on per unit, right? This is not in per unit, because if you remember, this unit was what? It was simply second per electrical radian or something, right? but they have asked in megajoule. Megajoule. How will I find this in megajoule? So actually, okay, sorry, this was second square. If I remember correctly, it was second square. Correct? Second square per electrical degree. So this was in PU, right? I have to find out the absolute value. What will be absolute value? M will be equals to G into H divided by pi f. What was its unit? So this unit was seconds, right? If you remember, this was second. This is MVA, right? This is 1 by second, right? Megajoule per MVA. Yeah, yeah. MVA second. So this will become megajoule second. Yeah, megajoule second. Yeah. So MVA into second or power into second is what? Energy. So it becomes M megajoule, and this second will go up, right? So this will become second, and this pi I can write as 180. If I write this as 180, this will become electrical degrees. Okay. So now it is correct. Now it is correct, right? So we have to actually multiply G as well. What is G in MVA? G in MVA is 100 MVA. So I have already explained all this. Still I am doing from basics because I know you will also forget this in the examination hall. So these tricks will help you, right, to solve the question in examination. So I am teaching you exam oriented as well. So this will be 100 times H is 5, divided by pi, that is 180, into F, that is 50. So this becomes, this will be 10 by 1 by 18. Yeah, 1 by 18. 10. What is 1 by 18? It is 0.056, right? Unit is this megajoule per second electrical degrees. Okay, so they will play in units, right? Gate examiners will play you with units, but here you are lucky that this option was already matching, so you did not have to calculate this one, right? But what if they just ask you this? You will make a mistake. Just I was making here as well, right? I was calculating in per unit. So please take care of the units. Don't mess up with the units. Okay. So yeah, that's it basically for this question. Let's now move on to the next one. Okay. So again, if I will zoom this a bit. Okay. So the generator shown in the figure is delivering 1 pu power to the infinite bus with generator terminal voltage 1 angle 0. With find the generator EMF behind the transient reactance here. What is the generator EMF? How will I calculate it? So for that, right, I simply have to use KVL. There is no other way. I have to use KVL, right? So if I convert this into a single circuit, right, I will have a generator here, that is EF angle delta. Then I will have the equivalent reactance. What is the equivalent reactance? It is J 0.1. This is J 0.25. So this will be J 0.35. J 0.35, and then I will have the terminal voltage 1 angle 0. So I can easily find out the current. So they have given me the power 1 pu. It is delivering 1 pu of power. So I know the power delivered here. Do I know the current? Okay, power factor is not given to me. Power delivered is given, power factor is not given. That is interesting actually. Power factor is not given. How will I find out the power factor? Right? Okay. Okay. The generator terminal voltage is also 1. Okay, sorry. They have given that the generator terminal voltage is also 1. Right? Okay. Okay, that's interesting. That will help me. Okay. So here this much equivalent reactance is 0.35, and also the generator terminal voltage, right, is 1. That will help me to find out the power actually. So this is J 0.25, right? The generator reactance is J 0.25. This voltage is 1, but I don't know what is the angle. So I will assume this angle to be theta. Right? Now I can simply equate the currents. So current here and current here will be same. They are just in series circuit, right? So what is the current here? Current here will be EF angle delta minus 1 angle theta divided by j 0.25, that is equals to 1 angle theta minus 1 angle 0 divided by j 0.35. Okay, so here jj will get cancelled. So this value, right, ef angle delta will be equals to 5/7 angle theta minus 5/7 plus 1 angle theta. So this will become 12/7 theta minus 5/7. Okay, this is my ef angle delta, right? This is one of the relation, right? What is the other relation? So from here I can get few relations, right? So the real part, if I equate the real part, so ef cos delta will be equals to, or ef sin delta will be equals to, if I just equate the real part, 12/7 sin theta. Okay, another thing I know that the power delivered, right, is 1 pu, 1 or 0.5, it is 1 pu, right? If it is 1 pu, so power delivered, I know the terminal voltages at these two ends, so I can use the formula ef v by x sin delta will be 1. So ef is ef, v is 1, right? X equivalent reactance is how much? It is 0.6, 0.6 into sin delta equals to 1, right? So ef sin delta, from here I can get the value of ef sin delta, right? Actually ef sin delta is equals to 0.6. So I can replace this 0.6 over here in this equation, right? So if I replace this over here, what will I get? I will get that 0.6 is equals to 12/7 sin theta. So my sin theta is equals to 7 into 0.6 divided by 12, 0.35. So sin theta comes out to be 0.35. Okay, and if I take the cos on both sides, this will be ef cos of delta equals to 12/7 cos of theta minus 5/7. So I know what is sin theta, right? What is cos theta? So sin inverse cos of this. So cos theta 0.93675 into 12 minus 5 divided by 7. So your ef cos delta comes out to be 0.89157. Okay, that is what your ef cos delta comes out to be. Right, now it's very simple, right? I know what is ef sin delta, it is 0.6, right? I know what is ef sin delta. Okay, it is not going up. It is 0.6, right? It is 0.6, and I know my ef cos delta, so I can easily be able to find out my delta. Like what have they asked? Actually, I don't have not the generator EMF, so I can easily find out my ef, right? Ef will be what? This whole square, right? This equation whole square plus this equation whole square, right? So it will be, ef will be under root of 0.6 whole square plus 0.89157 whole square. So it will come out to be 1.07 46. Okay, that is what my magnitude of EF is, 1.0746. Can I find out the delta angle as well? Yes, I can find out the delta angle as well. Let us find out the delta as well. Delta will be what? So I know magnitude of EF, that is 1.07. If I take the inverse into 0.6 and then if I take the sine inverse, that comes out to be 33.994. 33 0.94 degrees. Okay, the maximum power that can be transferred under healthy condition. What is the maximum power that can be transferred? So P max, what is P max? P max, so this is the part 2, right? Part 1. Part 2 will be EFVT by X, right? Equivalent reactance. So EF magnitude I know, that is 1.0746. VT is 1, right? What is the equivalent reactance X? The equivalent reactance X is 0.6, right? Equivalent reactance X, right, is 0.6 throughout the line. It is 0.6, right? So it will be 0.6. So from here I can easily find out 1.075 046 divided by 0.6 comes out to be 1.791. This is the power, like maximum power transfer that I can transfer. This is the steady state stability limit. The maximum power that can be transferred if one of the line is open. If one of the line is open, then what will happen? If one of the line is open, right, then what will be your X equivalent? Then your X equivalent will change, right? It will not be like this, will become 0.25. So if one of the line is open, right, then I will copy this thing. Now this one potential also will change, but of course I know the value of EF, so that will not change, right? So I will have the transformer. Transformer will still be there. That reactance of the transformer is 0.1. Okay, and one of the line is open, other line is still working, so it will be J 0.5. So of course it will reduce, right? Your steady state stability limit P max will reduce. So now the equivalent, so EF is 1.076, right? So this will become, now if I convert this into a equivalent reactance, so your equivalent reactance will become 0.5, 0.6, 0.6, 0.85, 1 angle 0, so 1.706 angle delta. Okay, so P max equals to 1.706 into 1 divided by 0.85. Of course it will reduce now, so it will become 1.267. okay, 1.2643. you see there is a reduction in the P max. Okay, so this is the answer here, this is the answer here, this is the answer here for the first case. Now in the fourth portion, what they are telling me, the maximum power that can be transferred if one of the line is shorted in middle. If I short one of the line in middle, what will be the maximum power transfer? Again you have to do the star delta conversion. You have to do. So if one of the line is shorted in the middle, that means basically this this will be J 0.25, this will be J 0.25, this will be started. So I have to do the star to delta conversion, right? So let me do it here only. So like it's like opposite of delta, so maybe it might feel you it's a bit difficult. So let me do one thing, let me replace this, right? Otherwise it is difficult to visualize. So let me keep it over here. So this will convert to star. So what we'll do, this will be star connection, right? One reactance will be here, another reactance will be here, right? So like I will, at the end of today's lecture, I will tell you how to solve this using the look. I will now only I will tell you how to solve this using a different method. Okay. Okay. So what is the equivalent reactance here, right? I am converting from star to delta, right? So star to delta means summation, so it will be x1 plus x2. So if I am talking about this one, x1 plus x2, that is J 0.25, so J will be here 0.25 plus 0.25 plus this into this divide by this, that is infinity. Okay, so this will be open circuit, this will be basically open circuit, right? So 0.25 into 0.25 divided by 0, so this will be infinity. So this reactance, top reactance, is basically open circuit. I have only two parallel reactances, right? So two parallel reactances I have. So what will be this value? This will be this plus this, and this into this divided by this, so that is 0 as well. So this is this reactance only. So okay, basically I don't even need to convert this, right? So basically I have two reactances that are connected like this. Okay, so if I convert this, right, I will have here J 0.35, this will be there. I will have this J 0.5, right, in this part, one angle 0, and here I will have a reactance that is 0.25, and here again I will have another reactance that is 0.25. Okay, so now how will I solve this? That is the main purpose. How will I solve this? I know this is 1.076 angle delta, right? Okay. How do I find out the equivalent reactance from here? That is the important point. So this point is same. So what I can do, if this point is same, right, this point is common, I can connect these two points. Right, if I connect these two points, I will have a reactance here, and reactance here, that is grounded. Yeah, now I think we'll be able to solve it. Yes. So if it is grounded now, okay, now it is fine. So I was doing it wrong. I was thinking it wrong, right? So I will have a reactance here, I will have a reactance here, I will have a reactance here, right? So it's 0.25 into 0. I'm converting from, what is it? This is delta to star. If I'm converting from delta to star, that means I have to do division, right? D for division, right? Division basically means that division, right? So if I'm writing this reactance, it will be this times this divided by the sum of all the three reactances, right? So it is 0.5 times 0.25, J is there, divided by sum of all the reactants, that is 0.5 plus 0.25 plus 0.25, sum of all the reactants. So it is actually 1, right? So it will be basically 0.125 pu. Basically this reactance, right? It will be 0.125. I will just quickly confirm this value as well. So this will be 0.5 into 0.25, yeah, 0.125, right? So the circuit, right, draw the circuit. Zero 0.35, okay, and this reactance I have just calculated, this reactance, right, will be 0.125. This reactance also will be same because this is 0.5, this is 0.25. This reactance also will be 0.125. So I will have here J 0.125, and then I will have J 0.125, and here I will have, what will be this? This will be just half, right? Because here both sides have J 0.25, J 0.25. So this will be J 0.0625. Okay, J 0.0625. So now again I will convert this back into delta. Again I will convert this back into delta because I will add these two reactances. So these two reactances will become what? These two reactants will become J 0.4, okay, 475, J 0.475, right? So this reactance is now J 0.475, this reactance is J 0.0625, and this reactance is still same, that is J 0.125. Why? Because I only have to calculate this reactance. What reactance? The top one. Because I have to convert this into equivalent circuit where, like, what will be the power transfer, maximum power transfer? Here the voltage is fixed, right? Here the voltage is fixed, 1.17, 1.17, 1.1076, right? Delta. So I can easily find out my maximum P max, right? So what will be your 1.70, what will be your X? X will be basically, I'm converting from star to delta. So star to delta, it will be summation. Summation will be, if I'm writing this one, so this one will be this plus this, that is point J will be there, 0.475 plus 0.125 plus this into this divided by the opposite reactance. So 0.475 into 0.125 divided by 0.0625. Okay, so by x will be equals to what? X will be equals to this into 0.125 into 0.475 plus 0.125 plus 0.475, so it comes out to be 1.55. so this comes out to be 1.55. Now I will be able to calculate my P max, right? It is very easy. P max 3, it will be EF 0.706 into VT divided by the reactance 1.55. so this into 1.076, right? 0.76 is correct, right? Yeah, comes out to be 0.69, 0.6942 pu. Okay, all these things we have solved already in class notes. All these are there already. Okay, but I'm still again solving it. If someone still has some doubt, he or she will be able to solve this, right? So let's now solve the next one. Just give me 1 second. Yeah, so it's a very recent question. So in recently they have asked, so a 3-phase 2-pole, so number of poles is 2, frequency is 50 hertz, has a rating of 250 MVA, cos phi is 0.8 lakh. The kinetic energy of the machine at synchronous speed is 1000 megajoule. So kinetic energy stored in the machine is 1000 megajoule. The machine is running steadily at synchronous speed and delivering power of 60 megawatt at a power angle of 10 electrical degrees. Delta naught is 10 electrical degrees. If the load is suddenly removed, assuming the acceleration is constant for 10 cycles, right? Cycles, number of cycles is 10. 10 cycles meaning one cycle is how much? Seconds. What is it? It is 1 by f, right? Frequency is what? Cycles per second. So one cycle will be how many seconds? 1 by f. So 1 by f is 20 milliseconds, right? 20 milliseconds, and 10 cycles will be 200 milliseconds, right? 10 cycle will be 200 milliseconds, which is equals to 0.2 seconds. So they are asking me if the acceleration is constant for 0.2 seconds, right? The value of the power angle after 5 seconds. So after 5 cycles, what will be the time after 5 cycles? It will be basically 20 millisecond into 5, right? One cycle is 20 millisecond, 1 by 50. 1 by 50 is 20 millisecond. So 5 cycles will be 100 millisecond, that is 0.1 second. So they are asking me what is the rotor angle at 0.1 seconds. What is the rotor angle at 0.1 seconds? So what was the formula, right, of rotor angle? Delta t. It was delta naught plus half PA by m into t square. Every time, whenever we have solved, our accelerating power was always in per unit. But this time, our accelerating power is not in per unit. It is in actual. So our m value also will be in actual. Okay. So what is the accelerating power first of all? So they have told me that initially it was electrically loaded with 60 megawatt, but suddenly the load has been removed. So your PM naught, obviously during steady state, your PM naught will be equals to PE naught, that is equals to 60 megawatt. But if suddenly the load has removed, so PA is equals to PM1 minus P1. So your PE1 goes to 0. That means your PM1 will be your P1, that is 60 megawatt. That is 60 megawatt. Okay. PA is equals to PM1, that is 60 megawatt, right? This is my PA. PA I have found out. What is my M? M is equals to, in actual value, it is GH upon pi f. Remember, your delta is in, what have they asked? In electrical degrees, right? So your pi I will write in electrical degrees, that is 180 degrees. 180 degrees. What is your H? H I don't know, but I know when it is delivering, kinetic energy of the machine when it is rotating at synchronous speed is 1000 megajoule. What is H? If you remember, what was H? H was actually equals to your kinetic energy of the machine divided by the rating of the machine. So G into H actually is equal to simply kinetic energy of the machine. That's it. So I will replace my G into H here with kinetic energy, that is given as 1000 megajoule. So I will keep it mega only. 1000 megajoule, because power is in megawatt, so mega will get cancelled, right? So megajoule is there upon 180 into frequency, that is 50. Okay. Now I will just put here in the formula. Time is what? Time is given to me, that is 0.1 second. I will just simply put in the formula, right? So a delta of t at t equals to 0.1 second will be equals to what? At t equal to 0.1 second, it will be equals to 10 degree plus half into PA. PA is 1000 divided by 180 into 50 into t square. Sorry, PA is 60, right? PA is 60. PA by m is 1000, this into t square, that is 0.1 whole square, right? So if I solve this, what will I get? So this will be 60 into 180 into 50 divided by 1000 into 0.01 divided by 2 plus 10. So 12.7 degrees. Okay, 12.7 degrees. This is your answer. So this question is like very simple. Like we have solved this kind of question previously as well. But trust me, this kind of question is not that simple for other guys. These kind of question is not that simple for other guys. It is difficult. So here they have mentioned that PA is constant. They have mentioned that your accelerating power is constant, right? I hope now you understand why during writing down the formula I have mentioned that this formula is only valid when the accelerating power is constant, and in GATE they will give you this formula only. If it's not constant, then you have to solve by the basic equation. What is the basic equation? Basic equation is PA is equals to m alpha, right? And then you have to derive basically. Then you have to derive the expression for alpha, right? Then you have to derive the expression for alpha with this equation, right? PA will be given in terms of delta. M is a constant number, so alpha you can simply find out, right, in terms of delta. Like that you can solve. Okay, let's now solve the next one. So a 50 hertz generating unit has H constant as 5 MVA, sorry 2 megajoule per MVA. The machine is initially operating in steady state at synchronous speed, okay, producing real power of 1 pu. So PE naught is equals to 1 pu, which is equals to PM naught, right? The initial value of the rotor angle delta is 5 degrees. So initial value of the rotor angle delta is 5 degrees. When a bolted 3-phase to ground short circuit fault occurs at the terminals, assuming the input power remain 1 pu, so PM1, right, is 1 pu, but a bolted 3-phase fault, ground short circuit fault occurs at the terminal. That means your PE1 becomes 0, right? Assuming the input mechanical power is constant, the value of the delta after 2.02 seconds after fault. Like again, it's the same question only. So here everything is in per unit. If everything is in per unit, again your M also will be in per unit. So it will be simply H upon pi f. So they have asked in degrees. So your pi will be in degrees, right? So H is given to me, that is 2 megajoule per MVA. It is in degrees. Frequency is 50 hertz, right? So what will be your? I will directly solve. I will not do all the derivation. So delta T will be delta naught plus PA by 1 by 2 PA by M into T square. So delta naught is given to me, initial angle is 5 degree, plus 1 by 2 PA is initial acceleration is 1, like accelerating power is 1, divided by M. M is simply 2 divided by 180 into 50 degrees, okay, into T square. T is given to me as 0.02 seconds. Okay, so here this value will be 180 into 50, this is not degree, right, divided by 2 into 0.02 whole square, divided by 2 is divided by another 2 plus 5, so it comes out to be 5.9 degrees. So I'm directly solving it. So I have solved one with actual values, one with per unit values, right? Answer. Let's now move on to the next one. So in the next question, a synchronous machine is connected to infinite bus through a transformer and a double circuit line. The infinite bus is maintained at 1 pu. So again, I have my generator, right? I have my transformer, and then I have double circuit line, and this is maintained at 1 pu. The system parameters are expressed as follow. The direct transient reactance of the machine is J0.2. Okay, this is J0.2, right? Transformer is J0.1. Line reactance, each transmission line is J0.4, J0.4. Okay. Initially the machine is supplying 0.8 pu power with terminal voltage 1.05, right? So initially the machine is supplying initial power P naught is 0.8 pu 0.8 pu power with terminal voltage of the machine to be equals to 1.07. So E, right, EF angle delta is 1.07, 1.05. Now what are they telling me? The inertia constant of the machine is 5 megajoule MVA at 60 hertz. So F is equals to 50 hertz, H is equals to 5 megajoule per MVA. Okay. Formulate the swing equation for the machine expressing the rotor acceleration in electrical radians per second square. Okay. So I have to formulate the swing equation. So what will be the swing equation? The swing equation will be what is happening if a fault have the they have not even asked, like they have not even told me that. Okay. Formulate the swing equation. I think this is a common data question, right? No, this is not a common data. So they are just asking me to formulate the swing equation. That's it. Oh. It's very simple. So they are just asking me to formulate the swing equation. What will be the swing equation? So swing equation will be simply Pm minus P m d square delta dt square, right? That is what is written over here. So basically they are asking me the d square, like they are asking me the differentiation of this value. They are just asking me this value. So what will be this value? D square delta upon dt square will be equals to Pm minus P divided by m. Okay, so Pm minus P, right? Pm minus P. So Pm minus P. So initial power is 10. It is 10 pu, correct? Where did it go? So P naught, right? P naught is 8.8 pu. So what is the Pm naught? Pm naught also will be same. Initially 0.8 pu, right? But what is the electrical power equation? So for that I have to find out the equivalent reactance, like it will be EF Vt upon X sine delta, right? So what is it equals to? So EF is 1.05, Vt is 1. What is the equivalent reactance? It is 0.2 plus 0.1 plus 0.2, so 0.5. Into sine delta. So this will be 2.1 sine delta. Okay, so this comes out to be 2.1 sine delta, right? If I'm not mistaken, yeah, 1.05, yeah, point, yeah, that is correct. Okay, so now we have to finally find out m. We don't know what is the value of m, right? So what is m? Again, everything is in per unit here, right? PMP are in per unit. So I have to find out the value of m in per unit only. I have to find out the value of m in per unit. Okay. So m in per unit. What will be the value of m in per unit? Okay. So okay, this question, one thing. Okay. The infinite bus voltage is maintained at this. Initially the machine is supplying with the terminal. Okay, I have made a mistake. They have told the terminal voltage to be 1.05. What do you mean by terminal voltage of a machine? What do you mean by the terminal voltage of a machine? The terminal voltage of a machine, that's my bad, right? Actually it should be this, after the synchronous reactance. That is the terminal voltage. It is not the field voltage, right? That's why the options are here are not matching. That's what I was thinking. So I made a mistake here. So they are talking about terminal voltage. This is my terminal voltage actually. terminal voltage of the generator. This is a infinite bus voltage, that is a separate thing, but the voltage at the generator side is 1.05, right? But I have to find out the EF magnitude. How will I find out the EF magnitude? How will I find out the EF magnitude? So this is actually wrong. This thing is wrong actually, because here EF is not correct. EF is incorrect, right? So how will I, like, again you have to draw the equivalent circuit diagram here, right? First of all, I know the power delivered is 0.8. This should be equals to EF into VT, that is 1, right? This side voltage, right? This side potential, divided by the equivalent reactance X equivalent into sine of delta equals to this, right? So what is the X equivalent, overall equivalent reactance? It is simply 0.5, right? So basically your EF sine delta is coming out to be 0.4. That is what my EF sine delta is. Like, we have solved this question like in today's lecture only. Similar question we have solved. So here I can equate the currents, right? So here I know the terminal voltage is one angle whatever theta, I don't care, and this point voltage is what? This point reactance is how much after the generator? It is 0.1 plus 0.2, that is 0.3. This will be 0.3, and this will be 1 angle 0, and this will be my voltage, that is EF angle delta. Okay, so here what I can do is again I can equate the currents, right? Whatever current is incoming here, same current will go here. So it will be EF delta minus 1 angle theta, right? Because not 1 angle theta, sorry, 1.05, because they told me that the terminal voltage is, I know the magnitude of the terminal voltage, that is 1.05. So this will be 1.05 divided by J 0.2 equals to 1.05 minus 1 angle theta minus 1 angle 0 divided by J 0.3. So from here I can write down the expression for EF angle delta. So EF angle delta will be 2 by 3 into 1.05 angle theta plus 1, so it will be 5 by 3 into 1.05 angle theta minus 2 by 3, right? So from here I can say that what is my EF sine delta, the imaginary part will be 5 by 3 into 1.05 sine theta, and I know what is my EF sine delta, that is 0.4. So from here I can easily find out what is my sine theta. So 0.4 into 3 0.4 into 3 divided by 5 into 1.05, say not 1.05, sine inverse, it comes out your theta, this is 0.23, your theta comes out to be 13.21 degrees, right? Theta is this value. So what is your EF value? So I know theta, right? I know sine theta is 0.23. I can easily find out my EF from, no, not from here. So I can easily do, I can easily find out my, again if I equate the real parts here, if I equate the real parts, it will be EF cos delta will be equals to 5 by 3 into 1.05 cos theta minus 2 by 3. Okay, so your cos theta will be cos theta zero point 9735. Okay, so this into 1.05 divided by 3, so minus 2 divided by 3, it comes out to be 1.037, right? So EF cos delta is 1.037. So from here I can easily find out what is my EF, right? So what is my EF? EF will be under root of 0.4 whole square plus 1.037 whole square. So this will be equals to plus 0.4 whole square whole under root. So 1.11. So here EF comes out to be 1.11. Now it is correct. Now what is my P max? P max will be EF or P, right? P will be EF Vt by X equivalent into sine delta, which is 1.11 into 1 divided by X equivalent. X equivalent is 0.5 into sine of delta, right? So this will be 2.22. So that was missing, basically 2.22 sine delta. This will come, right? So here if you see 2.22 sine delta is here and here. So option A, B can be the possible answers, but before that I have to find out my M. So what will be M? M should be in per unit, right? M should be in per unit. So M value will be H upon pi F, right? It's in radian per second square, right? That's why pi is pi only. So H is I guess they've given me what is H. H is 5 megajoule per MVA. Okay, 5 megajoule per MVA. Pi frequency is 60 hertz, right? I guess frequency no 50 hertz. 50. Okay, so basically my equation, right? D square delta upon dt square will be, here M inverse will be there, right? So 50, so it is basically 10 divided by pi. So it should be actually something I'm missing, radian per second square, electrical radian per second square, swing equation of the motor. Okay, what am I missing over here? Electrical radian per second square. This is sorry, frequency is 60 hertz, right? Sorry, frequency is 60 hertz. Still I'm missing something. 5 megajoule per MVA. So it is 60 upon. So it is okay. No, I'm not missing anything. So it is basically 12 into pi. What is 12 pi? 37.7. Okay, I'm not missing anything. So basically it is what? 1 by M into Pm minus P. So mechanical input power will not change. 1 by M is 37 basically 0.7. Pm is 0.8 pu. Right? It's basically 1 by N. 0.8 pu minus P max we have calculated 2.22 sine delta. This is the equation. This is the answer. Right? Okay. So here, what will be your correct answer? Your correct answer will be option C. Option C. 37.17 into 0.8 minus 2.22 sine delta. Okay. So let's now move on to the next question. This is a good question because here, right, they have given the graphs. So we have not discussed about the graphs. Like I've shown you the graphs about the rotor angle, but we have not discussed those in like with the question. So we'll see with the question, right? So the synchronous generator shown is supplying active power to an infinite bus via two short lossless transmission lines. So short lossless transmission lines are simply short transmission lines will be modeled with simply a series inductive reactance. That's it. Now the mechanical power input of the generator and the voltage magnitude E are constant. Okay, so mechanical power input Pm and magnitude of the voltage are constant. If one line is stripped at time t1, okay, at time t1 one of the line is stripped by opening one of the circuit breakers, right, at the two ends, although there is no fault, right, we're just opening the circuit breakers on our own, then it is seen the generator undergoes a stable transient. Which of the following waveforms of the rotor angle delta shows the transient correctly? Okay, if I remove one of the lines, which of the following graphs shows the transient correctly? Okay, so here the thing is, this graph here I am seeing that yeah, transients are there, delta is oscillating and delta is always positive here. Delta is always positive here, right, in the first graph. Here sometimes delta is going to 0. Here delta is negative. Delta negative meaning what? Power flows from the infinite bus to the generator, right? And here also delta is sometimes 0 and negative. Now it's very simple, right? If I open one of the lines, will the power flow go to 0? Will the power go to 0? Power will reduce. So PE, like with two transmission lines connected, right? PE naught will be greater than PE1 when only a single transmission line is connected. This we have done multiple times. I think thousands of times we have done this, right? So if one of the line is suddenly open circuited, the electrical power output will reduce. So there will be some accelerating power, but this will not be equal to 0. This will not be equal to 0, right? Because still I'm delivering one line and it is totally healthy. I'm just open circuiting the other line. So if it is not equal to 0, P1 is never equal to 0, then your formula, what is the formula for P1? It is EF, magnitude is not changing, VT will not change, reactance, there is some finite reactance, sine delta. So I know that PE is never going to 0, that means your delta also can never go to 0, never, not possible. So here, right, delta going negative, not possible, delta going 0, not possible. Here delta negative, how delta can go negative? If power will always flow from the higher angle to lower angle. Initially generator was supplying the power, so still one line is intact, right? Still I will deliver power. So power will always flow from higher angle to lower angle. So delta cannot be negative. If delta is negative, that means this point is higher angle and this point is lower angle. Power is flowing like this, not possible, not possible. Okay, so power will always flow. This, I think, conclusion we have done in the, I think, in the fault chapter. Flow from higher angle to lower angle, right? So only, of course, one option is matching here, this option. This is only matching because here, yes, there is some oscillations, there will be some oscillations because the PE has reduced, there is some accelerating power, but delta can never go negative because I'm still delivering some power, right? Okay, it will lie within, it will always be positive. So option A will be my correct answer for this particular question. Okay, let's now move on to the next one. Next one, again something similar kind of question they've asked in GATE 2007. So consider a synchronous generator connected to an infinite bus by two identical parallel transmission lines. The transient reactance X dash of the generator is 0.1 pu. The mechanical power input is held constant to 1 pu. Okay. Due to some previous disturbance, the rotor angle delta is undergoing undamped oscillation. Due to some disturbance, it is undergoing undamped oscillation. So it is oscillating. It is oscillating, right? Undamped. Basically, the oscillations are not reducing. Okay. Now what they are telling me? And the maximum value of delta t is equals to 130 degrees. Okay. One of the parallel lines trips due to relay maloperation. So automatically one of the parallel line is trips. Basically, it is removed from the circuit suddenly, right? At an instant when the delta t is 130 degrees as shown in the figure. So here there is a trip. The maximum value of the per unit line reactance X such that the system does not lose synchronism subsequent to this tripping. Good question, right? So we have to find out the maximum value so that the system does not lose synchronism subsequent to this tripping, right? So when the two lines were connected, right, what will be the graph? What will be the PE? So PE 1 or PE naught initially when the two lines were connected, right, the equation of PE naught will be what? It will be EF. EF is 1, right? VT is 1. So 1 into 1 divided by X equivalent. What is X equivalent? 0.1 plus X by 2. These are in parallel. So 0.1 . this will be equals to into sine delta. Now this was the initial. So initial, what was some Pmax? Pmax naught was this well, right? So it is basically 1 upon 0.1 plus x by 2. So just at the instant of fault, during fault, what is Pmax? Pmax will be 0.1. One of the line has stripped, so this line has been removed. So only x is there. So this will be 0.1 plus x. So your denominator has actually increased, right? This is lower. Denominator has increased, so your Pmax will reduce. So if your initial graph was like this, right? Now your graph will be like this. I think I have done a problem similar to this. We have discussed this, right? Now, if I keep on increasing my x, right? If x value is higher, what will happen? The Pmax will keep on reducing. What is the drawback? So, your Pmax will reduce if the x is kept increasing, right? The drawback is my mechanical power is constant actually, right? My mechanical power is constant. Mechanical power input is constant, and I have told you, if there is no valid operating point, if the mechanical power graph and the electrical power, they don't intersect each other, then simply the machine will go out of synchronism. Then the machine will go out of synchronism. If the this point I have written, right? I have written this point. If there is no valid intersection, okay, if there is no if there is no intersection between the mechanical input power and electrical output power characteristics, then the machine will simply go out of synchronism. Machine will simply go out of synchronism. Okay, so that is the thing over here, right? So here what is happening, machine will simply go out of synchronism. So what can I say is that there is no valid intersection, machine will go out of synchronism. Yeah, so basically my it should intersect, right? It should intersect. So what is the last point where it will intersect? This point, right? So basically your Pmax, right? What is the critical point? The critical point is, because your Pmax is reducing, so this graph is going down. So there will come a point where the Pmax and Pm naught will be equal, and at that instant, that is the critical point. So what is the critical point? Critical point where my Pmax will be equals to my Pm naught. After that, if I keep on increasing my reactance, it will never intersect, right? If you see, is it intersecting? Is the green graph intersecting the Pm naught? No. So it will simply go out of synchronism. So what is Pmax? Pmax is basically Pmax is basically 1 divided by, we have calculated it, Pmax is simply 0.1 plus x. Okay. Now what is Pm naught? What is Pm naught? So Pm naught is but different to calculate. So your one more thing is there, right? If the line trips here, mechanical power input is constant. Okay. Here what is the rotor angle? So actually on the graph, right? On the graph, which position I am in? On the graph, right? what is the, like, this is the maximum rotor angle delta m, right? Maximum rotor angle delta m. I'm in this position, otherwise if my angle will not increase beyond this, correct? Yeah, so yeah, basically it will be this value. So it is p, what is pm naught? Pm naught is given to me 1 pu, right? Mechanical power input is given to me 1 pu, so 1, so your x will be equals to 0.9 pu. But in the question they have not given 0.9 pu, because like what I have seen few guys, what they do is they have done this, like they have written this formula and they have multiplied sine of 130. So sine of 130 inverse, wait, sine of 130, no sorry, sine of 130 minus 0.1, so 0.67. So few guys have done this sine of 130.1. I think that is wrong actually. I think this question is wrong. So they have done what? They have multiplied this p max with sine delta, right? Sine of 130. So for them it came out to be 0.76 and they subtracted 0.1 from this, right? They got 0.67 and the answer they put as option C. But for me I think this will be the answer. Okay, you guys can put in the comments below if you guys have some alternate answer, but I think according to me the answer should be this only, because it should depend on the mechanical input power and the current electrical characteristics, right? Not on the current electrical power output. Electrical power output will keep on changing. Okay, so according to me this should be the answer, 0.9. Okay, so let's now move on to the next question. So you guys can verify this. Let's now move on to the next question. So here consider a model shown of a transmission line with a series capacitor at its midpoint. The maximum voltage on the line is at location what? What will be the maximum voltage of the line? Where will be the maximum voltage of the line? Okay, so here I have 1 angle 0, here I have 1 angle 0. At which point maximum voltage will be there? Current is 1 pu, power factor 1, right? Okay, how is there? Okay, VR is given, but remember you will think that, sir, here I have 1 angle 0, here I have 1, so there is no current flow, both ends potentially same. No, here, right, there is some theta, 1 angle theta, so due to the phase difference there will be some current flow. Okay, due to the phase difference there will be some current flow. So they are asking me at which point the voltage will be maximum. For that I have to write down the expression for voltage. So here Vp1 will be what? Vp1 will be simply Vs, that is equals to 1 angle 0. What is Vp2? Vp2 is 1 angle 0 Vs, right, plus j 0.1 I. Power factor is 1. If you see here, power factor is 1. If power factor is 1, its angle is also 0 with respect to reference. With respect to reference, its angle is 0. It is 1 pu. So this will be basically 1 plus j 0.1. Sorry, 1 minus j. This will be minus, right? There is a drop. 1 minus j 0.1. What is Vp3? Vp3 will be Vp2 minus of j, because it is a capacitive reactance, into current. So Vp2 is minus j 0.1 into current, right? They was the maximum voltage on the line into current, right? So this will be plus j 0.15. So this will be 1 plus j 0.5. Okay, then P4. What is Vp4? Here Vp4 magnitude I know, magnitude of Vp4, right? Magnitude of Vp4 is simply Vp4 is 1 angle theta, that is magnitude of Vp4 is 1. Okay, now what is the magnitude here and here, right? So magnitude here is, sorry, this is right, this is added, so sorry, this will be 0.05 actually. This will be 0.05, right? So they're asking me the maximum voltage on the line will be maximum voltage. Okay, maximum voltage on the line. Okay, This will be magnitude of, what is the magnitude of VP2? Is 1 plus 0.1 whole square whole under root, right? And here what is the magnitude of VP3? It is under root 1 plus 0.05 whole square, correct? So whose magnitude is greater? Whose magnitude is greater? So your magnitude of VP2 will be greater, right? If I am not mistaken, VP2 will be greater, correct? Because we are just concerned with the magnitude. We are just concerned with the magnitude. So if the magnitude is given, so magnitude of VP2 will be greater. So answer will be VP2. Magnitude of VP2 will be greater than magnitude of VP3, and of course here the magnitude is 1, here also the magnitude is 1, right? So this will be your answer. These are all same. Okay, let's now move on to the last question, and with this I will again, like the same question, like same similar question we have done. So with this we'll try to solve this power transfer using Y transfer as well, right? So what is the power transfer pre-fault and post-fault we have to calculate. So again we have to do that exercise, same old exercise, right? Star delta conversion. Okay, boring. Okay, so maximum power transfer pre-fault and during fault, right? So during fault at midpoint, during fault occurs at midpoint of one of the transmission lines. So here, right, pre-fault, what is the equivalent circuit? So pre-fault, right, if I draw the equivalent circuit, so here I have J 0.2, this J 0.6, 0.6, so this will be J 0.3, J 0.2 plus 0.3 will be 0.5. So this overall pre-fault circuit will be J 0.5, right? And here it is 1 angle 0 and it is EG angle delta, right? So what is the maximum power transferred pre-fault? So pre-fault P max will be EG into VT divided by J 0.5, right? So this will come out to be 2 EG. Okay, this comes out to be 2 EG. So now what is the maximum power transfer during fault? So when a fault happens, the fault will happen at the midpoint of one of the transmission lines, right? So at the midpoint, so fault will happen at the midpoint, so it will happen at the midpoint of one of the transmission lines. So here it will be divided, here I will have a reactance, right? Here I will have a reactance of J 0.1, this will be J 0.25, and then this will be J 0.25, and here the fault happens, right? Three phase fault. So three phase fault. 3-phase short circuit fault. Okay, so this whole thing will be converted into a single reactance, that is J 0.6, right? So overall again I can break it down into, this is in delta currently, I can break it down into star, right? So what will be this value? It will be this, I am doing delta to star, so there will be division, right? Division will be this, right? This is how much? It is 0.35, 0.35, this is 0.6, right? This is 0.35, 0.25, that is 0.6, 0.6, that is 1.2. So in bottom I will have 1.2 always, there will be j here, and this value will be this times this, right? This whole thing is 0.6 times 0.35, so 0.6 times 0.35. So this will be your first reactance. Next reactance will be, this is how much value? 0.6 into 0.35 divided by 1.2, okay, 0.175. So this will come out to be 0.175. So this, right, here I have 0.2, here I have J 0.175, here I have what? So this into this, right? So it will be, instead of 0.35 it will be 0.25. So 0.6 into 0.25 divided by 1.2. So this will be 0.6 into 0.25 divided by 1.2. So it is actually J 125. Then here I will have another reactance. That reactance will be this times this, right? So it is 0.35 into 0.25. So it is 1.2. So 0.35 into 0.25 divided by 1.2 equals to 0.729. Right? That is your reactance. Okay, so this is your reactance. Now I will add these two, right? I will add these two together so that I can find the equivalent reactance between this and this, so that I can find the maximum power. So this will be basically this whole thing, if I combine, right, this will be 0.35. So the value is basically J 0.375, then I have J 0.125, and then I have this whatever value is J 0.0729. Okay, now what I will do is, again I will convert this into delta. So I just need this reactance, right? I just need this one. So for delta, star to delta, it is summation, right? So it will be J 0.35, 0.735 plus 0.125 plus 0.375 into 0.125 divided by the opposite reactance 0.729167 J, right? This is the equivalent reactance here, X. into 0.375 into 0.125 plus 125 plus 0.375. This is equals to J 1.1428. That is my X, right? So now I will be able to find out my equivalent power P max post fault. It will be Eg Vt upon 1.1428. Now if I take the ratio, right, the ratio required answer, right, desired answer, P transferred pre fault to post fault, two Eg upon Eg upon 1.1428. So this times 2 will basically be 2.28. Now there is another way, like this question we have already solved, right? There is another way to solve this using y parameters. Okay, I'll just quickly explain in brief how can you use y parameters to solve this. So if I convert this, right, at the other end I have a voltage that is 1 angle 0, right, and I have converted my source to two terminals. It's a two-port device. So inside this network, I have converted it into y parameters. So individually, if I am able to find out the y parameters, then I will be able to find out my power delivered, active power and reactive power. What is the power delivered by this voltage source? It will be E1 into I1 conjugate. E1 into I1 conjugate. So what is I1 conjugate? So I1 in terms of y parameter is y11 E1 plus y12 E2, right? So I will replace this I1 here with conjugate. If I take the conjugate here, it will be, if I take I1 conjugate here, what will be I1 conjugate? It will be y11 conjugate E1 conjugate plus y12 conjugate E2 conjugate. Okay, and E2 is simply 1 angle 0, so we don't have to worry about E2, right? Just hold on, there is a bit of rain outside. So now I will replace my I1 star here. If I replace my I1 star, what will happen? Basically, if I replace my I1 star, it will be E1 into E1 conjugate, Y1 conjugate, right? And what is Z bar into Z conjugate? It is simply magnitude of Z, right? Okay, complex numbers, basics of complex numbers. I have taught this in basics of complex number, network theory. So every single thing is important that we teach. So it is magnitude of E1 square. Here also something will come, that Y12, it will be E1 will be here again. This will be E1 in vector, right? Into E2 star. Into E2 star. Okay. So your power expression, right? Like this is the apparent power expression. If I just want to write the power expression, I will just equate the real part. So it will be Y11. Like what is the real part of this, right? Real part of this. So if y11 has an angle, like this is my magnitude of y11, right? Sorry, not magnitude, this is my y11. So what will be y11 conjugate? It will be g11 minus jb11 minus jb11, right? So what will be the real part of this? Real part is same, right? Real part of y1, because I just want to equate the real part. This is already real. This is already a magnitude. It is just a constant number, right? So I want to find out the real part because I want to equate the real part on the left hand side. So on the right hand side also I have to write the real part. So here what is the real part? Real part is g11. This is the real part. Real part of y11 conjugate. So what is this? It is simply, what is g11? G11 is simply magnitude of y11 into cos of theta 11. That is what I have written over. Magnitude of y11 into cos of theta y1. This is just a constant number. This will stay. Now I have y2 conjugate. What is the real of y2 conjugate into e2 conjugate? I don't know. I don't know, right? So if I write this in angle, formula, this will be basically y magnitude of y12 angle of minus theta 12, and this will be magnitude of e2 angle minus of delta 2, because I don't know what is the angle here. Delta 2 is the angle of e2. E2 conjugate will have angle of minus delta 2. Angle simply reverses the sign. So that's why if I multiply, E1 has an angle of magnitude of E1 into delta 1. So delta 1 will be with plus sign, minus delta 2 minus theta 1. Minus theta 1 2. Okay. So this is what, this is simply y11, like this is simply the G11 into E1 conjugate, because magnitude of Y11 cos theta 1 is simply G11 plus Y12 into E1 into cos of theta delta 1 minus delta 2 minus theta 2. Now here few important conclusions, right? Few conclusions, important conclusions. So important conclusions. What is the important conclusion? Important conclusion is that if line does not have any resistance, right? So basically your G11 is simply 0. It does not have any real component, right? So your G11 will be simply equal to 0. So if your G11 is equal to 0, this will go away. So only this one will stay. And I know the secondary voltage is generally 1 angle 0, right? So your E2 actually, E2 is 1 angle 0. So basically this formula, your power formula will be equals to magnitude of Y12, magnitude of E1, E2 is magnitude of E2 is 1 cos of delta 1 minus theta 12, because theta 2 delta 2 is simply 0, right? So your formula is this one, right? Now let's apply that here. Let's find out the y parameter here so that I will be able to find out my expression for power. Okay, so what will be the expression for power here? So here, what is y12? What is y12? Y12 is I1 upon V2, right, when V1 is short circuited, right? So I will short circuit the terminal 1, so this will be short circuited. So I have to find out the current I1. So this is my port basically, and I have to find out the current I1 here. What is the current I1 here? If I am providing V2, V2 is here, right? That is 1 angle 0. V2 is 1 angle 0. For that I have to find out the current. So if I am providing some V2, right, here V2 vector, what will be the current here? That is what I want to find out. So here, what do I notice? This point and these point, right? These two are in parallel. Okay, these two are simply in parallel. And here I have V2 connected. So I can reduce this diagram. So basically this much and this much is parallel. Why? Because let's say this is point A, this point C, and this point C, right? So A is common, C and B are ground, right? So both are common. So these two are in parallel. So the parallel combination will be J 0.2 into 0.35. Okay, divide by 0.55. So this will be equals to, right, 0.2 into 0.35 divided by 0.55. So which is 0.123. Okay, that is what the equivalent reactance here is, right? So this circuit, right, will be here. I have 0.1273. This point is ground, right? Again here I have a reactance, right? What is the reactance here? 0.6, and here I am connecting my V2, and here also I have a reactance. So again these two are in series, right? These two are in series. So if these two are in series, I can add these two. So from here I can easily find out what is the current that is coming at this point, right? Ix. So what is Ix? Ix will be V2 divided by, remember this is V2 V2 vector, right? V2 vector divided by this whole impedance to ground. So it is 0.6 plus J 0.7273, right? That is what my Ix is, and this Ix is coming here, right? And from here it is getting divided into two parts. So one of the parts will go here, other part will go here, right? So what is the, it is simply current division, because here the potential is same. So what will be the current I2? I2 is basically minus sign will be there because my I2 is coming in. So not I2, sorry, I1. Okay. So I1 is coming in actually, but it is actually coming, it is going from point A to B, but actually my I1 direction of current is going from B to A, right? So that's why negative sign will be there, and there will be some division of current. It will be simply the opposite reactance upon the overall reactance, right? Opposite reactance is 0.35, right? Overall reactance is 0. 0.55 into Ix. Okay, so your I1 will come out to be minus 0.35 upon 0.55, and J is also there, right? So this will become plus J 0.35 divided by 0.55, then divided by 0.7273, so it comes out to be 0.875 V2. Okay, I1 is this value. So what is the phasor I1 divided by V2? It is simply, that is my Y12, it is simply J, I can write 0.875 angle plus 90. So I can easily find out what is the power expression. So from here I can find out theta 12 is 90 and magnitude of Y12 is 0.875, right? So from here I can easily find out what is my power expression. Power expression is this one, right? I will use this one. So this will be delta 1 is delta only, Y12 magnitude is 0.875, E1 is how much? Magnitude of E1 is 1.05, right? If I remember. Okay, it is not given actually. Magnitude of E is not given. It is EG only. It is EG. EG. Okay. Cos of delta minus theta 1 to cos theta minus 90, or cos 90 minus theta is simply sin theta. So it comes out to be 0.875 EG sin delta. Is it same? Is it same? So if I take the inverse, yes, it is exactly coming same, right? So here, right, what was the power that I derived? What was the power here? If I do this, right, if I further write, so what is the Pmax here? What is the Pmax? So Pmax will be basically 0.875 EG, right? And here what is the Pmax? Pmax here, right, EG divided by 1.1428, right? It is actually 0.875 EG. So I did not tell you this method at the starting because now I want you to do the exercise, because this method actually it's good, start with delta, right? It's good actually, but it is lengthy, but this is shortcut. But I did not want you to teach the shortcut at the starting. I did not want you to teach the shortcut at the starting. I want you to do a bit of hard work. Now things are so simple, right? So with Y parameters, you will easily be able to find out the power expression. But of course, you have to remember few things. If you don't want to remember, then you have to derive, which will take time. But intuitively, you can understand this will anyways go to 0. Only this will be there. And I know, right? Theta 12 will always be 90. Theta 12 will always be 90, right? So theta 12, if it is purely reactive, theta 12 will be 90. So this will be 90. So basically your expression will be magnitude of Y12 into E1 into sine of delta 1. And what will be your Pmax? Pmax expression will be what? Pmax expression will be simply magnitude of Y12 into magnitude of E1. So you just have to find out the magnitude of Y12 and you're good to go. Okay. So this is another elegant method, and trust me, no one will teach you this method, right? So with this, we have comprehensively covered our stability. So it took us around roughly around 12 hours, and in other places in any coaching institute they will teach this in like 5 hours, right? And it's not like I'm extending the duration just for the sake of it, like every single second I'm explaining some important concept, right? So it will take you some, it may take you up to 15 hours to cover this, actually 15 to 20 hours it might take you that, but trust me, whatever stability I've learned, it's the best. Okay, you can compare, like the students who have already studied it, they can comment down below what they feel regarding this stability. Have they studied power system stability like this before? Okay, they can let others know in the comments below. So yeah, I will see you in the next lecture. Until then, happy learning.